Welcome. Tonight, we are going to do something unhurried. We are going to take the whole of computer science, the entire field, from the very first time a human being made a mark to remember a number, all the way to the machines that are learning to write and reason tonight, while you listen. And we are going to do it slowly, in order, without skipping the strange parts, the wrong turns, the forgotten geniuses, and the quiet Tuesday afternoons on which the world changed. There is nothing you need to do. No notes to take, no quiz. If parts of this drift past you, that is fine. If you fall asleep somewhere along the way, that is, honestly, the highest compliment this format knows. The story will keep unfolding either way, patient as the machines it describes. Let me set the question first, because it is a better question than it looks. What is a computer? You probably have a picture, a laptop, a phone, a rack of servers humming in some cold room. But those are computers, the way a piano is a song. The computer, the real one, the one we will spend the next hours understanding, is an idea. And the idea is this: thought itself, the following of rules, the manipulation of symbols, step by patient step, can be done by a machine. That counting, reasoning, composing, deciding, anything that can be written as a procedure, can be executed by something with no mind at all, by gears, by switches, by electrons flowing through sand. That idea sounds ordinary now, because we live inside its consequences. But it is one of the strangest and most consequential ideas our species has ever had, and for most of human history, it did not exist. Someone had to invent it. Several people, in fact, on several continents, over several thousand years, mostly without knowing what they were part of. And the story of how they did it is the story of how a few dozen simple insights, each one small enough to fit on a napkin, stacked on top of each other, until they became the civilization-scale machinery that now mediates nearly every moment of your waking life. Here is where we will go. We will begin before electricity, before machines, before mathematics had a name, on the shore of a lake in Africa, with a bone covered in notches that someone carved 20 or 40,000 years ago, the oldest surviving act of computation we have. We will watch counting turn into numbers, numbers turn into algorithms, and a 9th century scholar in Baghdad lend his name, mangled by centuries of translation, to every procedure that has ever run on any machine. We will sit with Charles Babbage and Ada Lovelace in Victorian drawing rooms, as they imagine, fully, a computer that will not exist for another 100 years. And write the first program for it anyway. Then we will watch the foundations of mathematics crack. In the 1930s, when 3 men, an Austrian logician, an American lambda scribbler, and a quiet Englishman, proved that the dream of perfect mechanical reasoning had limits, hard ones, written into logic itself. And out of that wreckage, improbably, the modern computer was defined. We will follow it into the war, into the secret huts of Bletchley Park and the classified rooms of Philadelphia, where the first electronic giants came alive to break codes and calculate the arc of shells. We will take one apart, slowly, until you can see how it actually thinks, one tiny logical operation at a time. We will watch the transistor shrink the room to a chip, and the chip shrink the computer to a desktop, and the desktop shrink to the slab of glass in your pocket. We will trace the languages, from raw binary to the first compilers, to the languages you have heard of and the ones you have not. Each one a new answer to the same question. How should a human speak to a machine? We will study the algorithms, the invisible recipes underneath everything you have ever searched, sorted, or streamed. And we will stand in front of the deepest open question in the field, the million-dollar question about what can be computed quickly and what, perhaps, can never be. We will map the zoo of all possible machines, from the turnstile to the Turing machine, and we will find computation living in places no one put it, in dominoes, in tiles, in the cells of a children's game. We will build the operating systems, the networks, the internet that began with 2 letters and a crash, the web that a physics laboratory gave away for free. We will open the databases that hold the world's memory, and the ciphers that keep its secrets. And we will walk through the disasters, the rockets that fell, the machines that overdosed patience, the projects that drowned in their own ambition, because this field, more than most, has learned everything the hard way. And then we will arrive at the present. And the present is strange. Machines that learn from oceans of text. Machines that beat us at our oldest games, with moves no human would make. The quantum computers coming slowly into being. The computers grown from biology. The deep claim, argued in the dark, that the universe itself might be made of information. We will go to all of it. And finally, at the very end, we will ask what it was all for, and come back to the bone by the lake. That is the journey. It is long, and we will take all of it. Each part builds quietly on the last, and if you lose the thread somewhere in the middle, do not worry. The themes will return. They always do. This story has a way of circling back on itself, of old ideas reappearing in new machines, of the same few questions being asked again and again across the centuries by people who had no idea the others had asked them. So settle in. Let your breathing slow. We have a bone to pick up, 40,000 years in the past, on the shore of a lake in the highlands of Central Africa. Someone is about to cut a notch into it, and everything follows from that. 20,000 years ago, near a river in what is now the Democratic Republic of Congo, someone picked up the leg bone of a baboon and began cutting marks into it. The bone is about 10 centimeters long. It was thinned down and polished first, and fitted at one end with a small piece of quartz. Then its owner cut notches into 3 of its sides, 168 of them, arranged in 16 groups, laid out in 3 careful columns. In 1950, a Belgian geologist named Jean de Heinzelien found the bone in the remains of a settlement that had been buried by a volcanic eruption. It became known as the Ishango bone, after the place where it lay. And it has been argued about ever since. Some researchers look at the notches and see a tally stick, a way to count things. One notch for one thing caught or stored or owed. Others notice something stranger. The first 2 columns are made up almost entirely of odd numbers, between 9 and 21. Several of them are prime. Some of the groupings relate to each other by doubling and halving. Maybe it was a calendar. Maybe a counting tool. Maybe a game. Nobody knows. What we know is that 20,000 years ago, someone needed to track quantities that memory alone could not hold. So they wrote them into bone. And the Ashango bone is not even the oldest object of its kind. A wolf bone found in Czechoslovakia in 1937 carries 55 notches and may be 30,000 years old. Marks like these go back 35,000 years at least, older than writing, older than farming. The need to count is older than almost everything we call civilization. The tally stick did not disappear with the Stone Age. It became a government technology. In medieval England, the exchequer recorded taxes and debts on sticks of wood. Each stick was notched with the amount, then split down its length into 2 halves. The creditor kept the larger half, called the stock. That is where the financial word comes from. The debtor kept the smaller half, called the foil. When the debt came due, the 2 halves were laid back together. The grain of the wood had to match, and the notches had to match, and forgery was nearly impossible because no 2 pieces of wood split the same way. You did not need to read to trust it. England ran on these sticks for 600 years, and their ending was memorable. The tally system was finally abolished in 1826, and in 1834, workmen were told to dispose of the leftovers. 2 cartloads of old tallies. They fed them into the furnaces beneath the House of Lords. The fire got out of control and burned down the Palace of Westminster, the old Houses of Parliament, destroyed by a bonfire of obsolete accounting technology. Half a world away, another civilization solved the same problem with string. The Inca ruled the largest empire in the Americas, and they did it without writing anything down. What they had instead was the quipu. The word simply means knot. A quipu is a main cord with colored strings hanging from it, sometimes a few, sometimes more than 1,000. On each string, the record keepers tied knots. There were 3 kinds: a single knot, a long knot with extra turns, a figure 8, and the position of a knot on the string worked the way the position of a digit works in our numbers. 1s here, 10s there, 100s above. It was a decimal system made of wool and cotton. Color carried meaning too. 1 shade for llamas, another for soldiers, another for grain. And the records moved. Runners carried quipus along the empire's road system, tens of thousands of kilometers of mountain roads, so that the capital always knew what was stored and owed and harvested at the far edges. About 600 quipus survive in museums today. A Harvard anthropologist named Gary Urton spent his career trying to read them, and he came to believe some of them hold more than numbers. Perhaps narratives. Perhaps the beginning of something like writing, encoded in knots, cut short when the Spanish arrived in 1532. 3 technologies: notches in bone, split wood, knotted string, all doing the same job. The human brain is good at many things, but holding exact numbers over long periods is not one of them. So humans learned to store numbers outside the skull, in objects that never forget and never get tired. The next step was to make the object do more than store the number, to make it do the arithmetic. That object is the abacus. The word itself remembers where it came from. It comes down through Greek from a Semitic word for dust, because the earliest version was a board spread with sand. A Babylonian merchant drew lines in the dust, set pebbles in the grooves, and slid them to add and subtract. The Greeks used a marked slab. One example, the Salamis tablet, survived to be dug up in the 19th century. The Romans shrank the whole thing into a bronze plate small enough to carry. It had grooves, and in the grooves were little sliding stones. The Roman name for those stones was calculi, little stones. Every time you use the word calculate, you are saying little stones in Latin. And somewhere in the phrase, there is a merchant sliding pebbles along a groove. In China, the pebbles moved onto rods. The swan pan, which means calculating tray, has a wooden frame split by a horizontal bar. Above the bar, 2 beads per column, each worth 5. The upper section is called heaven. Below the bar, 5 beads each worth 1. That section is called earth. With 2 heaven beads and 5 earth beads, a single rod can show any value from 0 to 15, which is more than decimal needs. It suited the old Chinese system of weights, which worked in 16s. Written records of the swan pan appear in the 2nd century BC, and it stayed the engine of Chinese commerce for 2,000 years. Japan took the swan pan in through Korea and refined it toward pure speed. Over the centuries, the Japanese version, the soroban, shed beads it did not need. By 1891, it had settled into its modern form. 1 heaven bead, 4 earth beads, exactly what decimal requires, nothing more. And here is the part that still surprises people. The soroban never really lost. In the 20th century, trained soroban operators competed in public speed contests against people using electric calculators, and the abacus won more often than the machine. In 2013, UNESCO listed Chinese bead arithmetic as cultural heritage, and children in Japan still learn on the soroban today. 5,000 years after the first dust board, the abacus is not finished. Europe, though, fought over it, and the fight lasted centuries. On one side stood the abacists, the people who computed on the counting board and recorded the results in Roman numerals. On the other side stood the algorists, a new faction armed with strange new figures from the East, and a different way of computing entirely, with pen and paper and place value. Around the year 1000, a French scholar named Gerbert of Aurillac studied in Muslim Spain, learned the new numerals, and came home to teach them on an abacus of his own design. He later became Pope Sylvester II. Even a pope could not settle the argument. In 1299, the bankers of Florence were forbidden to keep their books in the new figures. In 1348, the University of Padua ordered that book prices be written, quote, not by figures, but by clear letters. The suspicion was practical. A figure could be altered. Turn a 0 into a 6 with one stroke of the pen. A word was harder to fake. There is a famous woodcut from a textbook printed in the early 1500s that shows the whole war in one picture. On one side, Pythagoras sits at a counting board, standing in for the old way. On the other, Boethius writes with the new numerals, standing in for the new. The picture is an anachronism. Neither man used what the picture gives him. But the contest it shows was real, and it did not end until the French Revolution banned the counting board from schools and administration. Only then, around the turn of the 19th century, did the numerals win everywhere. To see why they won, you only have to look at what they replaced. Roman numerals are not a way to compute. They are a way to record. The system is additive. 7 letters: I, V, X, L, C, D, M, standing for 1, 5, 10, 50, 100, 500, 1,000. And a number is just the sum of its letters, with a few subtractive shortcuts bolted on later. There is no place value. The letter X means 10 wherever it sits. There is no 0. Now try it. Multiply 246 by 97 without ever writing an Arabic numeral. You can do it, with training, on a counting board, converting in and out of letters at each end. That is exactly what the Romans did. The numerals never touched the arithmetic. The board did the work. The letters only wrote down the answer. The new system from India did something no additive system could. In it, the value of a digit depends on where it stands. The 2 in 20 means 2 tens. The same 2 in 200 means 2 hundreds. The position carries half the information, which means a small alphabet of 10 symbols can write any number at all, and arithmetic becomes something you do with the symbols themselves, in columns, on paper. Carrying and borrowing are just the place values talking to each other. But positional notation has a hole in it, literally. If position is everything, you need a mark that says this position is empty. Otherwise 61 and 601 collapse into the same marks. The Babylonians hit this problem around 300 BC and patched it with a pair of slanted wedges, a placeholder. It worked with a telling limitation. Their mark only ever appeared between digits, never at the end. It was punctuation, not a number. Turning the placeholder into a number took India. The Sanskrit word for it was shunya, the void. Indian thought was unusually comfortable with emptiness as a concept, and that comfort shows up in the mathematics. In the 5th century, Aryabhata used the placeholder in his astronomical calculations. Then, in the year 628, Brahmagupta did the thing that changed history. In his book, The Opening of the Universe, he treated shunya as a number in its own right and wrote down its rules. A number plus 0 is the number. A number minus itself is 0. 0 times anything is 0. He even wrestled with the one case that still refuses to behave, division by 0, and got tangled, as everyone does. On the wall of a temple in Gwalior, you can still see some of the oldest zeros ever written, inside the numbers 270 and 50, carved into stone. From India, the system traveled west through the Islamic world, and in 1202, it reached Europe in a book by a Pisan merchant's son. Leonardo of Pisa, remembered now as Fibonacci, had been posted as a boy to a trading port in North Africa, and there he watched Arab merchants compute with the Indian figures. He understood immediately what he was looking at. His book, Liber Abaci, the Book of Calculation, demonstrated the new arithmetic to Europe from first principles. He called it the method of the Indians, modus indorum. It was one of the most consequential books ever written, and its whole argument was that counting had been done wrong. Which brings us to Baghdad, and to the man whose name you have been using your entire life without knowing it. Around the year 820, the Abbasid Caliph Al-Mamun presided over an institution called the House of Wisdom. It was a library, a translation bureau, and a research institute in one. Scholars there took in Greek and Persian and Sanskrit texts, translated them into Arabic, and then went further than the texts they translated. The caliph's astronomer and head of the library was a man from Khwarazm, in what is now Uzbekistan, named Muhammad ibn Musa al-Khwarizmi. Al-Khwarizmi wrote a book whose title describes two operations. In Arabic, it is called the Compendious Book on Calculation by Completion and Balancing. Completion, al-Jabr, is the operation of moving a subtracted quantity to the other side of an equation, where it becomes added. Balancing, al-Muqabala, is the removal of equal quantities from both sides. Those two moves, completion and balancing, are the heart of what the book teaches. A systematic way to take an equation and reduce it, step by step, until the unknown stands alone. Al-Jabr, worn down by centuries of use in other languages, became algebra. The book named the field. But the reason the book mattered was not any single result in it. It was the form. Earlier mathematics was largely a heap of specific problems with specific answers. A riddle about dividing grain with its solution. A riddle about an inheritance with its solution. Al-Khwarizmi instead wrote general procedures. If your equation has this shape, do this, then this, then this, and the answer comes out. Every time. Whoever you are. The cleverness moved out of the solver and into the procedure. That move is the birth of the algorithm as an idea, and it happened in a book about inheritance law, land measurement, and commerce, the everyday arithmetic of the caliphate. His other great book was about the Indian numerals themselves. The Arabic original is lost. It survives only in Latin, and the Latin version begins with two words. Dixit algorithmi. Thus speaks algorithmi. Algorithmi was the Latin form of al-Khwarizmi. From that name came the word algorithm, which for centuries meant the craft of computing with the new figures, the craft of the algorists in their long war with the abacists. And over more centuries, the word drifted from the name of the craft to the name of the thing the craft used. Algorithm became algorithm, a step-by-step procedure that solves a problem. Every time the word is used for a sorting method, or a search engine, or a recommendation feed, it is a 9th century scholar from Central Asia, Latinized, still on the page. So the deepest roots of computer science are already here, long before any machine. Store the number outside the skull. Then make the symbol itself do the work. Then write the method down as steps anyone can follow. What is missing so far is any hint that a machine could carry out the steps. The first hint comes out of the sea. In the spring of 1900, a boat of Greek sponge divers from the island of Symi was caught by a storm and took shelter off a small rocky island called Antikythera. While they waited for calm water, they dove. One of them came up terrified, telling of a heap of dead, naked people on the seabed. It was a field of marble statues. They had found a Roman cargo ship sunk around the middle of the 1st century BC, 45 meters down, still holding the wealth of a lost trading voyage. Among the statues and the coins and the amphorae came up a corroded lump of bronze and wood about the size of a shoebox. It was logged and shelved in Athens, and for a while nobody knew what it was. Then it dried and cracked, and someone noticed what was inside the lump. Gears. dozens of them. Bronze gear wheels, precisely cut, meshed in trains. It came to be called the Antikythera mechanism, and it has now been X-rayed, scanned, modeled, and reconstructed for over a century. Here is what it did. You turned a crank on its side. On the front face, pointers swept across dials, showing the place of the sun and the moon against the zodiac, and most likely the 5 planets the Greeks knew. A small ball, half black and half silver, rotated to show the moon's phase. And hidden in that little display is one of the most astonishing details in the whole history of machines. The phase of the moon depends on the difference between the moon's position and the sun's position. To show it, the mechanism had to subtract one rotation from another, mechanically. It does this with an arrangement now called a differential gear, the same principle that lets the drive wheels of a car turn at different speeds around a corner. In bronze. In the 1st or 2nd century BC, there is more. The moon does not move at a constant speed across the sky. It speeds up and slows down. The mechanism models that wobble with a pin riding in a slot on a slightly offset wheel, so the gearing itself breathes, faster and slower, exactly as the moon does. On the back face, spiral dials tracked the 19-year calendar cycle and the 223-month cycle, after which eclipses repeat. Turn the crank far enough, and the machine warned you of eclipses that had not happened yet. There was even a small dial for the 4-year cycle of the Pan-Hellenic Games, including the Olympics. And the bronze plates were engraved with inscriptions that read like a manual, labels, instructions, a description of the cosmos as the machine understood it. For decades, it was dismissed as too advanced to be real. Nothing with gears anywhere near this sophisticated appears again in the historical record until the astronomical clocks of medieval Europe, roughly 1400 years later. We have this one because one ship went down in a storm. Whether it was a lone masterpiece or one of many, nobody knows. But it proves that 2,000 years ago, people were not only counting with machines, they were modeling the heavens with them, computing futures, in bronze. Between the ancient machine and the French teenager, one more quiet invention changed what arithmetic felt like. In 1614, a Scottish laird named John Napier published a table of his own invention, the logarithm, and with it, multiplication became addition. To multiply 2 numbers, you no longer multiply them. You look up their logarithms, you add, and you look up the answer. Long work becomes looking things up, and the astronomers, who multiplied more than anyone, blessed Napier's name for 2 centuries. His humbler gift was Napier's bones, a set of numbered rods that turned multiplication into a mechanical shuffle of strips, the ancestor of the slide rule. And the slide rule itself, 2 marked scales sliding past each other, became the engineer's constant companion for 300 years. It designed the bridges and the rockets, and it went to the moon with Apollo, until the pocket calculator retired it in a single decade. Tables, rods, sliding scales. The theme is the theme of this whole story. Move the work out of the head. The thread picks up again in France in 1642, with a 19-year-old who was tired of watching his father drown in arithmetic. Etienne Pascal was the supervisor of taxes in Rouen, which meant endless columns of figures, added and re-added by hand into the night. His son, Blaise, decided a machine should do it. The result was the Pascaline, a box of wheels and dials. You entered numbers with a stylus, wheel by wheel, and the machine added them. The hard part of mechanical addition is the carry. When a wheel rolls past 9 back to 0, something has to nudge the next wheel up by 1, and that nudge has to ripple across as many wheels as it takes. Pascal solved it with a little lever called the sautoir that lifted and then dropped into place, knocking the carry through. And because French money was not decimal, 12 deniers to a sol, 20 sols to a livre, he built versions whose wheels counted in 10s, 6s, and 12s. He made around 50 of them. It was not the first time a machine had held a number. It was the first time a machine had done the bookkeeping step, the carry, entirely on its own. A small piece of arithmetic had been handed to matter. 30 years later, in Paris, Gottfried Wilhelm Leibniz saw a pedometer and began thinking bigger. He knew of Pascal's machine through Pascal's writings, and he wanted more than addition. Multiplication is just addition repeated, but repeating it by hand is exactly the kind of labor a machine should eat. His answer, worked out around 1672 and built and rebuilt for decades after, was the stepped reckoner. Its heart was a new kind of gear, the stepped drum, a cylinder with teeth of increasing length along it. A sliding gear can sit at any position along the drum, and depending on where it sits, one turn of the drum engages anywhere from 0 to 9 teeth. One crank, and any digit you choose is added. That meant all 4 operations: addition, subtraction, multiplication, division. He showed a wooden model to the Royal Society in London in 1673. Only one original survives, in Hanover. And the stepped drum went on to run inside calculators for the next 275 years, an unbroken reign no other mechanism has matched. But Leibniz is here for 2 other reasons, and both point straight at the future. The first is binary. Leibniz worked out arithmetic in base 2, everything written in nothing but zeros and ones, and published it in 1703. He read it almost mystically. 1 and 0, something and nothing, all of creation drawn out of the void by God. The mysticism is his, but the arithmetic is ours. Every computer on Earth now counts in Leibniz's base. The second is his dream. Leibniz imagined a universal symbolic language in which every idea could be written precisely, and a calculus for manipulating those symbols by rule. When 2 people disagreed about anything he said, they would not need to argue. They would sit down, take up their pens, and say to each other, "Let us calculate." Calculemus. It was the dream of mechanized reasoning, 300 years early. We will meet the 2 men who eventually proved that this dream has a hard ceiling, that not every question can be settled by calculation. That is Gödel and Turing, and they are coming. But the part of Leibniz's dream that does work is sitting on your desk right now. One thread remains in the mechanical age, and it is the one that ties everything else together. It begins with silk. The city of Lyon wove the finest patterned cloth in Europe, and patterned cloth was agonizing to make. A fabric like brocade, with flowers and vines woven into it, required a master weaver, working with an assistant who manually lifted sets of threads, row by row, thread by thread, exactly right, thousands of times. One error ruining the whole. The pattern lived in the master's head and hands. It could not be copied, only relearned. In 1804, Joseph-Marie Jacquard perfected a loom that took the pattern out of the weaver's head and wrote it onto cards. He was building on decades of earlier work: Bouchon's perforated tape, Falcon's hand cards, Vaucanson's automatic mechanism. But his version worked, and it spread. The idea is simple to say. Above the loom, a chain of stiff cards laced together into a loop. Each card controls one row of the weaving. At each position on the card, there is either a hole or there is not. Needles press against the card. Where there is a hole, a needle passes through, and the hook it controls lifts its thread. Where there is no hole, the thread stays down. Hole, no hole. Thread up, thread down. Row after row, card after card, the loom reads the chain and weaves exactly what the cards say. A single elaborate pattern might need tens of thousands of cards. But punch them once and punch them correctly, and the loom will weave that pattern perfectly, forever, as many times as you feed the cards through, with workers who do not need to know the pattern at all. The design had become information, detachable from the craftsman, storable on a shelf, copyable, sellable. Cloth got dramatically cheaper, so cheap that the weavers of Lyon smashed the machines in the streets, because they understood exactly what the cards had done to the value of a lifetime of skill. It would not be the last time a card full of holes did that to a profession. The cards did not stay in the mills. In the 1880s, a young American engineer named Herman Hollerith watched the United States Census drown in its own success. The count of 1880 had taken 8 years to tabulate by hand, and the country was growing so fast that the count of 1890 threatened to outlast the decade itself. Hollerith's answer was a card, one per person, punched with holes for age, sex, birthplace, occupation, and a machine that read the holes electrically. Pins pressed against the card, and where a hole let them through, they touched a little cup of mercury, closed a circuit, and advanced a counter. The 1890 census was tabulated in about a year for a fraction of the feared cost, and the punched card left the loom for good. It became the medium of data itself. Hollerith founded a company to sell the machines, and through mergers, that company became the Computing Tabulating Recording Company. And in 1924, it changed its name to International Business Machines, IBM. The loom's card is the direct ancestor of the entire industry. In 1839, a Lyon weaver named Michel-Marie Carquillat used the loom to weave a portrait of Jacquard himself. Silk, shaded like an engraving, made of about 24,000 punched cards. A picture built entirely out of yes and no, hole and no hole. It is one of the great quiet milestones in human history, because it proved the cards could encode anything you could break into a grid, not only patterns for cloth. Anything. Charles Babbage saw that portrait, and he never forgot it. He kept a copy and showed it to guests at his London salons, because he understood what it really was. And a young woman who visited those salons, and who knew the loom's story, would later write the sentence that closes this part of the story, and opens the next one. The analytical engine, she wrote, weaves algebraical patterns, just as the jacquard loom weaves flowers and leaves. Her name was Ada Lovelace. The cards had taught cloth to remember. The next question was whether they could teach a machine to think. In the early 19th century, the world ran on printed tables of numbers, and the tables were wrong. If you sailed a ship, you found your position with tables, logarithms, trigonometric functions, the movements of the moon for the lunar method of finding longitude. If you built a bridge or an engine, you used tables. If you insured a life or lent money, tables again. And every one of those tables had been computed by people. There were offices full of them, human computers. That was a job title before it was a machine. Rows of clerks, each doing arithmetic all day, passing partial results down the line. Humans get tired. Humans make mistakes. And the mistakes did not stay on the clerk's desk. They got typeset, printed, bound, and sold. And then they went to sea in the captain's cabin. An error in a navigation table was not an inconvenience. It was a ship on the rocks. Charles Babbage knew these tables better than almost anyone alive. He collected them and hunted errors in them the way other men hunted game. And in 1821, sitting with his friend the astronomer John Herschel, checking a set of calculations made for the Astronomical Society, he hit his limit. He is reported to have said that he wished to God these calculations had been executed by steam. It sounds like a joke. It was a career. Babbage's idea was this. Many of the functions in those tables are what mathematicians call polynomials, and polynomials have a beautiful property. Their values can be produced by adding differences. If you know the first few values of a polynomial, you can compute every later value by doing nothing but addition, over and over, in columns. No multiplication, no cleverness, just addition, which is the one thing a machine of gears can do without ever misunderstanding you. He called the machine the difference engine, columns of figure wheels, each wheel holding one decimal digit, each column holding one number. Set the starting values, turn the crank, and the columns add their differences into each other. The carries ripple through, and out come the next values of the function, one after another, forever, without fatigue. And at the end of the machine, a printer. Because Babbage had noticed that even a correct calculation could be destroyed by a tired typesetter. The machine would compute the table and print the table, and no human hand would touch the number in between. The British government saw the value immediately. In 1823, they gave him an initial grant of £1,700. It was the beginning of the most expensive engineering saga of the century. The difference engine required parts made to tolerances that ordinary workshops had never attempted. Thousands of identical wheels and gears and levers, each one precise, because in a machine of addition, one sloppy tooth is one wrong digit, and one wrong digit is the ship on the rocks. Babbage's engineer was a man named Joseph Clement, perhaps the finest machinist in England, and together they pushed metalworking into territory it had never occupied. In 1832, they completed a working section, about 1/7 of the full engine, roughly 2,000 parts. It worked. It computed correctly, every time. You can see it today at the Science Museum in London, and it still works. And then the whole thing came apart. Clement wanted payment terms Babbage would not accept. Work stopped in 1833 and never restarted. The government grants kept arriving in bursts and drying up. Governments fell. Officials changed. During the years of the project, Babbage lost his father, his wife, and 5 of his 8 children. By the time the government finally closed the books in 1842, the Treasury had spent £17,500. The Science Museum likes to translate that sum plainly. It was the cost of 22 brand-new steam locomotives. Most of the 12,000 manufactured parts were eventually melted for scrap. 2 Swedish brothers, Georg and Edvard Scheutz, read about the difference engine and did what England had not managed. They built a smaller version with their own hands in a workshop in Stockholm, largely with their own money. And it worked. Their machines computed and printed real tables and were actually used. The machine England failed to finish was finished by 2 men in a smaller country with a fraction of the money. It is one of the quieter embarrassments in the history of engineering, and the story has a postscript 150 years later. In 1985, the Science Museum in London decided to settle the old question once and for all. Could the Victorians have built it? And if they had, would it have worked? Led by the curator, Doron Swade, the museum built difference engine number 2 from Babbage's own later simplified design of 1847, using only materials and tolerances that Babbage's era actually had. 8,000 parts, 5 metric tons, 11 feet long, completed in 1991 for the 200th anniversary of Babbage's birth. It worked flawlessly, to 31 digits of accuracy. The printer followed in 2002. The design was right all along. The century was wrong. But the difference engine, for all its tragedy, was only the rehearsal. Because while the project was collapsing, Babbage conceived something vastly larger. In 1834, he began designing what he called the analytical engine. And it was not a calculator. It was a computer. The difference engine could do exactly one thing: tabulate polynomials. The analytical engine was designed to do anything. And the way Babbage achieved that was to separate the machine from its instructions. The instructions would not be built into the gears. They would arrive on punched cards, borrowed from the jacquard loom. The cards that wove flowers and leaves in silk would weave arithmetic in brass. Look at the design, and you are looking at the anatomy of every computer ever built since. There was a store where numbers were kept. It was designed to hold 1,000 numbers of up to 50 decimal digits each. There was a mill where the arithmetic happened, able to perform all 4 operations directly. Numbers moved from the store to the mill on one axis, and results returned on another. Ingress and egress, he called them. There were the cards, and the cards came in kinds. Operation cards said what to do. Add, multiply. Variable cards said where to do it, which numbers in the store to fetch, and where to put the result. And there was output, a printer, and even a device to draw curves. 2 features make it unmistakably modern. The machine could branch. If a result came out negative, the cards could direct the machine down one path of instructions, and if positive, down another. Decisions in machinery. And it could loop. A run of cards could be sent through again and again. Even stranger, the machine could punch new cards itself, producing numbers that would later be read back in as input. Its own notes, written to itself for later. A machine that could modify the course of its own work based on what it had already computed. It would have been the size of a small locomotive, and it would have run on steam. Babbage refined the design for the rest of his life. He was still working on a trial piece of the mill on the day he died in 1871. It was never built. And this is where the story's second mind arrives. Ada Byron was born in London in December 1815, the daughter of the poet Lord Byron and his wife Annabella. The marriage collapsed almost immediately. Byron left England, and Ada never met him. Her mother, whom Byron had once admiringly called his princess of parallelograms, made sure Ada was educated in mathematics, rigorously, privately, at a time when almost no girl in England was. Partly it was principle. Partly, by some accounts, it was insurance. Mathematics as a vaccine against poetry. On the 5th of June, 1833, at one of the London salons, 17-year-old Ada met Charles Babbage. He was a widower in his 40s who talked about calculating machines. Days later, her mother brought her to his home in Marylebone, where he kept the working section of the difference engine, and he ran it for them. Lady Byron, who understood more mathematics than most, wrote down what she saw. The machine, she reported, raised numbers to the second and third powers and extracted the root of a quadratic equation. Though she admitted she had only faint glimpses of the principles by which it worked. Ada had more than glimpses. She was captivated, and she and Babbage remained close for the rest of her life. He called her the enchantress of numbers. Life intervened in the usual way. In 1835, she married William King, who became the Earl of Lovelace, and she became the Countess of Lovelace. 3 children arrived in 4 years. But in 1840, she resumed serious mathematics by correspondence, and her tutor was Augustus de Morgan, the first professor of mathematics at what is now University College London, one of the sharpest logical minds of the century. Their letters survive. She did not want answers from him. She wanted the foundations. What exactly is a functional equation? What does an equation of a curve really mean? She wrote to him about her dissatisfaction with her own progress, and then kept going. She called her way of thinking poetical science. She believed imagination belonged inside mathematics, not outside it. Then, in 1842, an Italian military engineer named Luigi Menabrea heard Babbage lecture on the analytical engine in Turin, and wrote an account of it in French. Babbage's friend Charles Wheatstone suggested Ada translate it into English. She did, but she did more than translate. Over months of intense work, in constant letters back and forth with Babbage, she added a set of notes, labeled A through G, and the notes grew to nearly 3 times the length of the original article. The whole was published in August 1843 in Taylor's Scientific Memoirs, signed only with her initials. AAL. Of its 66 pages, 41 were hers. The notes are the reason we are talking about her. The most famous is Note G. In it, she works out how the analytical engine would compute the Bernoulli numbers, a sequence of numbers that appears all over mathematics, defined so that each one is built out of the ones before it. It is exactly the kind of calculation that breaks human computers. Long chains, each link depending on the last. She wrote to Babbage in July of 1843 that she was doggedly attacking and sifting to the very bottom all the ways of deducing the Bernoulli numbers. And notice what she did next. There were simpler ways to compute those numbers on the engine. She deliberately did not use them. Her object, she wrote, was not simplicity or facility of computation, but the illustration of the powers of the engine. She was not solving a puzzle. She was showing what a program was. The result is a large table. Its columns are the variables, the data, and the intermediate results. And as you read down it, you watch the machine work. She described it as a complete simultaneous view of all the successive changes the engine goes through during the calculation. And in the middle of it, there is a line that the History of Science Museum at Oxford translates for us. Where Ada writes, "Here follows a repetition," we would now say, a loop. People call Note G the first computer program ever published, and the historians will gently remind you that Babbage had sketched earlier examples in his private notebooks, and that is fair. But what Ada published was something beyond the program. It was the explanation. The first time anyone showed the public not only that a machine could compute, but how to think about a machine that computes. And then there is the part that reaches forward 100 years. In the notes, Ada argues that the engine is not really about numbers at all. The numbers are just symbols, she saw. And if you can represent something by symbols, the engine can act on it. She wrote that it might act upon other things besides number. And she gave the example that still stops people when they read it. Supposing that the relations of pitched sounds in music could be so expressed, the engine might compose elaborate and scientific pieces of music, of any degree of complexity or extent. A machine writing music in 1843. The loom wove flowers and leaves. The engine, she saw, could weave anything that could be encoded. And yet in the same notes, she drew a firm line. The analytical engine, she wrote, has no pretensions, whatever, to originate anything. It can do whatever we know how to order it to perform. The machine executes. The human originates. A century later, Alan Turing would pick up that sentence and argue with it directly. He called it Lady Lovelace's objection, and much of his famous paper on machine intelligence is an answer to her. We will come to that argument. For now, it is enough to hear the two voices, hers and his, 100 years apart, holding opposite ends of the same question. There is one more scene in the Lovelace story that tells you who she was. As the translation neared publication, Babbage tried to attach to it a long, unsigned attack on the government for its treatment of him. Ada refused. He pressed. She wrote to him, cold and clear, and held the line, and the article went to print as she intended, without his grievance stapled to her work. She was 27 years old. Her health had always been fragile, and after 1843, it failed in earnest. She died on the 27th of November, 1852, of cancer, at the age of 36, the same age her father had been when he died. At her request, she was buried beside him, in the church at Hucknall, next to the poet she never met. The analytical engine existed nowhere but on paper, and her notes existed in one journal, read by almost no one. And then the whole thing slept for 90 years, until a century that had finally built the machine went back and found the book that had described it. In the 1970s, the United States Department of Defense designed a new programming language for its most demanding systems. And they named it Ada. So here is where the story stands as the 19th century closes over them. Babbage had designed a universal machine and could not get it built. Lovelace had explained what a universal machine means and could not get heard. The ideas were all present: programmability, memory, branching, loops, symbols beyond number. Everything except the electricity. And the electricity is coming. But before the hardware arrives, something stranger happens first. Mathematics turns inward and asks what a machine like this could do, even in principle. And the answer contains a wall that no engine, not steam, not silicon, not quantum, will ever get past. That is where we go next. At the end of the 19th century, mathematics was having a quiet crisis about itself. For 2,000 years, mathematics had been the one place where certainty lived. A theorem was not an opinion. Once Euclid proved something about triangles, it stayed proved, through the fall of Rome, through plagues, through everything. But in the late 1800s, strange things started appearing at the foundations, paradoxes. The most famous one came from Bertrand Russell, and it is simple enough to state as a story. Imagine a barber who shaves everyone in town who does not shave themselves, and nobody else. Who shaves the barber? If he shaves himself, then by his own rule, he must not. If he does not shave himself, then by his own rule, he must. Either answer breaks the rule. Russell found the same trap hiding inside the new theory of sets, which was supposed to be the bedrock of all mathematics. The set of all sets that do not contain themselves. Does it contain itself? In 1902, he wrote a short letter about it to an elderly German logician named Gottlob Frege, who had spent his life building arithmetic on pure logic and was about to publish the second volume of his life's work. Frege's reply is one of the saddest notes in the history of ideas. A scientist, he wrote, can hardly meet anything more undesirable than to have the foundations give way just as the work is finished. He published anyway, with an appendix admitting the collapse. Into this shaken world stepped the most influential mathematician alive, David Hilbert of Göttingen. And Hilbert did not want to patch the foundations. He wanted to settle them, once, permanently, with mathematical proof itself. In August of 1900, at the Great International Congress in Paris, Hilbert stood before the mathematicians of the world and gave them a list, 23 unsolved problems chosen as the work of the coming century. Some of them are still open today. But his deeper ambition was bigger than any list. Hilbert's view, called formalism, held that mathematics is a game played with symbols, according to strict rules. If that is true, then the game itself can be studied. you can prove things about the rules. And Hilbert wanted 3 proofs. First, that the rules of mathematics are consistent, that they can never produce a contradiction. Second, that they are complete, that every true statement can be proved from them. And third, the most mechanical wish of all, that there exists a definite procedure, a finite recipe, that can take any mathematical statement and decide, yes or no, whether it is provable. No genius required. Just follow the steps. In 1928, in a logic textbook written with his student Wilhelm Ackermann, Hilbert stated that third wish precisely. It became famous under its German name, the Entscheidungsproblem, the decision problem. They called it the principal problem of mathematical logic. And if it sounds familiar, it should. It is Leibniz's old dream, calculimus, let us calculate, finally written as a formal question. A machine for settling arguments. That is what Hilbert was asking for. Does such a procedure exist? As late as 1930, Hilbert believed the answer had to be yes. He said so, in public, in a way that became legendary. In September of that year, he gave an address in his hometown of Königsberg, and it was broadcast on the radio. He ended it with 6 words that are now carved on his gravestone. Wir müssen wissen. Wir werden wissen. We must know. We will know. And here is the part that feels scripted. The day before that speech, in the same city, at a small conference on the foundations of mathematics, a quiet 24-year-old from Vienna had stood up and, in the politest possible way, ended Hilbert's dream. His name was Kurt Gödel, and what he announced and then published in 1931 was the incompleteness theorem. Here is what Gödel did, in plain language. Take any rulebook for mathematics, any consistent system of axioms and rules, as long as it is powerful enough to do ordinary arithmetic, adding and multiplying whole numbers. That is all the strength it needs. Gödel found a way, inside any such rulebook, to write a sentence that says the following. This sentence cannot be proved from these rules. Now think about that sentence, slowly. If the rulebook can prove it, then the rulebook has proved something false, because the sentence says it cannot be proved. So the rulebook is broken. And if the rulebook cannot prove it, then what the sentence says is true, and the rulebook contains a truth it can never reach. So the rulebook is incomplete. One of those two must happen, in every rulebook rich enough to do arithmetic. There is no third option. Every system strong enough to be useful contains true statements it cannot prove. Truth is bigger than proof. It always was. The trick that made it possible is beautiful, and it is worth knowing by name. Gödel numbering. He found a systematic way to turn every symbol, every formula, every proof into a number. And once statements are numbers, arithmetic can talk about statements. The system can examine itself. Self-reference, built out of multiplication tables. When the paper appeared, it carried a Roman numeral 1 at the end of its title, because Gödel planned a sequel with more detail. The sequel was never written. It did not need to be. Everyone who understood the first paper understood that it was finished. Hilbert's first 2 wishes, consistency and completeness, died that year. But the third wish survived a little longer. The Entscheidungsproblem was still open. Maybe truth outruns proof. Fine. But could there still be a definite mechanical procedure that decides, for any statement, whether it can be proved? That question had a hidden catch, and the catch was the opportunity. To prove that no such procedure exists, you first have to define, with total precision, what a procedure even is. Nobody in history had ever done that. The first person to manage it was an American logician at Princeton named Alonzo Church. Church built an austere little formal system called the lambda calculus, where everything is built from functions applied to functions. And he defined a mechanically calculable procedure as anything his system could compute. With that definition in hand, in a paper published in April of 1936, he exhibited a specific problem that no such procedure can solve. And from that, he showed the Entscheidungsproblem itself has no solution. The answer to Hilbert's third wish was no. Church got there first. But almost nobody outside logic could feel what Church's answer meant, because his formalism did not look like anything. It did not look like a process. It did not look like work. The answer was correct, and it was hard to hold in your hands. The person who made it impossible to ignore was a 23-year-old at Cambridge who had not read Church's paper because it had not been published yet. Alan Turing was born in London in 1912. At Sherborne, the boarding school where the teachers valued Latin and complained about his untidiness, he was the boy who, at 15, wrote a summary of Einstein's theory of relativity for his mother, and who at 16 was solving advanced problems without having been taught the calculus they were supposed to require. He went up to King's College, Cambridge, in 1931, took a first-class degree in mathematics in 1934, and was elected a Fellow of the college in 1935, at 22, for work on the mathematics of probability. That same year, he sat in a lecture course by Max Newman on the foundations of mathematics. Newman had been to the Great Congress in Bologna in 1928, where Hilbert spoke, and he had come home infected with these questions. In his course, he explained the Entscheidungsproblem, and he used a phrase for the kind of procedure Hilbert meant: a mechanical process, something a clerk could do by rote without thinking. Most students heard a metaphor. Turing heard a blueprint. His question became, what does a human computer actually do? Not the romantic version, the physical version. The clerk sits with paper. The paper is ruled into squares. The clerk writes one symbol in a square. The clerk looks at one square at a time. The clerk follows fixed rules, and the rules depend on what the clerk is looking at and on the clerk's state of mind at that moment. And the clerk has only finitely many states of mind. That was Turing's analysis. If that is what computation is, then here is a machine that does all of it. Imagine a tape. It is divided into squares, and it runs as long as you need, forever in both directions. Each square holds one symbol, or sits blank. A head sits over one square. It can read the symbol there. It can erase it or write a new one. It can move one square left or one square right. And the machine itself is in one of a finite number of states. Everything the machine does comes off a fixed table of instructions. If you are in this state, reading this symbol, then write this, move this way, and go into that state. That is the whole machine. No gears specified, no electricity, no size, no cost, no physics. He called it the automatic machine, the A machine. When Church later reviewed the paper, he gave it the name everyone uses now, the Turing machine. It is almost embarrassing how simple it is, and Turing's claim was total. Anything that can be done by following a definite procedure. Anything a clerk by rote can compute. This strip of tape and this table can compute. Every algorithm anyone has ever written, every spreadsheet, every program, every calculation in this video, all of it is this little machine wearing faster clothing. And then Turing did the thing that turns a clever model into the seed of an industry. A machine's whole personality is its table of instructions. And a table is just symbols. And symbols can be written on the tape. So write the table of machine A onto the tape of machine B, and let B read that table, and behave exactly as A would have behaved. One machine that can be any machine. He called it the universal machine. This is the stored program, born in a pure mathematics paper in 1936, 9 years before the first electronic computer existed. Your phone is not 1,000 machines. It is one universal machine. Reading tables. An app is a table. That is the entire idea, and it is right there in the paper. But the paper is famous for something darker, because Turing built the machine in order to find the wall. And here is the wall, slowly, because it is worth following. Some programs halt. They run, they finish, they stop. Some programs never halt. A loop with no exit, running forever. Turing had his own vocabulary for this, a machine that keeps printing its output forever. He called circle-free. A machine that gets stuck in a useless loop he called circular. Now ask the question, could there be a decider? A machine, call it H, that you can feed any program and any input, and that always answers correctly in finite time. This one halts, or this one runs forever. Such a machine would be the end of uncertainty in computing. Does it exist? Assume it does. This is the oldest move in mathematics. Assume the thing exists, and watch what follows. If H exists, you can build a second machine, a troublemaker. Call it D. D does something deliberately perverse. You feed D a program. D turns to H and asks, what happens when this program is fed its own description? Does it halt or run forever? And then D does the opposite of the answer. If H says it halts, D goes into a loop and runs forever. If H says it runs forever, D halts. D is a simple machine to build, if H exists. It is just H plus a little spite. Now comes the step where you should pause the video if you want to, and think. Feed D its own description. What does D do when given itself? D asks H what D does when fed its own description. Suppose H answers. It halts. Then D, by its construction, does the opposite. It runs forever. So H answered wrong. Suppose H answers. It runs forever. Then D does the opposite. It halts. Wrong again. There is no answer H can give that comes out true. If D halts, it runs forever. If it runs forever, it halts. The contradiction is total, and the only assumption we made was that H exists. So H does not exist. No machine can decide the halting question in general. The problem has a name now, the one everyone uses, the halting problem. And with that, the Entscheidungsproblem falls too. There is no procedure that settles all mathematical statements. Hilbert's third wish was No is no, and will always be no. Notice what kind of wall this is. It is not an engineering wall. It does not say our machines are too slow or our tape too short. It says the property itself cannot be computed by anything, ever. Not by gears, not by vacuum tubes, not by the fastest silicon that will ever be fabricated, not by a quantum computer whenever those grow up. Speed does not help. The wall is not about speed. It is about what the word procedure can possibly mean. There is one more way to feel the size of it, and Turing built it into the title of the paper. The paper is called On Computable Numbers. A computable number is a number whose digits a machine can print as far out as you like, given enough time. Pi is computable. The square root of 2 is computable. Every number you have ever used is computable. Now count. Every machine is a finite table of instructions, so every machine can be written down as a finite string of symbols, and finite strings can be listed. 1, 2, 3. The computable numbers can be counted. But Cantor had proved, with his own diagonal argument decades earlier, that the real numbers cannot be counted. There are uncountably many of them. So the computable numbers are a thin, countable dust, and the uncomputable numbers are an ocean beyond counting. Almost every number is unreachable by any procedure. We live, computationally, on a tiny speck of definable ground, surrounded by numbers that no machine will ever print. 2 men answered Hilbert in the same year. Church's paper appeared in April of 1936. Turing finished his in April of 1936 too, before he knew about Church's. And when he learned of it, he added an appendix proving that his computability and Church's effective calculability pick out exactly the same class of problems. Newman had to argue the paper's case before the London Mathematical Society would publish it, because Church had answered first. But the methods were not equal in their fate. Church's answer was a formalism. Turing's answer was a machine you could almost build in a workshop. And it was the machine that the future needed. Turing went to Princeton to study under Church, took his doctorate in 1938, and came home to Cambridge. The 2 definitions being identical, and every other definition anyone has proposed since landing on the same set is now called the Church-Turing thesis. It has survived nearly a century of attempts to break it. So by 1938, the deepest facts were in place. There exists a universal machine. Anything computable, it can compute. And there are questions it can never answer, and neither can anything else. The theory of computing was essentially complete before the first computer. It is like the physics of flight being fully worked out on paper before anyone had built an engine. The timing is what makes your skin tighten. Turing came home in 1938. The next year, Britain was at war, and the British government suddenly had a desperate, secret need for exactly one kind of person. Someone who thought about machines that process symbols. The A machine was about to come off the page, and the first real computers were about to be built in secret, at war, to read messages that were never meant to be read. That is where we go next. The theory of computing was finished in 1936, on paper, before a single modern computer existed. What turned the theory into hardware was not curiosity or commerce. It was the largest war in human history. And the strange thing is, it happened 3 times, in 3 countries, almost independently. So we will take them one at a time. Berlin first, then a Victorian estate in the English countryside, then Philadelphia. In 1935, in his parents' apartment on Metfesselstrasse in Berlin, a young civil engineering student named Konrad Zuse started building a machine because he was tired of doing arithmetic. Civil engineering in the 1930s meant endless structural calculations, long chains of arithmetic done by hand. And Zuse decided a machine should do them. He knew almost nothing of Babbage. He had never heard of Turing, whose paper was still a year away. He worked alone, with his own money, and with parts that other people had thrown away. And from the very first machine, the Z1, he made the choice that everyone else in the world was avoiding. He worked in binary, ones and zeros, open and closed, the system Leibniz had written down in 1703. Everyone else was building decimal machines, machines that counted in tens the way people do. Zuse reasoned that a machine does not have 10 fingers, and that 2 states are easier to hold reliably than 10. A metal plate is slotted, or it is not. He also made another choice that would take the rest of the world decades to catch up with. His numbers were floating point, meaning the machine itself kept track of where the decimal point belonged, the way scientific notation does. So it could handle very large and very small numbers in the same calculation. The Z1, finished around 1938, was mechanical, built from slotted metal plates, and it was unreliable. But its design was right. In 1940 came the Z2, which mixed a relay arithmetic unit with the mechanical memory. And it was enough to convince a German aeronautics research institute to partially fund a fully electrical version. And on the 12th of May, 1941, in the middle of the Second World War, Zuse presented the Z3 to a small audience of professors. The Z3 was built from around 2,000 relays, electromagnetic switches salvaged from discarded telephone stock. It ran at 5 to 10 cycles per second, slow enough that you could hear it think. It computed in binary floating point with 22-bit words. It read its programs from punched holes in discarded movie film. And it handled the awkward cases of arithmetic on purpose. Divide by 0, and it did not crash or lie. It produced a flag for undefined or for plus or minus infinity, and passed that flag correctly through the rest of the calculation. In 1941, it went to work doing aerodynamic calculations, analyzing the flutter of aircraft wings. It was the first fully functional, program-controlled, freely programmable computer on Earth. And almost nobody knew. It lacked one thing, a conditional branch, the ability to choose between 2 paths. And it took until 1998 for a computer scientist named Raul Rojas to formally prove that, even so, the Z3 was universal in principle. Turing complete, before Turing's name was known to its maker. There is one more beat to this story, and it is the painful one. Zuse's collaborator, Helmut Schreier, saw past the relays. In 1942, he built a small experimental computer out of 100 vacuum tubes, electronic switches with no moving parts at all. and it switched at 10,000 cycles per second. He asked the German government to fund a fully electronic successor to the Z3. The request was denied. The reason given was that the project was strategically unimportant. The Allies were, at that moment, spending fortunes on exactly that idea. The Z3 itself was destroyed in the bombing of Berlin. Zuse's company survived, and after the war, his Z4 was leased to the university in Zurich, months before the first American commercial machine was sold. And in 1945, hiding out in a Bavarian village, Zuse wrote down a design for a full programming language, the Plankalkül, the first of its kind in the world. It was not published until 1972. The computer was invented in total isolation, and for years it counted for almost nothing. History, it turns out, runs on networks, not lone geniuses, now England. And to understand England, you have to start in Poland, years before the war. The German military had adopted a cipher machine called Enigma. It was small, electromechanical, built around a set of rotors and a plug board, and every day its settings changed. The number of possible settings was roughly 103 sextillion. You cannot try them all, not by hand, not with any machine anyone could imagine in 1935. The German services relied on that arithmetic. What they did not know was that in 1932, a young Polish mathematician named Marian Rejewski had already broken it. France had passed Poland some leaked documents about Enigma. Rejewski combined those with pure mathematics, the theory of permutations, and reconstructed the internal wiring of a machine he had never held. Then he found the crack in German procedure. Operators began each message by encrypting the message key twice. That small repetition created relationships between the first and fourth, second and fifth, third and sixth letters of every message. And Rejewski turned those relationships into equations, and the equations into the day's settings. By 1938, the Poles had built their own machine to do the searching, the Bomba Kryptologiczna. And in July of 1939, at a meeting in the Pyry Forest outside Warsaw, weeks before the invasion that would destroy their country, the Poles gave their allies everything. The methods, replica Enigma machines, the Bomba designs. Historians still struggle to price that gift. The work moved to England, to a Victorian estate in Buckinghamshire called Bletchley Park, home of the government code and cipher school. And Poland had already taught the British the key lesson, which was that code breaking was no longer a job for classicists and linguists. It was a job for mathematicians. So Bletchley hired mathematicians. Among them were Alan Turing, fresh from the A machine, and Gordon Welchman, a Cambridge algebraic geometer. Working first in the stable yard, they broke wartime Enigma traffic by hand in January of 1940. But hand methods could not keep up with daily setting changes. The process had to be mechanized. The result was the bomb. Turing designed it. Welchman made the improvement that transformed its power, a clever wiring addition called the diagonal board, and an engineer named Harold Keane and the British Tabulating Machine Company built it. The first one, named Victory, went to work in March of 1940. Here is the idea, gently. You still cannot try 103 sextillion settings, so you do not try. You guess a piece of the message instead. A crib. German operators were disciplined, and disciplined people are predictable. There were weather reports sent at the same hour every morning in the same format. There were routine phrases. You take your guessed plaintext, wire its relationship to the intercepted ciphertext into the bomb, and set the drums spinning. 36 Enigma machines worth of drums, turning through rotor settings. The machine is not looking for the answer. It is looking for contradictions. Any setting that produces a logical impossibility is discarded electrically in a fraction of a second. The drums stop when something survives. Human hands test the survivors. What Turing built at bottom is a machine that runs a proof by contradiction at industrial speed. By the end of the war, there were 211 bombs run around the clock, mostly by young women of the Royal Naval Service, the Wrens, working shifts in huts, told nothing of what they were reading. Bound by an oath most of them kept for 30 years. Naval Enigma was the hardest nut, and it mattered the most because the U-boats were sinking the convoys that kept Britain fed. When the naval codes broke, the convoys survived. Historians generally credit the work at Bletchley with shortening the war by years. And Bletchley had a second, deeper secret. Enigma was the battlefield cipher. The German High Command used something far more serious, a teleprinter cipher machine with 12 wheels, the Lorenz, which the British codenamed Tunny. It carried the orders of the highest levels of the German command. Nobody at Bletchley had ever seen one, and a young Cambridge mathematician named Bill Tutt, working from nothing but intercepted encrypted traffic, deduced the entire logical structure of the machine. The number of wheels, the number of pins on each wheel, how they stepped. It remains one of the most astonishing feats of cryptanalysis ever performed. He rebuilt a machine he had never seen from its shadows. But knowing the structure was not enough. Breaking Tunny by hand took weeks, and a message weeks old is history, not intelligence. Max Neumann, the same Neumann whose lectures had set Turing on the Entscheidungsproblem, proposed attacking Tunny mechanically. The first attempt, a relay machine named Heath Robinson, worked barely. Its 2 paper tapes stretched, slipped, and tore, and it was slow. And this is where the post office arrives. Tommy Flowers was a research engineer at the General Post Office's station at Dollis Hill, a working-class Londoner who had put himself through night school, an expert in the switching systems of telephone exchanges. Turing had met him earlier over a small project, and in 1943, Turing introduced him to Neumann. Flowers looked at Heath Robinson and proposed something the establishment did not believe in. Do it electronically. Vacuum tubes, thousands of them. Everyone knew vacuum tubes were unreliable. They burned out, like light bulbs. Flowers knew something everyone else did not, because he came from telephones. Tubes fail when you switch them on and off, and when you push them hard. Leave them running, leave them warm, never push them to their limits, and they run for years. The officials hesitated. Flowers built it anyway, in 11 months, dipping into his own money for parts. They called it Colossus. 1,500 vacuum tubes, reading teleprinter tape at 5,000 characters a second, doing its Boolean logic in parallel, delivering in hours what hand methods delivered in weeks. It was installed at Bletchley in January of 1944. On the 5th of February, Flowers wrote one of the great understated diary entries in the history of technology. Colossus did its first job. Car broke down on the way home. The Mark II, with 2,400 tubes, went into service on the 1st of June, 1944. 5 days later was D-Day, and the Colossi were reading the enemy's highest-level orders. 10 of them ran by the end of the war in purpose-built rooms, tended around the clock. Colossus was the world's first programmable electronic digital computer. It was programmed with plugs and switches rather than a stored program, but it was electronic, it was digital, it was programmable, and it worked. And then the war ended, and it vanished. The machines were dismantled. The drawings were burned. Flowers went back to the post office and was not allowed to say what he had built, or that he had built anything. He watched the 1950s celebrate other men as the fathers of the electronic computer, and could not correct the record. The secret held until the 1970s. He received little recognition in his lifetime, and the job of rebuilding a colossus from fragments and memory, which succeeded in 2007, fell to a volunteer team at the museum that now stands at Bletchley. Now cross the Atlantic, where the same war produced the opposite of a secret. The American problem was ballistics. Artillery needs firing tables. For this gun, this shell, this wind, this angle, the shell lands there. Every entry is a differential equation, and one trajectory took a human computer between 20 minutes and several days on a desk calculator. A table needed hundreds of trajectories. The Army had more than 80 women at the University of Pennsylvania computing trajectories by hand, and hundreds more elsewhere, and the backlog was still growing. The tables were falling behind the guns. At Penn's Moore School of Electrical Engineering, 2 men had an idea. John Bletchley was a physicist who had been dreaming about electronic computation for years, partly out of an obsession with weather prediction. Presper Eckert was a phenomenally gifted young engineer, the one who could actually make temperamental electronics behave. Bletchley was the visionary. Eckert was the builder. And in 1943, the Army's Ballistic Research Laboratory gave them the contract. The machine they built was called ENIAC, the Electronic Numerical Integrator and Computer, 18,000 vacuum tubes of 16 types, 70,000 resistors, 10,000 capacitors, 1,500 relays, 30 tons, filling a room 30 feet by 50, drawing about 140 kilowatts. And it was electronic all the way through, which is the entire point. A relay is a switch with a moving arm. A vacuum tube has no moving parts at all. Only electrons move. So where a relay clicks thousands of times a minute, a tube switches thousands of times a second. ENIAC did 5,000 additions a second. It was roughly 1,000 times faster than any computing device that had ever existed. The trajectory that took a human a day took ENIAC under a minute. 2 details are worth slowing down for. First, ENIAC was decimal. It counted in tens, in ring counters, the way people do. Binary was still the road less traveled. Second, the tubes. Everyone assumed 18,000 tubes meant constant failure, and they were nearly right. Eckert's answer was exactly the one Flowers had found independently in London. Run the tubes gently, far below their ratings, and never switch the machine off. Treat the electronics with kindness, and the electronics behave. But ENIAC had an enormous catch, and everyone involved knew it. There was no stored program. To make ENIAC solve a new problem, you did not type anything. You walked into the machine and rewired it. You replugged dozens of cables and set thousands of switches by hand, and setting up a new problem could take days. Which brings us to 6 names, and you should hear all 6. Kay McNulty, Betty Jennings, Betty Snyder, Marlin Weskoff, Fran Biles, Ruth Lichterman. They were chosen from the pool of women who had been computing ballistics by hand. In 1945, they were handed the logical and electrical block diagrams of a machine that was still being built, and nothing else. There was no manual, because nobody had ever written one. There were no programming languages, because there were no programming languages. They taught themselves the machine from the diagrams. They figured out how to decompose a differential equation into the machine's operations. They invented flowcharts to plan programs and wrote the programming sheets. And then they physically rewired 30 tons of hardware to make the mathematics run. When the machine misbehaved, they debugged it, tracing signals through the cables. Jean Bartik said it plainly years later. The ENIAC was a son of a bitch to program. These 6 women went from being computers to commanding one. They were the first programmers of the first general-purpose electronic computer. ENIAC was completed too late for the war it was built for. Its first real production task, in December of 1945, was a classified calculation for Los Alamos, for the scientists working on the hydrogen bomb. The public unveiling came on Valentine's Day, 1946. The press saw the machine. The 6 programmers were not at the celebration dinner, and their role disappeared from the record for nearly 50 years. The correction has been slow. In 1997, they were inducted into the Women in Technology Hall of Fame. And in 2023, the United States Army began naming its new supercomputers after them. All 6. And now, the last scene of this part, the one the whole future hangs on. In the summer of 1944, Herman Goldstein, the Army's liaison officer on the ENIAC project, found himself on the train platform at Aberdeen, Maryland, with the most famous mathematician in America, John von Neumann, consultant to the Manhattan Project, founder of game theory, a mind that colleagues described with a kind of awe. Goldstein told him about the secret machine. Von Neumann started visiting the Moore School, and he joined the discussions everyone was already having about the successor machine, the EDVAC, and about its central idea. Because everyone could see the flaw. The program lived in cables, and the fix had been floating around the Moore School for months. Store the instructions in the machine's memory, right alongside the numbers. Then, changing what the machine does is loading different symbols, not rebuilding the hardware. Instructions as data. If that sounds familiar, it is exactly the idea at the heart of Turing's universal machine from 1936. The table, on the tape, on the 30th of June, 1945, a 101-page typescript was mailed out across the United States and Britain. first draft of a report on the EDVAC. It described, for the first time in writing, the complete logical design of a stored program computer, a central arithmetic organ, a central control, a memory, input and output, instructions and data living together in the same read-write memory. That anatomy is the anatomy of every computer built since, and it is still called the von Neumann architecture because the report carried one name, his. And that is a controversy you should know about. Goldstein had distributed the draft without asking von Neumann, and the name on the cover meant the world attributed the stored program idea to him alone. Eckert and Mauchly believed, and said for the rest of their lives, that the ideas were the Moore School teams, discussed in detail for months before von Neumann ever arrived. The instant, wide distribution of the report also destroyed their ability to patent the concept. The quarrel ran for decades and ended in court in the 1970s. What no one disputes is the importance of the idea itself. And the deeper truth is that the idea was never really anyone's. It had been sitting in a mathematics journal since 1936, waiting for the hardware to catch up. One more name belongs in this part, because the courts eventually put it there. In Iowa, between 1939 and 1942, a physics professor named John Atanasoff and his graduate student Clifford Berry built a small electronic digital machine, binary, using vacuum tubes to solve systems of linear equations, the Atanasoff-Berry computer. It was special purpose, it was temperamental, and it was forgotten until a federal court case in 1973, Honeywell versus Sperry Rand, threw out the ENIAC patent entirely, ruling that its ideas derived in part from Atanasoff, whom Mauchly had visited in 1941. The invention of the computer has no single parent. It has a crowd spread across a planet at war. So take stock of where we are, because it is remarkable. In 1936, computing was a thought experiment about a clerk and a paper tape. 10 years later, there are electronic machines 1,000 times faster than anything before them, programs stored in memory, and the certain knowledge proved of what such machines can and can never do. The war made the computer real, and then it ended, and the machines came blinking into the light, into a world about to remake itself around them. We have spent 5 parts on where the computer came from. Now, before we watch it shrink onto a chip and wire itself into every corner of life, we should do the honest thing. We should stop, open one of these machines, and slowly, carefully, answer the simplest question of the entire video. What is a computer actually doing when it computes? That is next. We have watched the computer arrive, 5 parts of history, and now the machines exist, electronic, programmable, real. So this is the moment to do the honest thing. Pick up the device nearest to you, a phone, a laptop, it does not matter, and ask the simplest question of the whole video. What is it actually doing right now when it computes? The answer is one trick. One single trick, repeated billions of times per second. And the trick is so simple that by the end of this part, you will understand all of it in principle, genuinely. Not a metaphor for the machine. The machine. It begins with a switch. A switch has 2 positions, on and off. Current flows. or it does not. And the entire computer, all of it, every photo, every message, every game, every calculation, is built on a decision that was made before the hardware even existed. The decision to work with 2 states instead of 10. Ask why. Because the answer is the foundation of everything. A signal that only ever has to answer one question. Are you on or are you off? Is a signal that can survive the real world. Heat, age, electrical noise, interference from the cable next to it. If a machine tried to tell 10 voltage levels apart, 10 little steps between 0 and full, then dirt and heat and time would blur the steps into each other, and the machine would start to guess. And a computer that guesses is a paperweight. 2 states do not blur. There is a wide, empty margin between fully on and fully off, and the machine never has to sit in it. A 1 is a high voltage. A 0 is a low voltage. Nothing in between counts. Reliability is why the digital world is binary. Not because 2 is elegant, because 2 is safe. So the numbers inside are written the way Leibniz wrote them, 3 centuries early. Base 2. The place value system you already know, except each column is worth 2 times the one before it, instead of 10 times. 1s, 2s, 4s, 8s, 16s. Count upward and watch how it goes. 0, 1. And now you're out of digits, so you carry, exactly like school. 1 0 is 2. 1 1 is 3. Carry again. 1 0 0 is 4. The number 13 becomes 1 1 0 1. An 8, a 4, no 2, and a 1. Each symbol in that string is a binary digit, and the word for it has its own small history. In January of 1947, in a Bell Labs memorandum, a statistician named John Tukey contracted the phrase binary digit into a single word, bit. Claude Shannon picked it up the next year and put it into the most influential paper in the history of communication. And the word stuck to everything. Tukey, as a side note, also coined the word software. Some people get to name the world twice. That is half the trick. The machine holds 2 states, so numbers live inside as bits. The other half of the trick is older than electricity. It is logic. In 1854, an English mathematician named George Boole published a book called The Laws of Thought. And in it, he did something that looked like a philosophy exercise. He turned reasoning into algebra. In Boole's system, statements are true or false, 1 or 0. The word and behaves like multiplication. The word or behaves like a careful kind of addition. And the whole system rests on one strange little law. In ordinary algebra, x times x is x squared. In Boole's algebra, x times x is just x. 1 times 1 is 1. 0 times 0 is 0. That one law is the difference between arithmetic and logic, and for 80 years it lived in books of philosophy. Then, in 1937, a 21-year-old master's student at MIT named Claude Shannon spent a summer at Bell Telephone Laboratories, playing with switching circuits. And when he came home, he wrote a thesis built on a single observation. An observation so simple that you can hold all of it in one sentence. A switch is Boole's algebra made of metal. Wire 2 switches in series, one after the other, and current flows only if the first and the second are closed. That is the AND operation. Wire them in parallel, side by side, and current flows if the first OR the second is closed. That is OR. A switch that is wired backward gives you not. So any statement of logic, anything Boole could write, Shannon could build out of relays. And because it was algebra, you could simplify a circuit the way you simplify an equation. Fewer switches, same behavior. The thesis appeared in 1938, and it has been called the most important master's thesis ever written. Zeus had found the same idea alone in Berlin, working with telephone relays, unaware of Shannon. But it was Shannon's version the world read, and from that year on, logic was something you could wire. Shannon was not finished. 10 years later, in 1948, he published a mathematical theory of communication and founded an entire field in a single paper. Information theory. The core idea sounds like a riddle until it clicks. Information is surprise. A message that tells you what you already expected carries almost nothing. A message full of the unexpected carries a lot. Shannon gave surprise a measure and called it entropy. And from that one move came two limits that run your life. The first is compression. No file can be squeezed smaller than its entropy without losing something. Every zip file, every photo, every song you stream is negotiating with that limit. The second is stranger, and it concerns noise. Intuition says that sending data down a noisy channel, a crackling line, a scratch on a disk, means errors are inevitable. Shannon proved the opposite. With a little clever redundancy, you can speak through the noise as reliably as you like, up to a speed limit set by the channel. Error-correcting codes are why a scratched disk still plays, why a damaged QR code still scans, why a spacecraft whispering from the edge of the solar system still arrives intact. The man who taught switches to do logic also taught the world what a message is. Now comes the construction, and we will go slowly, because this is the heart of the machine. A gate is a tiny circuit that answers one fixed question. The AND gate asks, are both of my inputs 1? The OR gate asks, is at least one of my inputs 1? The NOT gate flips whatever it sees. And there is one more you should meet, because it is about to do something important. The exclusive OR, written XOR. It asks, are my two inputs different? 1 gives 0, 1 gives 1. Different is 1, same is 0. Here is the complete rulebook for adding two binary digits. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is 2, which in binary is 1, 0. So you write down a 0 and carry a 1. Look at what that rulebook actually produces. Two outputs. The digit you write down and the carry. The digit you write down is 1 exactly when the two inputs differ. That is XOR. The carry is 1 only when both inputs are 1. That is AND. So adding 2 bits is 2 gates. 1 XOR for the digit, 1 AND for the carry. That little circuit has a name, the half adder. A full column of addition also has a carry arriving from the column before. So a full adder takes 3 inputs, the 2 digits, and the incoming carry, and it is built from 2 half adders plus 1 OR gate. And then you chain them. Line up 32 full adders, the carry out of each one feeding the carry in of the next, and the machine can add any two 32-bit numbers. The carry ripples down the chain, so it is called a ripple carry adder. And it is the schoolbook column method, electrified. 64 bits is the same chain, longer. That is it. That is addition. And the rest of arithmetic is addition in costume. Subtraction is done by a trick called 2's complement. Flip every bit of the number you are subtracting, add 1, and then add. The circuit does the rest. Multiplication is addition with shifting, the way you multiply in columns on paper. Division is subtraction with shifting. By the end, the arithmetic unit inside a real processor, the part that computes, is the same few gates, repeated, arranged with care. And here is the detail that makes engineers smile. You do not even need the variety of gates. In 1913, an American logician named Henry Scheffer proved that a single operation is enough. The operation is called NAND, short for not, and it answers, are my inputs anything other than both 1? From NAND alone, you can build everything. Tie its 2 inputs together, and it becomes a NOT, since it flips whatever it hears. Put that NOT after a NAND, and you get AND. Invert both inputs first, then NAND them, and you get OR. And that last step uses a law from Augustus de Morgan, the same de Morgan who once tutored Ada Lovelace by post. From NOT, and OR, you can build every gate, every adder, every circuit in this story. A modern chip is, at the bottom, a sea of one kind of gate, repeated billions of times. And the computer that flew to the moon, the Apollo guidance computer, was built from a single type of chip, one little package containing NOR gates, thousands of identical copies of one logical move. Sameness is not a limitation. Sameness is the manufacturing miracle, so the machine can compute. Now, it has to remember. And memory, in the early years, was the hardest problem of all. The first solutions were strange and wonderful. There were mercury delay lines, tubes filled with liquid metal, where a bit was converted into a ripple of sound at one end, traveled the length of the tube at the speed of sound, was picked up at the far end, amplified, and sent around again. The machine's memory was sound, circling in mercury, forever, until the machine changed it. It came out of radar research from the war. It worked, but you had to wait for your bit to come around, like waiting for a suitcase on an airport carousel. EDSAC used delay lines. So did UNIVAC. Then there was the Williams tube. Freddie Williams and Tom Kilburn at Manchester took a radar display, an ordinary cathode ray tube, and used its screen as memory. A bit was a dot of electric charge on the phosphor, and the machine could read the dots back electronically. Any dot, at any moment, in any order. No carousel. That is the first electronic random access memory, and to test it, they built a small machine around it. We will come back to that machine in a minute, because it made history. And then came the technology that ruled computing for 20 years. Core memory. At MIT, an engineer named J. Forrester was building Whirlwind, a computer meant to run in real time, fast enough to simulate an aircraft while it flew. And real time demanded a memory faster and steadier than anything around. Forrester's answer was a grid of tiny magnetic rings, each one smaller than a pinhead, each one strung at the crossing of fine wires, like beads on a loom. send current through the right pair of wires, and one ring flips its magnetism. Clockwise for 1, anti-clockwise for 0. Read it back by watching which wire pulses. 1 ring, 1 bit, and the ring remembers with the power off, because magnetism does not leak away. The first big array was installed on Whirlwind in the summer of 1953, and the access time fell to 9 microseconds, and reliability jumped. And within a few years, every serious computer in the world had a woven core of little rings at its heart. The Apollo spacecraft carried a form of core memory to the moon, literally woven by hand by textile workers. And the word never left the language. When a program crashes today, and the system writes out its memory for inspection, we still call it a core dump, 50 years after the last core was strung. Now assemble the whole machine. Watch, because it is only 4 ideas. First, the memory. It holds numbers, both kinds of numbers, the data and the program, because an instruction is also just a pattern of bits, and a pattern of bits is a number. This string means add. This string means store. This string means jump to a different instruction if the last answer was 0. The program sits in memory next to the data, and that, physically, is the stored program idea from the EDVAC report, which is the universal machine from 1936, which is the table on the tape. The machine reads a number, and the number changes what the machine does. Second, the registers. A handful of tiny, fast memory cells right next to the arithmetic circuits, holding the numbers being worked on at this exact instant. Third, the arithmetic and logic unit, the adders and gates from a moment ago, wired so the control can route numbers through them. Fourth, the control unit, running the simplest loop in the world. Fetch the next instruction for memory. Decode it. Read the pattern. Ah, this pattern says, add the number in this memory cell to the one in that register. Execute it. Then fetch the next. Fetch, decode, execute, over and over. A quartz crystal, vibrating at a fixed, precise rate, paces the loop like a metronome, and the speed of that metronome is the number you see in advertisements. 3 gigahertz means 3 billion beats per second. 3 billion fetch, decode, execute. And there is nothing else. There is no other part. There is no understanding hiding in a corner of the chip. Every program ever run is this loop, running very fast on very simple instructions over gates made of one logical move repeated 1 billion times. When people say computers are mysterious, this is the thing to remember. The mystery is speed and scale. The machine itself is patience. Now watch it happen for the first time. June the 21st, 1948, Manchester. The small-scale experimental machine, quickly nicknamed the Baby, built by Williams and Kilburn out of war surplus parts, never meant to be a real computer at all. It existed to test the Williams tube. Tom Kilburn wrote a program for it, 17 instructions long, to find the highest proper factor of a number by trying each candidate in turn, dividing by repeated subtraction. They set the number to 2 to the 18th, 262,144, laboriously inserted the program, and pressed the start switch. Williams wrote about that morning later, and his words are worth hearing whole. A program was laboriously inserted, and the start switch pressed. Immediately, the spots on the display tube entered a mad dance. In early trials, it was a dance of death, leading to no useful result. But one day, it stopped. And there, shining brightly in the expected place, was the expected answer. It was a moment to remember. This was in June 1948, and nothing was ever the same again. 52 minutes. 2 million instructions. The first time in history that a program stored in a writable electronic memory ran on Earth. The machine had no cables to replug. You changed its mind by writing different numbers into memory. Software had begun. 11 months later, on the 6th of May, 1949, at Cambridge, Maurice Wilkes switched on EDSAC. Wilkes had read the EDVAC report in 1946 and attended the lectures at the Moore School, and he came home with a deliberate goal. Not a demonstration, a service. EDSAC computed a table of squares on its first day, and then went to work for the university. And that is its real claim on history. It had users. Scientists from across Cambridge brought it problems. A committee allocated machine time, the way telescope time is allocated today, and its team invented the working tools of programming. A young man named David Wheeler invented the subroutine, the idea that a piece of a program, written once, could be called up by any program, anywhere. And he wrote the initial orders, the little resident program that loaded all the others. In 1951, Wilkes, Wheeler, and Stanley Gill published the preparation of programs for an electronic digital computer. The first programming textbook, EDSAC, is where computing stopped being a stunt and became a practice. And at Princeton, between 1946 and 1952, von Neumann and his chief engineer, Julian Bigelow, built the machine at the Institute for Advanced Study, and they did something as important as the machine itself. They gave the design away. Progress reports, visits, letters, no secrecy. 17 machines around the world were built as copies or near copies, including one at Los Alamos called Maniac, which did the calculations for the hydrogen bomb. The architecture of the machine you are listening to this on was settled in those years, in that basement, and distributed for free. So by the early 1950s, everything in this part is in place. Binary, gates, adders, memory, the fetch and execute loop, the stored program, the computer, as an idea, is complete. What remains is everything about scale, because those first machines were rooms. Hot rooms, drinking the power of a small town, built from tubes that burned out and delay lines full of mercury and cores woven by hand. Every one of them was a prototype for a world that could not afford a prototype per person. The whole future depended on finding a better switch. Something with no filament to burn out, no heat, no vacuum. And it was found in 1947 in a slab of crystal that barely conducts electricity at all by 3 men at Bell Labs who famously could barely stand each other. The transistor is next, and it does not only shrink the computer, it shrinks the price of a switching action so far that computation becomes, effectively, free. That changes the world more than any calculation ever will. By the early 1950s, the computer exists, and it is magnificent. And it is a monster. It fills rooms. It glows, literally, with the heat of thousands of vacuum tubes, each one a little light bulb wired to switch on and off. And the tubes are the weakness. They burn out. They drink power. They are made by hand, one at a time, the way light bulbs are made. ENIAC's builders found, as Tommy Flowers had found, that the machines only survived if you never switched them off and never pushed them hard. The entire future of computing is sitting on top of the most fragile component in electronics. Everyone knows the tube cannot be the final answer. At Bell Telephone Laboratories, one man had been betting on that for a decade. His name was Mervyn Kelly, and his problem was telephones. By the 1930s, the Bell system was a continent-wide machine made of two unreliable parts: electromechanical relays, millions of them, clanking away in switching offices, connecting calls, and vacuum tubes, amplifying voices across long lines, glowing hot, burning out. Kelly became director of research in 1936, and he started hiring solid-state physicists, people who studied the strange electrical behavior of crystals, in the hope that a crystal might one day replace both. His very first hire for the program was a young theorist from MIT named William Shockley. The crystals they were betting on were semiconductors, materials that conduct electricity badly. Not conductors, not insulators, something in between. And they were not new. The earliest radios, the crystal sets that hobbyists built in the 1920s, worked with a lump of galena crystal and a fine wire called a cat's whisker, which you moved around the crystal's face, hunting for the magic spot where the signal appeared. A semiconductor junction, found by feel, in millions of living rooms. Nobody understood why it worked. The physics of the almost conductor was a mystery with a knob on it. Then the war came, and the work paused. And in 1945, Kelly sent Shockley back to the problem with a proper group around him. And this is where the two other names enter. Walter Brattain, the experimentalist, a man who could make any piece of apparatus behave. And John Bardeen, the theorist, quiet, devastatingly deep, the only person in history to win the Nobel Prize in Physics twice. Their first idea failed. Shockley had a theory that an electric field applied to a semiconductor should control the current through it, like a valve. The experiments showed nothing. No effect. It was Bardeen who saw why. The surface of the crystal, he argued, was covered in trapped electrons, a skin of surface states that shielded the inside of the crystal from the field. The theory was fine. The surface was in the way. So they turned the whole group to studying the surface itself, and in November of 1947, Brattain found a way to neutralize the shielding. And then, in the space of a few weeks, in a fourth-floor lab in Building 1, they stopped trying to push a field into the crystal and instead pressed two tiny gold contacts against a slab of germanium, spaced a hair's width apart. Brattain wrapped gold foil around a plastic triangle, sliced through the gold at the tip with a razor, and pressed it gently onto the crystal. Two contacts, closer than anyone had achieved. On December 16, 1947, a small signal on one contact came out of the other one, amplified. A crystal, with no vacuum, no filament, no heat, controlling current with current. On December 23rd, they demonstrated it to Bell Labs executives. Someone called it a magnificent Christmas present. One person was notably absent from that room. Shockley, the group leader, had not been present for the breakthrough. And he knew what that meant for the history books. What happened next is the part of the story that tells you about scientists as people. Shockley went away, and over the following weeks, he drove himself into a solitary fever of work. And he came back with a better transistor. Not 2 point contacts on a surface, but a sandwich. A layered junction of treated semiconductor, which he designed from theory in January of 1948. The junction transistor was rugged, predictable, manufacturable. It is the design that actually went into production. Bardeen and Bratton got the breakthrough. Shockley got the device. In 1956, all three shared the Nobel Prize, and by all accounts, the celebration was strained, because by then, they could barely stand one another. Bell Labs announced the transistor at a press conference on June 30th, 1948. The press barely noticed. There were a few column inches here and there, and that was all. The first commercial use was modest. Hearing aids in 1953, where a small, cool amplifier was worth real money. Then, for Christmas of 1954, came the Regency TR-1, the first transistor radio. 4 transistors, $50. And for the first time, music went portable. A generation of teenagers carried the future in a jacket pocket without knowing that is what it was. And here, the story picks up its most consequential thread. In 1956, fresh from the Nobel Prize, Shockley left Bell Labs and started his own company, Shockley Semiconductor, in a former fruit packing shed in Mountain View, California, near where he had grown up. He recruited brilliant young scientists and engineers from across the country. And then he managed them badly. Distrust, secretiveness, erratic direction, and a research obsession with a 4-layer diode that nobody else believed in. In September of 1957, 8 of his best people walked out together. Gordon Moore, Robert Noyce, John Horney, Jay Last, Sheldon Roberts, Eugene Kleiner, Julius Blank, Victor Greenwich. Shockley called them traitors, and the name stuck. The Traitorous 8. With backing from Fairchild Camera and Instrument, $500 of their own money each, they founded Fairchild Semiconductor. It is hard to overstate what Fairchild became. It was the seed crystal of Silicon Valley, a phrase that did not exist yet. Fairchild alumni went on to found Intel, AMD, and dozens of other companies. The culture of the modern technology industry, young engineers, stock options, spin-outs, restless talent, is the culture of that walkout. And 2 of Fairchild's people are about to solve the next wall. Because by the late 1950s, there was a new bottleneck. And this one was conceptual. It was called the tyranny of numbers. Circuits were growing. A serious machine needed thousands, then tens of thousands of components. And every single component was manufactured separately and then wired to the others by hand. Every joint was a cost and a failure point. You could design a computer you could never build because the wiring would defeat you. The parts had gotten small. The connections had not. At Texas Instruments in Dallas, in the summer of 1958, a newly hired engineer named Jack Kilby did not yet have enough seniority to take a vacation. So while the plant emptied for the summer break, Kilby sat in the quiet lab, and thought about the tyranny of numbers. And he had the idea. What if the whole circuit, transistors, resistors, capacitors, everything, was made from the same single piece of semiconductor? Not assembled, carved. One block of material, everything formed inside it. In September, he built it, a sliver of germanium the size of a fingernail clipping, with the components formed in the crystal and joined by fine gold wires. On September 12, 1958, he showed it to TY's management. He pressed a switch, and an oscilloscope showed a clean, continuous sine wave. The integrated circuit worked. Kilby said later, looking back, that what they did not realize then was that the integrated circuit would cut the cost of an electronic function by a factor of 1,000,000 to 1. Nothing had ever done that for anything before. Kilby's circuit proved it could exist, but it could not be manufactured. Those gold wires, the flying wires, were still attached by hand. The man who made it manufacturable was Robert Noyce at Fairchild, and he did it standing on the work of his colleague, John Horney. Horney had invented what is called the planar process, building the transistor into the flat surface of a silicon wafer and protecting it under a layer of silicon dioxide, glass, grown right on the crystal. And Noyce saw what that allowed. If the components live in the flat surface, you can print the wiring on top of them. Aluminum traces laid down in the same photographic process. All at once, no hands. In January of 1959, months after Kilby's demo, and unaware of it, Noyce wrote out his own version of the integrated circuit. Kilby showed it was possible. Noyce showed how to print it. The patent fight lasted years and ended with both men recognized as co-inventors. In 2000, Kilby received the Nobel Prize for it. Noyce had died in 1990, and the prize is never given posthumously. And now, the stage is set for the most famous prediction in the history of technology. In 1965, the editor of Electronics magazine asked Gordon Moore, then Fairchild's director of research, to write about the future of integrated circuits. Moore had a notebook with cost curves, and he plotted what he had. 5 data points from 1959 to 1964. The number of components on the most economical chip, doubling roughly every year. He drew a straight line through them, and he extended it. The article, Cramming More Components onto Integrated Circuits, came out on April 19, 1965, and it said the doubling would continue for at least 10 years. 65,000 components on a chip by 1975. Moore himself later called it a wild extrapolation. In 1975, he revisited it and relaxed the doubling to every 2 years. And by then, it had a name, Moore's Law, coined by Caltech's Carver Mead, and it had stopped being a prediction and become something stranger, a target. The entire semiconductor industry organized its research roadmaps around it, generation by generation, year after year. And so the extrapolation fulfilled itself. And underneath it sat a gift from physics, worked out by Robert Dennard at IBM in 1974. Dennard scaling. When you shrink a transistor in just the right proportions, it gets faster and cheaper and uses no more power per area. Smaller meant better in every direction at once. For 30 years, Every shrink was a free lunch, and the free lunch compounded. 2,300 transistors became billions. The same room-sized logic, then a desk, then a pocket, then a speck. And the moment the whole computer lands on a single chip is a story worth telling on its own, because it began as a calculator contract nobody wanted to overthink. In 1969, a Japanese company called Busicom came to Intel, a young memory chip startup founded the year before by Noyce and Moore, with a commission. 12 custom chips for a new printing calculator. An Intel engineer named Ted Hoff looked at the 12-chip design and disliked it. Too complicated. He proposed the opposite. Instead of 12 chips, each hardwired to do one job, make 4 chips, and let one of them be a general-purpose processor. A small computer, programmable, that could be made to do the calculator's job with software, and anyone else's job tomorrow. Busicom's managers, to their credit, chose it. Partly because they understood such a chip could be sold far beyond calculators. Federico Fagin, who had invented the silicon gate technology the design required, led the actual chip design, working with Busicom's Masatoshi Shima, with Stan Mazer on the architecture. In March of 1971, the first working Intel 4004 was delivered. 2,300 transistors, a whole central processor on one chip, the fetch and execute loop from the war years, miniaturized into something you could lose in the seat cushions. Intel announced it to the world on November 15th, 1971, with a slogan that turned out to be literal. A new era of integrated electronics. The computer had become a component. You could buy computation the way you buy screws. And once computation is a commodity, it stops belonging to institutions. January 1975. The cover of Popular Electronics shows a plain blue and gray box with rows of switches and little red lights. The Altair 8800, $439, as a kit from a tiny company called MITS in Albuquerque, built around Intel's 808. Oh, the 4004's grown-up descendant. The machine on the cover was an empty box, by the way. The only working prototype had been lost in shipment to the magazine, so they photographed a shell. It did not matter. Orders flooded in by the thousand from hobbyists who had waited their whole lives for exactly this. 2 young programmers, Bill Gates and Paul Allen, saw the cover and wrote a basic interpreter for a machine they did not yet possess, and called their new venture Microsoft. The Homebrew Computer Club started meeting in a garage in Menlo Park, and one of its members, Steve Wozniak, wanted to build a computer his friends could actually use, and his friend, Steve Jobs, wanted to sell it. In 1977, the dam broke for good. The Apple II, the Commodore PET, the Radio Shack TRS-80, all in 1 year. The computer left the institution and entered the home. Now step back and look at the arc of this one part. In 1947, the switch was a crystal with 2 hairs of gold wire demonstrated to a room of unimpressed executives. 24 years later, the entire computer was a product in a catalog. The hardware revolution is complete. The machine is small, cheap, reliable, and everywhere. But notice something. Owning one did not mean you could use one. The early owners of these machines programmed them the hard way, flipping the front panel switches, one instruction at a time, in raw binary. The machine had become simple. Talking to it had not. And that gap between what the hardware can do and what a human can say to it is the next great story. Because in the same decades, another revolution was running in parallel. A revolution not of circuits, but of language. How a woman who had programmed the Mark I at Harvard decided that programmers should write in English, like words, instead of codes, and was laughed at, and was right. How software learned to write software. The story of programming languages is next. The hardware revolution is complete. The machine is cheap, small, reliable, and spreading. And now we hit the problem that will occupy us for this entire part. The machine only understands numbers, long strings of binary digits, each string an instruction, each instruction one tiny step. Add this to that, store this there, jump if 0. Every program ever written is at the bottom, that. And a human being cannot think in that for long. The ENIAC's programmers proved humans could do it, at heroic cost. The question of the next 70 years is how to do it without the heroism. The first step up was small, but real. Assembly language. Instead of writing the raw number for an instruction, you write a short mnemonic. 3 letters for add. The machine's own codes, given names. A program called an assembler turns the names back into numbers. It sounds trivial. It was not. It was the first time anyone let the machine help write its own programs. And the idea that the machine could do clerical work on its own instructions is the seed of everything in this part. And at Cambridge, on EDSAC, David Wheeler had already taken the next step, the subroutine. Write a piece of program once for something common, like computing a square root, and store it in the library. Any program can then call it, use it, and come back. Write once, use forever. Wheeler also wrote the initial orders, the little resident program whose only job was to load other programs. You can hear the shape of the future in it. Software that manages software. Now that the person who turned that seed into a revolution worked for the Navy, and her story has a moth in it, so we should get the moth right. Grace Murray Hopper was a mathematics professor at Vassar, with a doctorate from Yale when the war came. And she joined the Navy Reserve, and in 1944 found herself working on the Harvard Mark I under Howard Aiken, one of the first programmers of one of the first computers. 3 years later, in September of 1947, the team working on the Mark II found the machine misbehaving and traced the fault to a relay, and inside the relay found a moth. They taped the moth into the logbook and wrote beside it, "First actual case of bug being found." The page is in the Smithsonian now. Hopper told that story with delight for the rest of her life, which is why her name is attached to it, though she was always honest that she did not find the moth herself. The word bug was already old engineering slang. Edison used it. The logbook's little joke is precisely that the metaphor had shown up in person. But the story stuck, because it was Hopper telling it. And Hopper had a gift for making the world listen, because her real fight was bigger than a moth. After the war, she joined Eckert and Moschly's company, working on UNIVAC, and there, in 1951 and 1952, she built something called the A-O system, the first compiler. The idea, in plain terms, is this. You write what you want in a notation a human can work with, and a program, running on the machine, translates your notation into the machine's own codes. The computer writes the machine code, software producing software, and the world's response will sound familiar. She said it herself. I had a running compiler, and nobody would touch it because, they carefully told me, computers could only do arithmetic. They could not do programs. It took 2 years of selling before people would try it. The establishment's instinct was that programming was priestcraft, and a machine could no more write a program than a loom could design a fabric. Hopper had the running system. They had the theory about why it was impossible. She was right, anyway. Then she pushed further, into the heresy that defined her. Business customers, she noticed, would not learn mathematical symbols. She had been a math professor, and she said the lesson of teaching was that it was never a question of whether people could learn the symbols. It was whether they would. Throw those symbols out, the data processing people told her. I do not know what they mean. So she proposed, in 1953, that data processing be written in English words. Management called it unfeasible. Her philosophy, as she described it, was to go ahead and do it and apologize later. The result was Flow-matic, running by 1957, the first compiler that worked from English, like statements. In 1959, the Defense Department convened a committee, Codicil, to design a common business language, and Flow-matic's fingerprints were all over what emerged. COBOL. It was designed by committee, and it shows, and one frustrated committee member famously mailed the chairman a tombstone engraved with the language's name. And yet, COBOL worked, and COBOL spread, and COBOL never left. By the 1970s, it was the most used language on Earth. Today, decades after its obituary was first written, something like 220 billion lines of it are still running. And almost every time you use a cash machine, COBOL is involved. Hopper spent the rest of her career promoting it, validating compilers, and serving the Navy, which kept calling her back from retirement until 1986, when she left as the oldest serving officer in the service, a rear admiral at 79. A ship in port is safe, she liked to say, but that is not what ships are built for. While Hopper fought for English, a different fight was happening at IBM over speed. John Backus was a young IBM programmer who had spent years handwriting machine code, including a program to compute the positions of the moon. And he knew exactly how painful programming was. In 1954, he assembled a team to build what became Fortran, the formula translator. The language itself was finished quickly. The hard part was the compiler, because everyone in the field believed the same thing. Machine-generated code would be slow, bloated, half the speed of handwritten code, and at a time when machines cost millions and ran glacially, half speed meant useless. So Backus's team spent the effort where it mattered: the optimizing compiler. 3 years of work, 18 person years, and when Fortran shipped in April of 1957 for the IBM 704, its compiled code ran nearly as fast as code written by hand by experts. That is the moment everything changed, because now the choice was no longer between fast and human. A scientist who had never seen a wiring diagram could write something close to mathematics and get an answer at nearly full machine speed. Programming stopped being priestcraft and started being a skill anyone technical could learn. Missile trajectories, weather models, economic forecasts, all written in Fortran. 68 years later, supercomputers still run benchmarks in it. And then the languages bloomed. This is the part of the story where everything happens at once, in the late 50s, so we will take the three great branches one at a time. COBOL, you have met. The committee language for business, English-like, machine-independent, built so a manager could read a program and roughly follow it. Despised by purists from the day it shipped, outliving them all. Lisp came from a very different mind. John McCarthy, the man who named artificial intelligence, built it in 1958 out of pure theory. Its ideas came from recursive functions and from Church's lambda calculus, the same lambda calculus from Part 4. Lisp treats code and data as the same kind of thing, lists of symbols, and a Lispy program can build and run another Lispy program as easily as it adds two numbers. It became the native language of artificial intelligence research for half a century, and its ideas keep reappearing in languages designed by people who never wrote a line of it. It is the second oldest language still in real use, and it still looks like it arrived from the future. And then there was ALGOL, the algorithmic language, designed by an international committee in 1958 and revised in 1960. ALGOL's gift was rigor. Its report defined the language with a formal grammar, Bacchus-Naur form. The first time any language had been specified with mathematical precision. It gave the world block structure, the idea that code nests inside code in clean, scoped blocks. Hardly anyone wrote production software in ALGOL, and nearly every language you have ever heard of descends from it. Alan Perlis, who was there, said it best. ALGOL, he wrote, was a great improvement on its successors. The next chapter is about who gets to compute at all. Dartmouth College, 1964. Two professors, John Kemeny and Thomas Kurtz, had a conviction that was radical for the time. Every student, they said, should be able to use a computer. The engineers, the philosophers, the poets, everyone, freely, openly. At 4 in the morning on the 1st of May, 1964, in the basement of College Hall, Kemeny and a student sat at two terminals side by side and typed "run" at the same moment. And both programs worked. Two things were born in that instant. The time-sharing system, many people using one computer at once, each with the illusion it is theirs alone, and a new language designed from scratch for beginners. 14 kinds of statement, line numbers, commands in plain words. They called it BASIC. Beginner's all-purpose symbolic instruction code. They gave it away. And for 20 years, learning to program meant learning BASIC. When the Altair arrived in 1975, the software that made it useful was Altair BASIC, written by Gates and Allen. The personal computer revolution was largely conducted in a language designed for undergraduates at 4 in the morning. Meanwhile, in a lab at Bell Labs, the systems language to end them all was being born almost by accident. The story runs through a failed grand project called Multics, which Bell Labs withdrew from in 1969, leaving some very talented people with good ideas and no machine. Ken Thompson found a little used PDP-7 and began writing what became Unix, an operating system built on small tools and plain files with Dennis Ritchie and others. And the languages came along for the ride. Thompson took an austere systems language called BCPL by Martin Richards and boiled it down into something called B. And Ritchie, between 1971 and 1973, took B and put the types back in, added structure, wrote the first real compiler for it, and called it C. And then came the move that made C immortal. In 1973, they rewrote Unix itself in C, an operating system written in a high-level language, able to move from one machine to another. Until that moment, operating systems were written in the assembler of one specific machine and died with it. C and Unix traveled together into universities, into industry, into everything. In 1978, Kernighan and Ritchie published their book, and a generation learned to program from 180 pages that begin with the words, "Hello, world." Every systems language since, C++, Java's syntax, JavaScript's syntax, Go, Rust, is written in C's accent. And as the languages multiplied, so did the ideas about how to think in them. In 1968, Edsger Dijkstra wrote a letter to the communications of the ACM with a title that became a slogan, "Go-to statement considered harmful." The go-to, the command that jumps anywhere in a program, produced what everyone called spaghetti code, programs whose flow tangled until no human could follow them. Dijkstra's answer was structured programming. Loops, blocks, subroutines, each with one way in and one way out. Nicholas Wirth built Pascal in 1970 to teach exactly that discipline. And for a generation, Pascal is how you learned to write clean programs. And in Norway, 2 researchers named Ole Johan Dahl and Kristen Nygaard, trying to simulate real-world systems like ships and warehouses, created Simula 67, and in it, almost in passing, invented the object. An object bundles data and the operations on it into one thing, a little self-contained machine, and objects belong to classes, and classes inherit from other classes. Simulation kept turning into philosophy. At Xerox PARC in the 1970s, Alan Kay's team took the idea further than anyone in Smalltalk, where everything is an object, and objects talk to each other by sending messages wrapped in the first truly graphical environment. Kay was chasing a dream he called the Dynabook, a computer for children, and his line from PARC's founding meeting has outlived every machine they built. "The best way to predict the future," he said, "is to invent it." Stroustrup carried Simula's ideas into C and got C++. Cox and Love blended Smalltalk with C and got Objective-C. In 1995, Sun released Java, C's syntax tamed and made portable. And the same year, at Netscape, Brendan Eich famously built JavaScript in about 10 days. And it became the native language of the web browser, which means it now runs on more machines than any language in history. Guido van Rossum had released Python a few years earlier, in 1991, named after Monty Python, built on the conviction that code is read far more often than it is written, so it had better read well. Larry Wall's Perl the duct tape of the early internet. Matsumoto's Ruby, designed, in its creator's words, for programmer happiness. The tower kept rising. So let us stop and say plainly what a programming language is, because we have climbed the whole tower now. At the bottom, the machine reads numbers. Above that, assembly gives the numbers names. Above that, a high-level language lets you write something closer to thought. And a translator does the descent. A compiler takes the whole program and translates it once, ahead of time, into a finished machine code artifact, fast every time it runs. That is Fortran's path and sees. An interpreter takes the program and performs it directly, line by line, every time, trading speed for immediacy and flexibility. That is BASIC's classic path and Python's. Either way, every program ends its life in the same place. The gates, the adders, the fetch and execute loop from part 6. Nothing you write ever escapes the hardware. The tower of languages is a tower of descriptions, all of which cash out at the bottom as electrons moving through silicon. And that is the real story of this part. Each layer of language hid the layer below. And each layer let a wider circle of people speak to the machine. The priesthood became a profession, and the profession became a common skill. When Kay McNulty and her 5 colleagues programmed ENIAC by rewiring it, they were the machine's operators. 20 years later, a student at Dartmouth could make a computer do something useful on their first day. Today, more people have written code than have ever flown in a glider. The language was the bridge. But a language is only a way of saying things. It says nothing about what to say. A recipe written in beautiful French is still a recipe, and some recipes are better than others, not tastier, faster, smaller. And it turns out the difference between a good recipe and a bad one can dwarf any difference in hardware. A clever method on a slow machine beats a clumsy method on a fast one, not by a little, but by more than the entire transistor revolution ever delivered. That is the mathematics of algorithms, and it has its own deep and surprising theory, with its own unsolved question worth $1 million. That is where we go next. A language lets you speak to the machine. It says nothing about what is worth saying. This part is about the what, the method, the recipe, and about the discovery, one of the deepest in all of computer science, that the recipe matters more than the machine it runs on, more than the transistors, more than Moore's law. A better recipe can outrun 50 years of hardware progress without breaking a sweat. The word is algorithm, and you remember where it comes from. Al-Khwarizmi, the house of wisdom, the Latin dixit algorithmi. Thus speaks algorithmi. But the idea is far older than the word, and the oldest great example is still in use, running inside your machine today, somewhere, probably this minute. Around the year 300 BC, in Alexandria, Euclid wrote the Elements, and in Book 7, he set down a procedure for finding the greatest common divisor of 2 numbers, the largest number that divides them both. Here is the whole method. Take the 2 numbers, subtract the smaller from the larger. Now work with the smaller number and the difference. Repeat. Keep going until the 2 numbers are equal, and what you are holding is the answer. Or, in the form computers prefer, divide and take the remainder, and the greatest common divisor of the pair is the greatest common divisor of the smaller number and the remainder over and over until the remainder is 0. 56 and 12. 56 is 4 12s and a remainder of 8. 12 is 1 8 and a remainder of 4. 8 is 2 4s and a remainder of 0. The answer is 4. It always ends. It always works. 23 centuries later, that same procedure sits inside the arithmetic of internet security, quietly reducing fractions and finding divisors every time a secure connection is made. It may be the oldest recipe in the world that has never once worn out. Notice what makes it an algorithm and not a suggestion. Every step is exact. No judgment calls, no taste, no insight required. It always finishes in a number of steps you can bound in advance, and when it finishes, the answer is right. Al-Khwarizmi wrote procedures for people. Euclid's was written for anyone or anything that can subtract. That is the whole idea of computation, and we are back at it again. The cleverness lives in the procedure, not the performer. Now let us go to the laboratory where this gets measured, because computer science has a favorite experimental animal, and it is sorting. Sorting sounds dull, putting things in order. But it is everywhere once you look. Your contacts, your photos by date, the index at the back of a book. Search results, bank statements. Every database on Earth sorts constantly. And sorting is perfectly suited for study, because the goal is obvious, the input can be any size, and the methods differ wildly in cost. Von Neumann understood this from the start. When he was thinking through how a stored program computer should be organized, he reached for sorting as the test case, because special-purpose sorting machines already existed, and they set a standard a general machine would have to match. So imagine the naive way. You have a row of 1,000 unsorted cards. You walk down the row, comparing neighbors, swapping any pair that is out of order. One pass is not enough. The biggest card bubbles to the end, but the rest are still a mess. So you walk the row again and again. 1,000 cards, 1,000 passes, 1,000 comparisons per pass. 1,000,000 little comparisons. Double the number of cards, and the work does not double. It quadruples. That is the signature of the naive way. The work grows like the square of the input, and squares are brutal. 1,000,000 cards would cost 1,000,000,000,000 steps. At 1,000,000 steps a second, that is 11 days. To sort a card file. In 1945, von Neumann wrote down a smarter way, one of the first algorithms designed for the new machines. Merge sort. The idea is the one that runs half of computer science: divide and conquer. Do not sort the whole pile. Split it in half. Sort each half, and here is the trick. You sort each half by splitting it again and again, until every pile is a single card, and a single card is already sorted. Then you merge. Take 2 sorted piles and zip them together into one sorted pile, always taking the smaller of the 2 top cards. Merging is fast because the piles are already in order. The splitting costs you a few rounds, only as many rounds as the number of times you can have the pile, and halving is the cheapest operation in the world. 1,000 cards is about 10 rounds. 1,000,000 cards is about 20. The 1,000,000,000,000 steps collapse into tens of millions. The 11 days become a breath. Real sorting, in practice, is usually a hybrid of these ideas. the sort built into Python, and into your phone is Tim Peters's Tim sort. Merge sort and insertion sort woven together, tuned to run fastest on the messy, partly ordered data of the real world. And in 1959, a young Englishman named Tony Hoare found something even faster in practice, in one of those settings that make the history of this field feel written rather than lived. Hoare was a visiting student at Moscow State University, working on machine translation for Britain's National Physical Laboratory. To translate, he needed to look up Russian words in a dictionary that lived on magnetic tape in alphabetical order, and that meant sorting the sentence's words first. His first method was too slow, so he invented a better one. Pick one card, any card, call it the pivot. Sweep through and divide the pile into everything smaller than the pivot and everything bigger. The pivot is now in its final, correct place. Then do the same thing to each half, and again. Each round parks one card permanently and shrinks the problem. He called it Quicksort, published it in 1961, and with care in how you choose the pivot, it remains, more than 60 years later, the standard way the world's computers put things in order. The lightning risk of its rare bad case is handled by shuffling the input first. Hoare said later that he had made two great contributions to computing. One was quicksort. The other, he said, was inventing the null reference, which he called his billion-dollar mistake. We will let that one sit for later. Now the companion problem, finding things. Suppose the cards are sorted. 1 million of them. Find one. The dull way is to start at the beginning and check every card. 1 million looks. But the cards are sorted, and sortedness is information, and information is speed. Open the pile in the middle. Is your card above or below the middle card? Whichever it is, you have just thrown away 500,000 cards without looking at any of them. Do it again. And again. Every look halves the haystack. How many times can you have 1 million? About 20. 20 looks instead of 1 million. This is binary search, and its speed up is the kind that makes hardware irrelevant, because no plausible machine makes 1 million looks beat 20. And here is the humbling part, the part that every programmer learns with some pain. Binary search is 60 lines of simplicity as an idea, and a swamp in practice. The first published binary search appeared in 1946. The first published version that handled every edge correctly appeared in 1962. 16 years for a lookup trick. John Bentley assigned it to a class of professional programmers in the 1980s and watched 90% of them fail to produce a correct version, given hours. And then the story got perfect. Bentley's own version, printed in his beloved book, Programming Pearls, contained a subtle overflow bug that went undetected for over 20 years, until 2006, when the same bug was discovered in the standard library of Java, which had been written by people who learned the algorithm from the book. If you ever feel bad about an off by one error, remember binary search. The simplest algorithm in this part defeated generations of careful professionals. Precision is hard. That is why we test. So how do we talk about these costs without getting lost in the details of this machine or that machine? We need a way to describe how the work grows as the input grows, and it comes from number theory, of all places. In 1894, a German mathematician named Paul Bachmann introduced a symbol, a capital O, to describe the growth of functions, and Edmund Landau spread it. It sat in pure mathematics for 3/4 of a century until Donald Knuth picked it up in the 1970s and made it the working vocabulary of computer science. Big O. When we say bubble sort is O of n squared, we are saying the work grows like the square of the input. And we do not care about the constants. Twice as fast, a machine just moves the constant. The square is the truth. Merge sort is O of n log n. Binary search is O of log n. And the logarithm is the hero of the whole story, because log n is the number of times you can have n. And having is what divide and conquer buys you. Feel the orders for a moment. At 1,000,000 items, O of n is 1,000,000 steps. O of n log n is about 20 million. O of n squared is 1,000,000,000,000, 1,000,000 times worse than the good ones. And the gap widens forever as the input grows. This is why the recipe beats the machine. The entire history of hardware, from the relay to the smartphone, delivered maybe 1,000,000,000,000-fold speedup. Choosing merge sort over bubble sort on a big enough pile delivers more than that by itself. Algorithms are the part of computer science where the mathematics does the heavy lifting. And no engineer with a soldering iron can argue with a logarithm. There is a companion craft to all of this, quieter than the algorithms, and just as decisive. Data structures. The ways of arranging information so the algorithms have something to work with. The array is the simplest. Items in a row, in consecutive cells of memory. Finding the 100th item is instant, because the machine can compute exactly where it lives. Constant time, the fastest answer there is. But insert something in the middle, and everything after it must shuffle down, one by one. The linked list makes the opposite trade. Each item holds its value, and the address of the next, a chain of signposts. Inserting is a snip and a knot. Finding the 100th item means walking the whole chain from the start. Then there is the structure that quietly runs the modern world. The hash table. Take the thing you are looking up, a name, an account number, grind it through a hash function, a little machine that turns it into a number, and use that number as the address. Lookup becomes nearly instant until two names grind to the same number, a collision, and the table needs a plan for that. And good tables have good plans. Trees organize by hierarchy. Each node points down to its children, smaller things to the left, bigger things to the right. And searching a balanced tree is binary search in disguise. Feed a naive tree sorted data, and it sags into a line, so self-balancing trees quietly rotate themselves back into shape as they grow. And finally, the most general structure of all. The graph. Nodes and edges. Roads between cities. Friendships between people. Links between pages. A surprising share of the world's hard problems are graph problems in costume. Shortest paths, connections, cycles. Every one of these structures is in your phone tonight, layered into everything it does, the way the architecture of a city hides inside its walls. The man who turned this craft into a science is Donald Knuth. In 1962, he set out to write a single book about how to analyze programs. And the book became a life's work. The Art of Computer Programming. Volume 1 appeared in 1968, and it did something new. It did more than present algorithms. It analyzed them. Exact step counts, exact growth rates, proofs. The analysis of algorithms became a discipline, with Knuth as its first great teacher, and the books became the field's scripture, so complete and so careful that American scientists later placed them on a list of the century's great science monographs alongside Einstein and Feynman. Knuth is still writing them. He is in his late 80s, and the series is still not finished, and nobody who knows it would trade it for finished. Now, we are ready for the cliff edge, where the fast recipes run out. In 1965, 2 papers quietly founded a field. Juris Hartmanis and Richard Stearns showed how to classify problems by the computation time they require, complexity classes, the beginning of complexity theory, and Alan Cobham, and independently Jack Edmonds, argued for a specific line in the sand: polynomial time, problems whose cost grows like some fixed power of the input, n squared, even n cubed, tame growth. Edmonds's paper was a marvel twice over, because it gave a polynomial time algorithm for a real problem, and then paused to argue that polynomial time is what efficient should mean. The Cobham-Edmonds thesis. On one side of the line, the tractable. On the other, the exponential, where the cost doubles with each extra item. And the universe simply does not have the atoms to run the algorithm on even moderate inputs. Because here is what exponential means. The traveling salesman problem is the famous one. A salesman must visit 100 cities and come home by the shortest route. Try every route. The number of routes is 99 factorial, a number with 156 digits. Every computer on Earth, running for the age of the universe, does not dent it. Moore's law is a doubling every 2 years. The factorial adds a multiplication by n. One is a wave. The other is the ocean rising. And now the question that defines the modern field, the one with $1 million on it. Some problems have fast solutions: sorting, searching, shortest paths. But a great many important problems have a stranger profile. Nobody knows a fast way to solve them. Yet if someone hands you an answer, you can check it quickly. Finding the root is brutally hard. Checking that a given route visits every city once and comes home is trivial. In 1971, Stephen Cook published a paper called The Complexity of Theorem Proving Procedures, and in it, he proved that one particular logical problem, satisfiability, is the hardest of all these checkable problems in a precise sense. A fast algorithm for it would give you a fast algorithm for every problem whose answers can be quickly checked. Leonid Levin proved the same thing independently in the Soviet Union. And in 1972, Richard Karp showed that this hardest status was not exotic. He took 21 famous problems, traveling salesmen among them, packing, scheduling, coloring maps, and proved every one of them equivalent in this sense. Solve one quickly, and you have solved them all quickly. NP complete, we call them. A hidden brotherhood of problems, thousands now known, all standing or falling together. So the $1 million question, literally, one of the Clay Institute's Millennium Prize problems, is the simplest question in this whole video. Is checking a solution really easier than finding one? If P equals NP, if every quickly checkable problem is also quickly solvable, then the world changes overnight. Optimization collapses into ease. Logistics, protein folding, chip design, all become fast. And every form of encryption we will discuss in a later part becomes breakable, instantly, because modern cryptography is a house built on the assumption that checking is easier than finding. Almost every expert believes P is not equal to NP, that hard problems are truly hard. But belief is not proof, and nobody has proved it in more than 50 years of trying. The greatest open question in computer science is a question a child can grasp. Are some things just hard to find, even when they are easy to check? And that leaves us at the edge of a deeper water. This whole part asked how fast. How fast can we sort? How fast can we search? What does a problem cost? But underneath speed, there is a more basic question, the one Turing's machine left us with. What can be computed at all? And what does it even mean to compute? Between the simple adding machine and the universal computer, there turns out to be an entire zoo of lesser machines and lesser languages, each with its own limits, each with its own place, mapped out mostly in the 1950s by a handful of linguists and logicians, including one linguist whose name you might know from politics rather than science. That zoo, and the strange creatures in it, is next. The last part asked how fast. This one asks something underneath speed. What is a machine at all? What does it mean to compute? And the surprise waiting for us is that between the simplest device that reacts to the world and Turing's universal machine, there is not a gap. There is a staircase, a whole zoo of machines, each one strictly stronger than the one below it, each matched to its own class of problems. And the zoo was mapped, mostly in the 1950s, by logicians, and unexpectedly, by a linguist. Start with the humblest machine you know, a turnstile. It has two states, locked and unlocked. A coin moves it from one to the other. It remembers nothing else. It cannot count the number of people who passed. It cannot remember your face. Its entire mind is which state it is in right now. That is a finite automaton, and it is the smallest creature in the zoo. A finite set of states. Rules that say, in this state, seeing this input, go to that state. No memory beyond the state itself. It is a Turing machine with the tape taken away. And the strange thing is how much of the world runs on exactly this. Vending machines, elevators, traffic lights, the controller in your washing machine, the part of every compiler that reads the raw text of your program and breaks it into words, the pattern matching engine inside every text search you have ever run. All finite automata, or their first cousins. The theory begins, oddly, with brains. In 1943, Warren McCulloch, a neurophysiologist, and Walter Pitts, a self-taught teenage logician who had run away from home, published a paper called A Logical Calculus of the Ideas Immanent in Nervous Activity. It was the first mathematical model of a neuron, a cell that sums its inputs and fires past a threshold. And they showed that a net of such neurons computes logic. It is the founding paper of neural networks, and we will meet it again in the part on artificial intelligence. But its first consequence was here. Stephen Kleene, a student of Church, took up the McCulloch-Pitts nets and asked the scientists question. Exactly what can such nets do? In a Rand memorandum in 1951, published in 1956 in a volume called Automata Studies, edited by Shannon and McCarthy, Kleene proved a beautiful equivalence. The patterns these finite machines can recognize are exactly the patterns describable by a notation he called regular events, which became the regular expressions that programmers type every day. The machine and the notation are the same thing in two costumes. That is Kleene's theorem, and it is the first time the field saw the shape of a deep truth. A language and the machine that accepts it are one object seen from two sides. And Kleene's machine has a sharp, provable edge, and the edge is easy to feel. A finite automaton cannot count. Not in the deep sense. It can tell apart 1 from 2 from 3, if you give it enough states, but it cannot tell apart n from n, for arbitrary n. Hand it a string of 1,000 opening parentheses, followed by 1,000 closing ones, all correctly nested, and ask it to check the balance, and it fails, guaranteed, because 1,000 levels of nesting require remembering 1,000 things. And its memory is its states, and its states are finite. There is a formal result behind this called the pumping lemma, and its spirit is simple. Any finite machine reading a long enough input must eventually revisit a state it has been in before, and from then on it is doomed to repeat itself. Finite machines loop. They cannot climb to arbitrary depth and climb back. So add one thing, a stack. A stack is the simplest useful memory, a pile of plates. You can put a plate on top and take one off the top, and that is all. Give a finite automaton a stack, and it climbs a level of the staircase. It becomes a push-down automaton. And now, watch what it can do. Reading an opening parenthesis, push a plate. Reading a closing one, pop a plate. If the pile is empty exactly when the input ends, the parentheses balanced. The 1,000 levels of nesting are no problem now, because the stack grows as deep as needed. Nesting, the exact thing that defeated the finite machine, is what the stack was born for. And this level of the zoo is not a curiosity. It is the skeleton of every compiler and every programming language on Earth. Remember Algol's gift from Part 8, the Bacchus-Naur form, the first mathematically precise description of a language's syntax. That notation describes what are called context-free grammars, rules that say a program is a statement list, and a statement is an assignment or a loop, and a loop is the word while followed by a condition, and so on, unfolding like an outline. And the theorem of this level says that the languages described by context-free grammars are exactly the languages recognized by push-down automata. The grammar and the stack machine, again, one object, two costumes. When your compiler reads your code, its front end is this staircase in miniature. A finite automaton breaks the text into tokens. A push-down automaton checks the nesting against the grammar. Two levels of the zoo, working in sequence, every time you build anything. Now, the man who drew the whole map. In 1956, a young linguist at MIT published a paper called 3 Models for the Description of Language, and refined it in 1959, and his goal was linguistic. He wanted to know what kind of machinery a grammar needs to capture a human language. His name was Noam Chomsky, To most of the world, he is known for entirely different things, for politics and dissent. But before all of that, he founded modern linguistics, and the instrument he built for it became a permanent fixture of computer science, the Chomsky hierarchy. Here is the map, and it is worth going slowly, because it is one of the most elegant results in all of science. Chomsky classified grammars by how much freedom their rules have, and the classification turned out to be, exactly, a classification of machines. At the bottom, type 3, the regular grammars, the simplest rules. They generate what Clean's machines recognize. Regular expressions, finite automata, turnstiles, text search, one level. Above it, type 2, the context-free grammars, rules that rewrite a single symbol regardless of what surrounds it. These are the grammars of balanced nesting, of programming languages, of arithmetic expressions. And their machine is the push-down automaton, the finite machine with a stack, a strictly greater power. Above that, type 1, the context-sensitive grammars, where a rule can look at a symbol's neighbors before rewriting it. Their machine is a Turing machine with a bounded tape, a linear, bounded automaton. More power still. And at the top, type 0, the unrestricted grammars, any rule at all. And the machine at that level is the full Turing machine, everything computable. The universal machine is the top of the staircase, and there is nothing above it. We know there is nothing above it because of part 4. Church, Turing, Clean, Post, and everyone since have found the same ceiling from every direction. 4 levels, each one properly stronger than the last, each grammar matched to its machine. A linguist, asking how human sentences work, ended up drawing the periodic table of computation. And the answer to his original question, by the way, turned out to be that human language sits awkwardly somewhere around the middle levels, not quite context-free, which is part of why machines took so long to speak passably, and why the ones that finally did came from the other branch of this family tree. The neural networks of McCulloch and Pitts, rather than from grammars. Hold that thought for the AI part. Now, the wall again, but bigger. In part 4, we watched Turing prove one specific impossibility. No machine can decide, in general, whether a program halts. In 1951, in his doctoral work, Henry Gordon Rice proved that this was never one wall. It is the whole terrain. Rice's theorem. Take any question about a program's behavior, not its text, its behavior. Does it ever print the number 42? Does it halt on all inputs? Does it compute the same function as this other program? Any such question, any question about what a program does that's true of some programs and false of others, is undecidable, not hard, provably unanswerable by any algorithm forever. Sit with what that means for a moment, because it rules a huge part of daily life in software. There can never be a perfect bug detector. There can never be a tool that reads an arbitrary program and tells you reliably whether it is correct, or whether it is safe, or whether it contains a virus. Every virus scanner, every linter, every static analysis tool ever sold is of necessity an approximation. It must sometimes say safe when it means probably, and sometimes cry wolf over innocent code. Rice's theorem is the reason. The vendors do not mention it. The theorem does not care. And then there is the creature that puts a face on the uncomputable. In 1962, Tibor Rado at Ohio State published a paper in the Bell System Technical Journal called On Non-Computable Functions, and in it he defined a little game. Take all the Turing machines with n states, tiny machines, 2 states, 3 states, 5. Run each one on a blank tape. Some run forever, some halt. Among the ones that halt, one of them writes the most ones before stopping. Call that number the busy beaver of n. It is a perfectly definite number. For every n, it exists. And Rado proved that no algorithm can compute it, because the function grows faster than any function any computer can ever compute, faster than factorial, faster than towers of exponents, faster than anything you can program by proof. The first few values are known. The 2-state busy beaver writes 4 ones. The 4-state writes 13. The 5th value was only settled in 2024 by a loose internet collaboration of amateurs and researchers after 40 years of effort. 47,176,870 steps. That number is now certain. The 6th value is, as far as anyone knows, beyond the reach of humanity, sitting out past the edge of proof, calm, and enormous, and uncomputable. There are specific, nameable integers that no machine will ever print. The busy beaver is where the wall from part 4 gets a street address. We end this part with the strangest fact of all. The one that changes how the whole video feels in hindsight. Computation does not stay inside computers. Start with dominoes. In 1946, Emil Post, another of the great logicians of that era, posed a puzzle. You are given a set of domino tiles, each with a string of letters on top and a string on the bottom. Can you line up a sequence of tiles, reusing them freely, so the string read across the tops equals the string read across the bottoms? It sounds like a coffee table game. It is undecidable. No algorithm can answer it in general, because the tiles can be made to simulate the steps of a Turing machine. So answering the domino question would answer the halting question. A children's tile game contains all of computation, hidden in it. Then tiles in the plane. Hao Wang, in 1961, asked whether a set of square tiles, colored on their edges, matched edge to edge like a mosaic, can always be detected as tileable or not. He conjectured that any tileable set would tile periodically, like wallpaper, and if so, a machine could check. His student, Robert Berger, proved him wrong in 1966. The tiling question is undecidable, and its undecidability means something you can hold in your hand. There must exist sets of tiles that cover the infinite plane perfectly and never repeat. Aperiodic tilings. They were found and simplified, and years later, Roger Penrose made them beautiful. And years after that, they turned up in the atomic structure of certain alloys in physics, where they are called quasi-crystals. Undecidability, crystallized in actual crystal. And then the most famous accident in all of mathematics. In 1970, John Horton Conway invented a toy. A grid of cells, each alive or dead, with 3 tiny rules about birth and death and crowding. The game of life. Martin Gardner wrote it up in Scientific American in October of 1970, and readers across the world began computing patterns by hand. Conway had offered $50 to anyone who found a pattern that grew forever. And within weeks, Bill Gosper had found the glider gun, a little machine that fires gliders across the grid endlessly. From gliders, people built logic gates, and, or not, in colliding streams of cells. And in 1982, Conway published the proof. The game of life is Turing complete. Those 3 rules contain a universal computer. People have since built actual working Turing machines in life, and someone has built a simulation of Tetris inside it, a game running on a game that was never meant to run anything. And it keeps happening in the places least expected. The redstone circuitry of Minecraft is Turing complete, and players have built working computers inside the game at walking scale. Microsoft Excel is Turing complete. PowerPoint is Turing complete through its animation system. And someone has demonstrated a Turing machine made of slides. The card game Magic: The Gathering is Turing complete. A single line of cellular automaton called Rule 110, 1 row of black and white cells with the simplest imaginable update rule, is Turing complete, proven by Matthew Cook, working alongside Stephen Wolfram, who built an entire research program on the claim that simple rules like these might underlie the universe itself. The lesson is not that these are party tricks. The lesson is that computation is not a technology. It is a substance. It condenses out of almost any system that follows simple rules, the way crystals form in a cooling melt. Turing asked what a machine could do. The universe keeps answering. Everything, everywhere, given time and room. So, we have the machine, the language, the algorithm, and now the map of all possible machines, and the knowledge of where the walls are. It is time to come back down from the theory and into the machine room, because by the early 1960s, theory was not the pressing problem. The pressing problem was that the computers had become precious, room-sized, million-dollar creatures. And far too many people needed them at once. One machine, hundreds of would-be users, programs queuing in trays of punched cards. Someone had to build a program whose job was to share the machine, to guard it, to run the other programs, a program to rule the programs. That program is called the operating system, and its birth and the fights around it are next. Everything so far in this story has been about one machine doing one thing at a time for one person at a time. By the mid-1950s, that arrangement had become an absurdity, and the absurdity had a price tag. A mainframe cost millions of dollars. It sat in an air-conditioned room, tended by a priesthood of operators, and a shocking share of its day was spent doing nothing at all, while a human being walked a deck of punched cards across the room, loaded the machine, watched it finish, unloaded the results, and walked back for the next job. The fastest calculating engine in the world, idle, waiting on footsteps. And notice the inversion that has happened. In the ENIAC days, the human's time was cheap, and the machine's wiring was precious, so 6 women spent days setting up a problem. 10 years later, the arithmetic had flipped. The machine's time was now the expensive thing, and the human's time did not matter to the accounting department. All the pressure ran one way: keep the machine fed. Never let it wait. The first answer was called batch processing, and the first real system to do it arrived in 1956 from a direction you would not expect. Not from IBM, from two of its customers. General Motors Research and North American Aviation had both ordered the same machine, the IBM 704, and their people, Bob Patrick and George Rickman at GM, Owen Mock's team at North American, had compared notes through the new users group, Share, and built what became known as the GMNAA input-output system, the first operating system. Its idea was simple enough to say in one sentence: let the machine load itself, stack the jobs. The system reads in a program, runs it, and when the program ends, the system is still there, resident in memory, and it immediately reads in the next one. No footsteps, no idle gaps, and it carried the shared input and output routines that every program needed, so no one had to rewrite the code that talks to the tape drives. It worked so well that versions of it ran in about 40 installations, and IBM's own follow-on systems descend from it. The operating system was invented by customers to stop wasting $1 million worth of idle time. But batch processing has a cruelty baked into it, and everyone who lived through it remembers the cruelty. You do not run your program. You submit it. You hand your deck of cards to the operator, and you go away. And hours later, or the next morning, you come back for the printout, and the printout says your run died on the fourth card because of a misplaced comma. You fix the comma. You resubmit. Tomorrow, another printout, another comma. A week of this, for a program that a modern laptop would reject in a second, with the error underlined. The machine was fed, and the humans were starving. Programming in the batch era was a correspondence conducted through a mail slot. The answer to that is one of the great ideas in this entire story, and it arrived at MIT at the turn of the 60s, in the mind of a soft-spoken physicist turned computing manager named Fernando Corbato. The idea is called time sharing. The machine is thousands of times faster than any human at a teletype. So let 30 humans connect at once, each at their own terminal, and let the machine serve each of them a thin slice of every second, round and round, so fast that each user feels the whole machine is theirs. 30 people, one computer, and each one alone with it. Corbato's system, the compatible time-sharing system, was designed in 1961, demonstrated that November, and by 1963, it was MIT's everyday computing service, running on a specially modified IBM 7094, with users dialing in on telephone lines from offices and labs across the campus. And here is what happened when computing became interactive for the first time. Everything social appeared at once, unplanned, like weeds after rain. Users wanted to leave each other messages, and CTSS grew mail. They wanted to write documents together, and it grew text editors and formatting programs. They wanted to save a sequence of commands and replay it, and it grew scripting. And because many people now shared one machine's files, it needed a way to keep private things private. And so CTSS gave the world something you used 5 minutes ago without thinking: the computer password. The first password in computing history protected CTSS accounts in 1961, and the first password theft in computing history followed almost immediately. In 1962, a graduate student named Alan Scher, needing more than his fair share of machine time, simply tricked the system into printing the master password file and used everyone's accounts until he was caught and was punished, if the stories are to be believed, mostly by being made to promise not to do it again. Security began the way it has continued ever since. Someone built the lock, and someone else immediately picked it. Corbato, who received the Turing Award for all of this, had a bigger dream behind the time-sharing trick. If a machine can be shared by 30 people in one building, why not a city? Why should computing not be a utility, like electricity or water, something you draw from a wall socket without owning a generator? That dream became Multics, the Multiplexed Information and Computing Service, launched in 1964 as a joint project of MIT, General Electric, and Bell Labs, presented to the world in 6 ambitious papers at the 1965 Fall Joint Computer Conference. Multics aimed to be everything, a shared, secure, always-on computing service for an entire community with a radical architecture to match. A single unified memory where files and memory were one thing. Rings of protection, concentric circles of privilege, so that untrusted code physically could not touch the kernel. Dynamic linking, so programs could share libraries at runtime. Half the vocabulary of modern operating systems was coined inside this one project, and it nearly collapsed under its own ambition. Multics was years late, expensive, and complex beyond anyone's full understanding. In 1969, Bell Labs pulled out, judging that the project would not produce a usable system in any reasonable time. The dream did survive. Multics became a Honeywell product in 1973 and served real customers for decades. And the very last Multic system was shut down in October of the year 2000, an ending few noticed. But the project's deepest legacy was the reaction it provoked. Because inside Bell Labs, the people coming off Multics were left with good ideas, no machine, and a profound allergy to complexity. One of them was Ken Thompson. Thompson had written a game, Space Travel, a little simulation of flying a craft around the solar system, first on the Multics GE635, where a single game cost about $50 of internal computing money. When Bell Labs left Multics, he found a little used PDP-7 minicomputer sitting in a corner, a machine with a nice vector display and hardly any users, and he ported the game to it. And then, in the summer of 1969, with his wife away visiting family, as the often told story goes, he did something far larger. He wrote a file system, a kernel, the beginnings of an operating system, on that little machine. Dennis Ritchie joined almost immediately. Others gathered: Doug McElroy, Joe Osana, Rudd Canaday. It was Multics reimagined by people determined to keep only what was worth keeping, on a machine 100th the size. Someone, Brian Kernighan gets the credit, punned on the name. Unix, one of something, where Multics had been many of everything. It became Unix. Unix's genius was subtraction, a few ideas held firmly. Everything is a file. The disk, the terminal, the tape drive, the network, all spoken to in the same simple way, as streams of bytes. Programs are small tools that do one thing well, and they connect. And the connection mechanism is the one Doug McElroy had been advocating since 1964, the pipe. Take the output of one program and feed it directly as input to another. Ritchie remembered McElroy explaining it on a blackboard one afternoon, intriguing everyone, igniting nothing, until Thomson added it to the shell in 1973 with a single vertical bar of punctuation. And overnight, anyone could build a conveyor belt of programs out of one line of text. Search this, sort that, count those, chained. The command line became a language for building with working parts. McElroy later compressed the whole philosophy into 3 sentences. Write programs that do one thing and do it well. Write programs to work together. Write programs to handle text streams, because that is a universal interface. And then came the decision that made Unix immortal. And we have already covered it in Part 8, because it is the same story. In 1973, the team rewrote the Unix kernel in Ritchie's new language, C, an operating system in a high-level language. Now, Unix was portable. It could move to new machines with a recompile instead of a rewrite. The 1974 paper in the Communications of the ACM made it famous. Version 6, in 1975, leaked out of Bell Labs into universities. And because AT&T was legally restrained from selling software as a business, the source code circulated cheaply, and a generation of students learned operating systems by reading it. At Berkeley, it grew a second branch, BSD, which added virtual memory and the networking code the young internet would run on. The descendants of those 2 branches now sit underneath nearly everything. The Mac's lineage is BSD. Your phone's is too, whichever phone it is. The next thread drops down in scale. The mini-computer shrank, computing to the size of a department. The microprocessor shrank it to a desktop, and the desktop needed its own operating system. It got one in 1974 from a quiet professor at the Naval Postgraduate School in Pacific Grove, California, named Gary Kildall. Kildall consulted for Intel, had written them a language called PLM, and had acquired one of the first floppy disk drives with a controller hand built by his friend John Torode. The disk needed software to be useful, so Kildall wrote it. CPM, the control program for microcomputers. He offered it to Intel for $20,000, and Intel passed, a decision that deserves a small place in any museum of missed chances. So Kildall sold it himself, through a company he founded with his wife, Dorothy, Digital Research. And he made one architectural decision that mattered more than the code. All the parts of CPM that depended on a particular machine's hardware were separated into one small layer. The BIOS, the basic input-output system. To move CPM to a new computer, you rewrote that one layer. The rest never changed. CPM became the first operating system that could live on anyone's hardware, and by 1980, it was the standard of the entire microcomputer world. Hundreds of different machines, one operating system, a market of software that ran on all of them. The personal computer industry grew up on Kildall's idea. And then came the deal that rewired the industry. And it is worth telling precisely, because it is misunderstood more often than it is told. In 1980, IBM, the largest computer company on Earth, decided to build a personal computer, secretly, on a deadline. It needed an operating system. The famous accounts all agree on the outline. IBM's people talked with digital research, and the talks failed over paperwork, over terms, over the most studied missed meeting in business history. So IBM turned to the small company supplying its basic, Microsoft. Microsoft had no operating system. What it had was knowledge of one. Down the road, Seattle Computer Products had been waiting on a delayed version of CP/M for its new hardware, and a programmer there, Tim Patterson, had gotten tired of waiting and written his own, a work-alike he called the quick and dirty operating system. Microsoft licensed it in December 1980 for $25,000, hired Patterson, and in July of 1981 bought the whole thing outright for $50,000. Weeks later, in August 1981, the IBM PC shipped, running what IBM called PC-DOS. And here is the clause that mattered. Microsoft kept the right to license the same system to anyone else under its own name, MS-DOS. Within a year, 70 companies had licenses. IBM had imagined it was buying a component. It had actually franchised away the layer that everything else would have to be compatible with. The richest real estate in the computer industry turned out to be the layer of software between the hardware and the programs, and Microsoft owned the toll booth. Kildall's architecture had won, after all. It was someone else's company. The graphical branch of this river, the Macintosh in 1984, and the long rise of Windows belongs to a later part of this video, because it is really the story of the interface, of how the machine presents itself to human beings. Hold it. Because the last OS story is the most unlikely, and it belongs entirely to the outsiders. By the late 1980s, Unix had become expensive again, locked-in licenses, and the free software movement, started by Richard Stallman in 1983, had spent years painstakingly rebuilding a free Unix piece by piece. The GNU project had everything: editors, compilers, shells, a whole userland, except the one piece in the middle, a working kernel. In 1991, a 21-year-old student at the University of Helsinki named Linus Torvalds had been reading Andrew Tannenbaum's Minix, a little teaching Unix, and hacking on his own 386 PC. And on the 25th of August, 1991, he posted a note to the Minix newsgroup. You can still read it. Hello, everybody out there using Minix. I'm doing a free operating system. Just a hobby. Won't be big and professional like GNU for 386 AT clones. He had ported a couple of tools. Things seemed to work. He asked what people liked and disliked about Minix. Just a hobby. It is the most charmingly wrong sentence in the history of computing. That hobby became the Linux kernel. The first releases went out to friends that September. The license became the GNUGPL in 1992, and the volunteers arrived from everywhere, and they never stopped arriving. Today, Linux runs every one of the 500 fastest supercomputers on Earth. It runs the overwhelming majority of the Internet servers, and every Android phone, billions of them, and the routers, and the televisions, and the cars, and the International Space Station, and a helicopter on Mars. The hobby that would not be big. Two of its jobs deserve a slower look, because they are inventions in their own right. The first is scheduling. 100 programs want the processor at once, and someone must decide who goes next. The naive way is first come, first served, and its failure is obvious the moment a long job parks in front of a short one. So the machine learned round robin. Every process gets a quantum, a thin slice of a second, and when the slice expires, the next process steps up. Nobody starves. Everybody waits a little. The second is virtual memory. Each program lives in a private fantasy of memory, and a dedicated piece of hardware, consulting the operating system's page tables, translates every address in the fantasy into a real location in the silicon. When memory runs short, whole pages are swapped out to storage and fetched back on demand, and the program never notices the trick. Fairness and illusion, running billions of times a day. So let us gather up what an operating system actually is, because we have now watched the whole species evolve. It is a referee. It keeps hundreds of programs from trampling each other's memory, and it decides thousands of times a second which of them gets the processor next, and it stands between you and anyone else using the same machine, enforcing the boundaries that Multics first engineered in rings. It is a librarian. It takes the raw chaos of a disk, a spinning surface with no opinions, and gives you the hierarchy you now think of as natural. Files, folders, paths. None of that exists in the hardware. The operating system invents the filing system and maintains it every second for your whole life. It is an illusionist. Every program you run believes it owns the whole machine, the whole memory, the whole processor. And the belief is a lie the OS maintains by sleight of hand, mapping each program's private fantasy of memory onto the real silicon through virtual memory, paging pieces in and out of storage so smoothly that no program ever notices the trick. And it is a translator, a printer, a disk, a network card, a camera. Each speaks its own electrical dialect, and the operating system's drivers absorb them all, so that your program never has to know what hardware it happens to be running on tonight. All of that, the referee, the librarian, the illusionist, the translator, is one program. The first one loaded when the machine wakes, the one still resident when everything else has run. The program that runs the programs. When people say a computer is just hardware without its software, this is the software they mean most. There is one more direction left for the machine to grow, and it is the direction that turns every one of these isolated rooms into a single planet-sized machine. Every computer in this part sat in one place, serving the people who could physically reach it, or at best dial into it down a phone line, one call at a time. The next revolution asks what happens when the machines talk to each other. Directly, continuously, across oceans. The story of the network, the internet, and the single letter sent crashing through the wire in 1969 is next. Late in the evening of the 29th of October, 1969, in a basement room at UCLA, a graduate student named Charlie Klein sat down at a terminal and tried to log into a computer 350 miles away at the Stanford Research Institute. It was to be the first message ever sent between two machines on a new experimental network. Klein typed an L. He typed an O. And the remote computer crashed. 2 letters. That was the entire first message on the network that would become the internet. L-O, low. As in, lo and behold, Leonard Kleinrock likes to say, looking back. They fixed the crash, and about an hour later, the full login went through. And no one in that basement thought they had witnessed anything historic. But the Internet's first word was a stutter, and there is something fitting about that, because the Internet was not built in a moment. It was assembled over a decade from 3 separate inventions made by 3 men on 2 continents, each answering a different question. And we should meet them one at a time, because the story only makes sense when you see that the network was never one person's idea. To understand the first invention, you have to understand what it was rebelling against. The world's great communication system in 1960 was the telephone network, and it worked on a beautiful, simple, ruinously wasteful principle. When you make a call, the network finds you a path and gives it to you entirely for the whole call. A dedicated circuit, end to end, yours alone, silent or talking. For voices, this was fine. A conversation uses the wire most of the time. But a computer does not talk like a person. A computer speaks in bursts. It says nothing for 3 seconds, and then fires 100,000 bits, and then says nothing again. Give a computer a dedicated telephone circuit, and you have rented a private highway for a vehicle that passes once an hour. The line sits empty, nearly all of its paid life. Connecting computers with telephone thinking would be like building the railroad, and then insisting every train travel with its own private track. The first man to see past telephone thinking was an engineer at the Rand Corporation named Paul Baran. And his question was a dark one, because 1960 was a dark time. The Air Force wanted to know how the country's communications could survive a nuclear first strike. Telephone switching was centralized. Destroy a few switching hubs, and the national network collapsed. Baran's answer, worked out over 4 years and published in the summer of 1964 in 11 thick volumes called On Distributed Communications, was to throw away the center entirely. Build a network like a net, he said, where every node connects to several others, and no node matters more than any other. And then, the deeper move. Do not send messages whole. Chop every message into small blocks of bits. Stamp each block with its destination. And let the blocks find their own way through the net, node to node, this one left, that one right, whichever path is alive at that instant. At the far end, reassemble them. If a node is destroyed, the blocks simply flow around it, like water around a stone. Destruction of the system, Baran wrote, would require the enemy to pay the price of destroying every one of its stations. It was, in essence, the Internet, described in full in 1964. And it went nowhere. Baran briefed the telephone establishment, and the telephone establishment, in the famous accounts of these meetings, could not hear him. The idea that you would chop a conversation into pieces and fling the pieces down different paths violated everything a century of telephony knew to be true. The Air Force hesitated, and the 11 volumes went onto the shelf. Now cross the Atlantic, because the second inventor did not know Baran existed. Donald Davies was a veteran of Britain's National Physical Laboratory. He had worked on Alan Turing's ACE computer back in 1947. And in 1965, at a computing congress in New York, Davies heard everyone talking about time sharing, about the new dream of many users on one machine, and he saw immediately what it implied. If 30 people want to share one computer across a city, they will soon want to reach many computers across a country, and the telephone network is the wrong tool for it. He went home, and over his kitchen table, he later recalled, he sketched the same answer Baran had found. Chop the data into small blocks. Stamp them. Let them flow through the network independently and reassemble at the end. Davies gave the blocks the name we still use. He called them packets. And unlike Baran, Davies got to build. His little packet network at the NPL was running locally by 1969. And he went further, proposing a national data network for all of Britain, a public utility for data, a decade ahead of its time. The British government declined. Britain's network was never built. But Davies's word, packet, and his clarity crossed back over the ocean and landed in the one place that was ready for it. Because meanwhile, at MIT, the third man had been quietly supplying the mathematics. Leonard Kleinrock's doctoral work, proposed in 1961 and finished in 1964, applied queuing theory, the mathematics of waiting in lines, to messages moving through communication nets. How long does a burst of data wait at a congested node? How do routing choices change delay? What topology serves a nation best? It was the theory the network would need before the network existed. And in 1963, Kleinrock took it to a young computer science department at UCLA. 3 inventions. Baran's survivable architecture, Davies's packet, Kleinrock's mathematics. What they needed was a patron. And the patron arrived in the form of a soft-spoken psychologist with a playful streak named J.C.R. Licklider. In October 1962, Licklider became the first director of the Computer Research Office at ARPA, the Pentagon's advanced research agency. And he carried a vision far bigger than survivable telephones. In April 1963, he sent his researchers a memorandum addressed, half-jokingly, to the members and affiliates of the Intergalactic Computer Network. The joke had a core of absolute seriousness. He imagined an electronic commons, open to all, in his words, the main and essential medium of informational interaction for governments, institutions, corporations, and individuals. He wrote that in 1963. He was describing your life. Licklider left ARPA before building anything, but he converted his successors, and by 1966, the office's new director, Bob Taylor, was living the problem personally. In Taylor's office sat 3 computer terminals, each connected by phone line to a different ARPA-funded computer in a different city, and none of them able to speak to each other. Taylor walked down the hall, described the absurdity to his bosses, and walked back, so the story goes, with $1 million. The engineer he hired to make it real was Larry Roberts. And it was in this circle that the last architectural idea appeared, from Wes Clark. Do not make every computer learn to speak the network. That would never converge. Instead, put one small standard machine at every site, a dedicated packet switching mini-computer, and let the big computers talk only to their own local one. The little machines would be the network. They were called Interface Message Processors, IMPs, the direct ancestors of every router on Earth. In July 1968, ARPA asked 140 companies to bid on building them. The winner was not a giant. It was a small Cambridge consulting firm, Bolt, Beranek, and Newman, BBN. And the team, led by a no-nonsense engineer named Frank Hart, built the IMP out of a ruggedized Honeywell mini-computer, hardened like a piece of military gear. And they delivered the first one on schedule to UCLA in September of 1969, to Kleinrock's lab, room 342. Bolter Hall. You can visit it today. The second IMP went to the Stanford Research Institute, then UC Santa Barbara, then the University of Utah, 4 nodes. And on that October night, with the first link live for only weeks, Klein attempted the login and got his 2 letters, and history stuttered into existence. The first permanent link came in November. By the 5th of December, all 4 nodes were connected. The ARPANET was real. And now comes one of the most instructive turns in this whole video, so let us slow down for it. What was the ARPANET for? The official answer was resource sharing. A researcher at UCLA could use a rare machine at Utah, as if sitting beside it. That was the pitch that funded it, and it was, in hindsight, almost entirely wrong about what humans would do with a network. Because the thing the researchers actually did, once they could reach each other's machines, was talk to each other. In 1971, a BBN engineer named Ray Tomlinson bolted together 2 small programs, one for leaving messages on a machine, one for copying files between machines, and produced the first networked email. He needed a way to say which person at which computer, and he looked down at his keyboard and chose a character that meant @ and appeared in no one's name. The AT sign. You carry his choice in your pocket, in your email address, 50 years on. The first message, sent between 2 computers sitting side by side but connected through the network, was, by his own recollection, something like QWWERTYUIOP. He said later that he invented email mostly because it seemed like a neat idea, and that no one was asking for it. Within a couple of years, the majority of all traffic on the ARPANET was email. The network for sharing machines had become a network for sharing minds, and every network since has followed the same arc. The communication is the resource. In October 1972, the ARPANET had its public debut, a full demonstration at a conference in Washington, organized by a young BBN engineer named Bob Kahn. Machines from across the country, reachable live in a hotel basement. It worked. And already the next problem was visible, because the ARPANET was no longer the only network. Out in Hawaii, Norm Abramson's group had built AlohaNet in 1971, a network with no wires at all, where the computers shouted packets into shared radio channels and sorted out the collisions by simple rules of etiquette. That random access idea, packets fighting politely for a shared medium, would be adapted to a coaxial cable at Xerox PARTS in 1973 by Bob Metcalf. And the result was called Ethernet, the ancestor of every office network, and at one more remove of the Wi-Fi in the air around you right now. There was a satellite network too, reaching Europe. 3 networks, 3 technologies, 3 owners. And they could not talk to each other. Each one was an island with its own customs. The solution to that problem is arguably the single most important design in this entire video, and it arrived in a paper in May 1974, written by Vint Cerf and Bob Kahn, a protocol for packet network intercommunication. The question they answered is subtle, so take it slowly. You cannot force every network to be the same. A radio network and a telephone line network and a satellite network are different creatures, and new ones will always be invented. So do not try. Let every network keep its own rules inside its own borders, and define one common language that the networks speak to each other through special machines at the borders, which Cerf and Kahn called gateways, and which we now call routers, and make a hard decision about responsibility. The network promises almost nothing. It will try to deliver each packet, and it may fail. Drop it, duplicate it, deliver them out of order. Best effort. The intelligence lives at the edges, in your computer and mine, which check and correct and ask for retransmission. This was a philosophical inversion of the telephone company, where the network was smart and the telephone was dumb. Cerf and Kahn made the network simple and the ends smart. And that choice, more than any other, is why the internet could grow without asking anyone's permission. Their protocol was named TCP. In 1978, it was split into two layers, TCP and IP, and TCP/IP is the constitution the internet still lives under. They did not stop at publishing it. They proved it in November 1977, with a demonstration that reads like a stunt. A van drove down a California highway with a computer shouting packets over radio into a local radio network, across the ARPANET, up to a satellite, down into Europe, and back again. Packets crossed 3 networks and an ocean, and arrived intact, with no end to end wire anywhere in the chain. The internetwork, the internet, worked. Then came the adoption, and it had a date, and the date has a name. The old ARPANET protocol, NCP, was tied to the IMP machines. TCP/IP was not. In March 1982, the Department of Defense made TCP/IP its standard and set the transition. On the 1st of January, 1983, the ARPANET would turn off NCP entirely in one day, a flag day. Every host on the network converted or lost access. It is almost unimaginable now, switching the protocol of a continental network on a single morning. And they did it, and the modern internet is usually dated from that day. 6 months later, in June 1983, another quiet piece of the foundation was tested. The network's addresses were numbers, and the table translating human names to numbers lived in a single file maintained at one institute in California, and every computer on the net had to fetch fresh copies, and the file was visibly outgrowing the world. Paul Mokapetris and John Postel replaced it with a distributed hierarchy of name servers, tested that June, specified that November. The domain name system, DNS. The reason you type letters and not numbers. One more institution carried the internet across the finish line into public life. In 1985 and 86, the National Science Foundation built NSFNET to connect its new supercomputer centers, and then, fatefully, opened the backbone to universities generally. Academic traffic flooded in. The backbone was upgraded again and again, and the NSF's acceptable use rules kept commerce out, which only built pressure behind the dam. In the early 90s, the restrictions fell away, and in April 1995, its work done, the NSF net backbone was switched off, and the Internet became what it is now. Not one network. A federation of tens of thousands of privately run networks, all agreeing on one protocol, owned by everyone and no one. Baran's net with no center, at planetary scale, exactly as designed. And yet, in 1990, almost none of this touched ordinary life. The Internet connected universities and laboratories. Its information lived on machines you reached with arcane commands, through tools with names like FTP and Gopher, and finding anything required, knowing where it already was. The wires connected the world, and the world's knowledge still sat behind locked doors in scattered filing cabinets. The last piece, the piece that turned a research network into the thing in your pocket, was invented in a physics laboratory in Switzerland by a man who kept losing track of which document lived on which machine. He wrote a proposal about it. His supervisor wrote 3 words on the cover. Vague, but exciting. The World Wide Web is next. The Internet connected the machines. But connecting machines is not the same as connecting knowledge. By the end of the 1980s, you could, in principle, reach a computer across an ocean. In practice, the information on it sat behind arcane commands. In filing systems, you had to already know your way around. The wires were global. The knowledge was still locked in cabinets. This is the story of the key. And the key was imagined long before it was built. 3 times, by 3 men, decades apart. The first was Vannevar Bush, and you have to place him correctly. He was not a dreamer on the fringe. He ran America's entire scientific war effort, the Office of Scientific Research and Development, the man at the top of the pyramid that built radar and the bomb. And in July of 1945, with the war ending, he published an essay in The Atlantic called As We May Think, and it was about a problem of peace. Science, he said, had given humanity an explosion of information, and our methods for finding any of it were still medieval. Libraries were warehouses with ladders. Knowledge worked by association, the mind leaping from one idea to a related one, while our filing systems forced everything into alphabetical rows. So he described a machine to match the mind, the Memex, a desk in which an individual stores all his books, records, and communications on microfilm with screens and levers. And this is the whole idea, with the ability to bind any document to any other with a permanent link, an associative trail, so that years later you could follow the trail again, or hand it to a friend. A private, linked library at your desk. He wrote this in 1945. There were no computers to build it with. There was barely a word for what he was describing. The second man gave it the word. Ted Nelson was a sociology graduate student at Harvard in 1960 when he took a computer course and had what can only be called a vision, and he spent the rest of his life chasing it. He named the thing Bush had gestured at. Hypertext. Text that is not a line, but a web. Text you can branch out of, mid-sentence, to anywhere. He coined the word in 1963 and published it in 1965, and he founded Project Xanadu, to build it. A worldwide library where every quotation would stay connected to its source, where links would work in both directions, where nothing would ever break or vanish, where authors would be paid in micropennies. It was a grander design than what we ended up with. It was also, famously, never finished. Xanadu's first incomplete public release arrived in 1998, 38 years after it began. And by then, the world had settled for something cruder. Nelson's judgment on the crude winner was sharp. Today's popular software, he said, simulates paper. Keep that grudge in mind. We will come back to what was traded away. The third man proved it could exist at all. Douglas Engelbart had read Bush's essay as a young radar technician during the war, and it set the direction of his life. Computers, he decided, should augment human intellect, help people think together. At the Stanford Research Institute, through the 1960s, he and his team built a system called NLS that quietly contained the future. And on the 9th of December, 1968, at the Fall Joint Computer Conference in San Francisco, before about 1,000 computer professionals, Engelbart showed it. 90 minutes. On the screen, live, he demonstrated text editing, and Windows, and video conferencing, and two people in two cities editing the same document at the same time, and hypertext links he clicked with a little wooden device on wheels that his colleague Bill English had built from his sketches, which they called a mouse because of the tail. The audience gave him a standing ovation, and the demo is remembered now as the mother of all demos, because nearly everything you use was in that room in 1968. And then the funding dried up in 1975, and Engelbart's people scattered, many of them to Xerox PARC, carrying the ideas with them. We will meet that place properly in the part about interfaces. So by the 1980s, hypertext existed. There were systems, dozens of them, in labs and on early personal computers. But they were all islands. They linked within one document collection, on one machine, or within one product. Nobody's link could point into somebody else's world. Which brings us to Geneva, and to a physicist's irritation. CERN, the European Physics Laboratory, is one of the most wonderful and most forgetful organizations on Earth. Thousands of scientists flow through it from 100 countries, staying months or years. And its real knowledge lived in corridor gossip, in notebooks, in the heads of people perpetually about to leave. Documents scattered across incompatible machines. Tim Berners-Lee had seen it up close. During a stint at CERN in 1980, he had written himself a private hypertext program called Enquire, named after a Victorian household manual called Enquire Within Upon Everything, a little web of typed links to keep track of his own projects. He left and came back in 1984 with a fellowship, and spent the intervening years learning networks the hard way, writing remote procedure call code. And in March of 1989, he wrote a proposal and handed it to his supervisor, Mike Sendell. It is worth reading that proposal because it is not triumphant. It is a quiet engineering memo about the loss of information at CERN, and about how the laboratory's real structure is not the org chart, but a multiply connected web of who knows what. And it proposes, modestly, a distributed hypertext system. Linked documents, readable from any machine, where a link in one document could point to a document on a different machine entirely. Sendel read it and wrote on the cover the 3 most profitable words in the history of management. Vague, but exciting. And he let it proceed. The marriage Berners-Lee performed was between 2 existing things: hypertext, the Bush-Nelson-Engelbart lineage, and TCP/IP, the Surf-Con Internet, which CERN had embraced early, making it the largest Internet site in Europe. That combination is the entire invention, and its genius is in what he left out. Look at the design decisions, because each one is a deliberate simplification, and the simplifications are why it spread. Every document gets a universal address, a URL, so that anything, anywhere, can be pointed at by anyone. The protocol, HTTP, is a tiny request and reply, "Get this address, here it is." The format, HTML, is plain text with a few tags, so simple a physicist could learn it in an afternoon, and, fatefully, so forgiving that a browser would render your page even if you wrote it wrong. And the links were one way. This is the decision to linger on, because it is where Nelson's dream was sacrificed. In Xanadu, links were 2-way, tracked, unbreakable, and that required a central accounting of everything. On the web, a link is just an address in a page. You can link to my document without my knowledge or consent. And if my document moves, your link rots, and nothing tells you. That is the famous flaw, the broken link, the 404. And it is precisely what made the web possible. A system where linking needs no one's permission can grow without asking anyone. The web traded perfection for permissionlessness, and the trade made it planetary. By Christmas of 1990, it worked. Berners-Lee had built the first server and the first browser on a Nextcube, a machine with such good development tools that, he said, he did in a couple of months what would have taken a year elsewhere. The first site, info.cern.cih, described the project itself, and the next bore a handwritten note. This machine is a server. Do not power down. And notice something. His program, called World Wide Web, was a browser and an editor in one. You read the web and you wrote it in the same window. The original web was not a medium for audiences. It was a commons for authors. On the 6th of August, 1991, he announced it to the Internet at large, and a student intern at CERN, Nicola Pello, wrote the simple line mode browser that freed the web from the next, so that any computer on Earth could read any page. And still, the web might have remained a physicist's tool, one protocol among several, had it not been for one decision and one accident. The accident first. The web's most serious rival in those years was Gopher, a tidy menu-based system from the University of Minnesota. And in 1993, Minnesota announced it would charge license fees for commercial servers. Users fled, exactly as you would expect, toward the alternative that cost nothing. Which raises the question, why did the web cost nothing? That is the decision. On the 30th of April, 1993, CERN's directors, Walter Hoogland and Helmut Weber, signed a short statement putting the web's software in the public domain. Royalty-free. Forever? For anyone. A physics laboratory gave away what a startup would have patented. And it is hard to find a more consequential act of institutional generosity in the history of technology. By the end of that year, there were more than 500 web servers, and the web was 1% of all internet traffic. A year later, at CERN, the first international web conference felt, to the people there, like Woodstock. Then came the spark that turned adoption into explosion. At the National Center for Supercomputing Applications in Illinois, a student programmer named Mark Andreessen and a programmer named Eric Bina wrote a browser called Mosaic, released in April of 1993, days before CERN's gift. Mosaic did two things earlier browsers had not. It was easy to install, so that an amateur could be browsing in minutes. And it put images inline, pictures and text on the same page, like a magazine, instead of the pictures that opened in separate windows. That single tag, IMG, changed what the web was for. It stopped being a library and became a page. NCSA reported that traffic devoted to web browsing grew 10,000-fold. Andreessen left Illinois at the end of 1993, teamed up with Jim Clark, a Silicon Graphics founder, and their company shipped Netscape Navigator in December of 1994. It was faster. It drew pages progressively as they loaded. It added cookies and a young language called JavaScript. And within months, it had 3/4 of the browser market. On the 9th of August, 1995, Netscape went public. The stock more than doubled on its first day. And Wall Street understood, all at once, that the web was a gold rush. The dot-com boom dates from that morning. What followed was the first browser war. Microsoft, late to the web, licensed Mosaic's code, shipped Internet Explorer in 1995, and then used its monopoly the simple way, by making its browser free and bolting it into Windows. Netscape, charging for what Microsoft gave away, bled, was sold to AOL. And in a final act of defiance, in 1998, released its code to the world, the seed from which Mozilla, and eventually Firefox, would grow. The war ended with the web's standards intact, largely because Berners-Lee had founded a consortium, the W3C, in 1994, to keep any one company, including his own side, from owning the language of the pages. And the boom, inflated by all that free excitement, peaked in March of 2000 and collapsed, wiping out thousands of companies and leaving behind, standing, the ones that had been selling things people actually wanted. The web shrugged off its own bubble. Usage never dipped. The last missing piece of the early web was finding anything at all. The web itself kept no index, so the first search engines built their own, crawling the pages and matching keywords, and they drowned in their own indexes. The fix came from two Stanford graduate students, Larry Page and Sergey Brin, in 1998. And the idea was to listen to the links. A link, they argued, is a vote, and a vote from a page that itself has many votes counts for more. Run that logic over the whole web, round and round until it settles, and every page gets a score, an authority drawn from the structure of the web itself, rather than from anyone's opinion. They called it PageRank. The mathematics of it is an eigenvector of a very large matrix, and it worked so much better than everything before it that a research project became Google. The keyword engines read the pages. PageRank read the web. Let us settle what the web is, because the confusion is universal and worth curing. The web is not the internet. The internet is the network of part 12, the wires and packets and routers, the thing that moves bits. The web is a layer of agreements on top of it, documents, addresses, and links. 3 ideas, each one almost trivial, combining into the largest library, marketplace, and argument in human history. When you click a link, your browser reads the address, asks the network for the machine named in it, speaks HTTP to that machine, receives a page of HTML, and renders it. That is all. There is no center. There is no index the web itself maintains. Anyone may publish a page, anyone may link to it, and no committee approves either act. Every property people love about the web, and every property people despair of, descends from that permissionlessness. It is Bush's trails, at planetary scale, without the desk. It is Nelson's Xanadu, minus the guarantees. It is Engelbart's demo, given to everyone. Now, pages are not the only way to organize the world's information. And long before the first link was clicked, a quieter technology had been organizing the facts underneath everything else. Bank balances, airline seats, the census. Every record the modern world cannot afford to lose. It predates the internet. It predates the personal computer. And it has its own founding mathematics, worked out by one IBM researcher whose employer took years to believe him. The database is next. The web organizes the world's pages. But underneath the pages, older and quieter, is the machinery that organizes the world's facts. Your bank balance, your flight reservation, the inventory of every warehouse, the payroll of every company, the medical record of every patient. This machinery predates the internet, predates the personal computer. And it begins, like so much in this story, with a problem of coupling that had become unaffordable. To see the problem, go back to the early 1960s, before the word database existed. A company's data lived in files, mostly on reels of magnetic tape, and the practice had descended directly from the punched card era. A file was a sequence of records. A record was a row of fields. And here is the detail that matters. The layout of those fields, the customer's name in columns 1 through 20, the balance in 21 through 28, was defined inside each program that read the file. The data and the code were fused. Now imagine that the company needs one more digit in the account number. Every program that touches that file must be found, edited, recompiled, retested. Miss one, and it silently reads the balance from the wrong columns. And the tapes themselves were serial creatures. Finding one record meant reading past all the records before it, and sorting a tape file was an overnight production. Banks needed balances now. Airlines were filling reservation books by telephone. The filing cabinet had been electrified, but not yet rethought. The first rethink came from an engineer, not a mathematician, and it is fitting that he had run a chemical plant. Charles Bachman spent the 1950s in the data processing world of Dow Chemical. And by the early 60s, he was at General Electric, automating business processes, when GE installed one of the new disk drives, a device that could jump to any record directly, no winding. Bachmann grasped what random access meant for data. Records could point to each other. An order could point to its customer, a part to its supplier, and the pointers could be followed at machine speed. The system he designed, the Integrated Data Store, released in 1964, was the first true database management system, a single piece of software that owned the data and served it to every program. Its model was called the network model, records linked into a web, and its style of use was called navigation. To find anything, the programmer wrote a path. Start at the customer, follow the pointer to the orders, follow each order to its items. Bachmann was honest about this in the title of the lecture he gave when he won the Turing Award in 1973. The Programmer as Navigator. He was the first Turing winner without a doctorate, the first from industry. And his system became the codicil standard that ran much of the business world for 2 decades. Meanwhile, IBM built the other great early answer for the grandest customer imaginable. The Apollo program needed to track the bill of materials for the Saturn V, millions of parts, and worse, the endless engineering changes to those parts, so that no engineer ever worked from a stale revision. IBM, North American Aviation, and Caterpillar developed a system, delivered in 1967 and 68, that organized data as trees. Each record has a parent. A record may have many children. The parts of a stage, the stages of the rocket, the hierarchical model. It became IBM's product, IMS, announced in 1968. And here is a detail I love. IMS never went away. It processed transactions for banks while men walked on the moon, and it processes transactions for banks tonight. Both of these systems worked. Both had the same deep flaw, and it was the old coupling flaw in a new form. The shape of the data, the pointers, the tree, was still written into every program. Restructure the database, and every navigation path in every program had to be walked again by hand. Asking a new kind of question meant writing a new program. Data was served, but it was not yet free. The man who freed it was, this time, a mathematician. Edgar Codd, Oxford-trained, worked at IBM's research laboratory in San Jose, and in June of 1970, he published a paper with a dry title, A Relational Model of Data for Large Shared Data Banks, and an incendiary opening demand. Users, he wrote, must be protected from having to know how the data is organized in the machine. Not advised, protected. The internal arrangement could change overnight. For efficiency, for growth, and not one program, not one person at a terminal should even notice. His proposal achieved this by an act of radical simplification. Throw away the pointers and the trees. Present all data as tables. Rows and columns, nothing else. A table of customers, a table of orders, and relationships expressed not by pointers, but by shared values. The orders row carries the customer's number. And then, the second half of the trick, borrowed from mathematical logic. Do not write paths. Declare what you want. The orders, over $500, placed this month by customers in France. You describe the answer's properties. The system figures out how to find it. And it can figure out a good way even if the data's physical arrangement has changed completely. This is the relational model. Say what, not how. It sounds gentle. It was a declaration of war on the entire installed base, and IBM, which earned a fortune from IMS, was in no hurry. Codd published, and for years his own employer's product line ignored him. So the relational model had to be proven twice outside the product division before it conquered anything. The first proof was IBM's own research project, System R, begun at San Jose in 1974, and its mission was to answer the skeptics' one serious objection. Tables and logic are elegant, but can they be fast? The System R team answered with inventions that are now so standard you have used them today without knowing their names. Don Chamberlain and Ray Boyce designed a query language in structured English, SQL, later shortened to SQL, over a trademark conflict, so that declarative questions could be typed by ordinary humans. Boyce died of a brain aneurysm that same year, 1974, at 27. And the language that outlived him is on your bank's machines right now. Patricia Sellinger built the cost-based optimizer, the component that examines your what and chooses among thousands of possible hows, estimating which path is cheapest. And Jim Gray built the machinery of locking and recovery that let hundreds of users bang on the same tables at once without chaos. System R's first real customer, Pratt & Whitney, came in 1977. Relational could perform. The second proof happened concurrently at Berkeley, where Michael Stonebreaker and Eugene Wong, funded at first for a campus geographic data project, and then by DARPA, built Engray starting in 1973 and 74 with its own language, Quell. Engray seeded an extraordinary family tree. Its commercial descendants were everywhere by the 80s, and its direct continuation at Berkeley, called Postgres, is the ancestor of PostgreSQL, one of the most relied upon databases in the world today. Stonebreaker took the Turing Award in 2014 for the whole body of work. And then there is the third story, the one business schools tell. The System R researchers published their papers openly, as researchers do. In 1977, 3 men in California, Larry Ellison, Bob Miner, and Ed Oates, read those papers and saw what IBM's management had not: a product. They founded a tiny company, took a contract whose code name from an earlier intelligence community project was Oracle, and shipped their database in 1979. There was no version 1. The first release was called version 2, on the theory that nobody buys a version 1. It ran on a mini computer in 128 kilobytes of memory, and it was the world's first commercial SQL database. IBM's own relational product, DB2, arrived in 1983, 4 years late, to a market its own research had created. Oracle was a billion-dollar company by 1990. Codd lived to see his model win everything, and to grumble, correctly, that SQL and the products around it honored his mathematics only in the breach. He had wanted purer logic. The world wanted working tables. The world got both, mostly. Now, underneath all of this, there is a quieter concept that may be the most important idea in this entire part, because it is the reason civilization can trust machines with money: the transaction. Think about what a bank transfer really is. Money leaves one account and arrives in another. 2 rights. And the world ends if only one of them happens. The money cannot vanish between the accounts, not even if the machine loses power at the worst possible microsecond. And while the transfer is half done, no one else may see the half state. And when it is done, done means done. Not done unless the disk fails. The database community turned this bundle of promises into engineering. And the man who did more than anyone to make it rigorous was Jim Gray, first inside System R, then at Tandem Building Machines for exactly this, non-stop transaction processing. The guarantees are known by their acronym, ACID. Atomicity, the transfer happens completely or not at all. Consistency, it moves the database from one valid state to another. Isolation, concurrent transactions cannot see each other's half-written work. Durability, once committed, the right survives the crash. Every time you move money, book a seat, or buy anything, you are leaning on four properties that were hammered into reliability over decades, largely by Gray. He won the Turing Award in 1998. In January of 2007, he sailed his boat out of San Francisco Bay alone toward the Farallon Islands and vanished. And despite one of the largest civilian search efforts ever mounted, thousands of volunteers scanning satellite photographs of the ocean, no trace was ever found. The systems he built have not once been lost. The story has one more loop, because scale kept changing the question. The relational empire held through the 80s and 90s. Then the web companies arrived with data measured in machines, not disks, thousands of cheap servers failing daily. And Google published its three famous papers: the file system in 2003, MapReduce in 2004, Bigtable in 2006, describing infrastructure that spread data and computation across whole warehouses of commodity hardware. A generation of systems followed under the banner NoSQL, trading away SQL's guarantees for availability and scale. And the trade-offs had been formalized by Eric Brewer's CAP principle, proven in 2002, which says a distributed system facing a network partition must choose between consistency and availability. It cannot promise both. For a few years, it was fashionable to declare SQL dead. And then the industry noticed what the applications actually needed. And one by one, the new systems grew query languages, transactions, and schemas, and Google itself published Spanner in 2012, a globally distributed database that is, of all things, SQL. There is a line from the Carnegie Mellon database group that should close this loop. The SQL versus no SQL debate, they say, replays the relational versus codicil debate of the 1970s. And the spoiler is the same both times. The relational model almost always wins. One footnote, small and enormous. Somewhere in your pocket right now is the most widely deployed database engine on Earth, and it is not Oracle, and it is not IBM's. In 2000, a programmer named Richard Hipp, working on software for a Navy destroyer, grew tired of operating a separate database server for an application and wrote one that needs no server at all. The whole database is a single file. The whole engine is a library woven directly into the application. SQLite. It is in every phone, every browser, most televisions, most cars, in quantities no one can count. When Android's millions of phones began surfacing rare bugs in it, Hipp spent a year of 60-hour weeks building a test suite that exercises every branch of the code at machine code level, and the bug reports stopped. The deepest infrastructure of daily life is often the software no one ever sees. All of this machinery, from Bachmann's pointers to Spanner's atomic clocks, answers one kind of question. What do we already know? Store it, find it, protect it, recombine it. The oldest dream of computer science was always a different question. Can the machine produce something no one stored? An answer that was never written down. A judgment. A thought. That dream was named at a summer workshop at Dartmouth in 1956, but it had begun, in a sense, with those threshold neurons of McCulloch and Pitts back in Part 10. Artificial intelligence is next. Every other part of this video describes a machine that does what it is told, faster and more reliably than any human. This part is about the oldest dream in the whole story, the dream that breaks that pattern. A machine that does what it was never told. You can feel how old the dream is, because it was already being argued about before a single modern computer existed. Remember Ada Lovelace in 1843, writing that the analytical engine has no pretensions to originate anything. And remember Alan Turing in 1950, answering her directly in the paper that proposed the imitation game. Can machines think? He asked, and then refused the question's wording and replaced it with a test. If a machine converses so that you cannot tell it from a person, he argued, the question of what it is doing inside stops mattering. The field of artificial intelligence was born between those two people, 7 years before it had a name. And from the very start, the dream came in two flavors, two bets about what intelligence is made of, and the entire 70-year history we are about to walk through is the pendulum swinging between them. The first bet says intelligence is reasoning. Symbols, rules, logic. Give the machine facts and rules of inference, and it will prove, plan, deduce. The second bet says intelligence is learning. Do not write the rules. Wire up something simple, like a neuron, and let experience shape it. In 1943, Warren McCulloch and Walter Pitts, whom we met in Part 10, had shown that a net of threshold neurons could compute any logic. So both bets were on the table before either had a machine to run on. The naming happened at a summer workshop, and the proposal is worth quoting, because its confidence still takes the breath away. On the 31st of August, 1955, 4 men, John McCarthy, a young Dartmouth mathematician, Marvin Minsky at Harvard, Nathaniel Rochester, the designer of IBM's 701, and Claude Shannon himself, wrote to the Rockefeller Foundation asking for $13,500 to fund a 2-month, 10-man study. The study would proceed, they wrote, on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. Language, abstraction, problem-solving, self-improvement. In a summer, the foundation gave them half. The workshop convened at Dartmouth in the summer of 1956, people drifting in and out across 8 weeks. And it did not solve intelligence, but it did christen it. McCarthy had coined the phrase artificial intelligence for the proposal, to nail the flag to the mast, as he put it. A field now existed, and it existed, with maximum ambition, written into its birth certificate. And here is the thing about that summer. The attendees brought results that seemed to prove the conjecture already. Alan Newell and Herbert Simon, with the programmer Cliff Shaw, arrived from the Rand Corporation carrying the logic theorist, a program that proved theorems in symbolic logic. It had already ground through the first chapter of Whitehead and Russell's Principia Mathematica, the same book whose formalism Gödel had turned against itself. And it proved 38 of the first 52 theorems. And for one of them, it found a proof more elegant than the one Russell and Whitehead had sweated out by hand. Simon showed the new proof to Russell himself, then in his 80s, who responded with delight. And when they submitted the work to the Journal of Symbolic Logic, it was rejected as unremarkable, a new proof of an elementary theorem being no news, the referees apparently overlooking that one of the authors was a computer program. Meanwhile, at IBM, Arthur Samuel had been writing a checkers player since 1952, and by 1955, his program was not playing the game Samuel taught it. It was playing games against itself, adjusting its own evaluation of positions, and learning to beat the person who wrote it. Samuel demonstrated it on television in February of 1956, and in his 1959 paper, he gave the second bet its name: machine learning. The field would later watch his little program's descendants go all the way. In 1962, it beat a checkers master, Robert Neely, and in 2007, researchers proved the game of checkers completely solved, optimal play in every position, 55 years after Samuel's first version. So the early years were drunk on momentum, and the predictions were made, and they are painful to read now. Simon and Newell predicted a computer world chess champion within 10 years. That was 1958, and the neuron bet had its own spectacular moment. At Cornell's Aeronautical Laboratory, a psychologist named Frank Rosenblatt built the perceptron, a learning machine for recognizing patterns. And in July of 1958, the Navy held a press conference about it. And the newspapers lost all restraint. The New York Times reported the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. The New Yorker called it the first serious rival to the human brain ever devised. By 1960, Rosenblatt had the Mark I perceptron, a real machine, a wall of photocells wired through motor-driven dials that physically turned to learn. You can see it today at the Smithsonian. The 60s produced the illusions too, and the illusions taught more than the successes. In 1966, Joseph Weizenbaum at MIT wrote a little program called ELIZA, which played a therapist by the cheapest trick imaginable, reflecting your sentences back as questions. Tell it you are unhappy, and it asks why you think you are unhappy. People confessed their lives to it. Weizenbaum's own secretary asked him to leave the room so she could talk to it privately. He had built it as a parody, and the public's eagerness to be understood by it horrified him for the rest of his life. In 1970, Terry Winograd's SHRDLU conversed about a world of colored blocks, stacking them on command, answering questions about what it had done, and it looked like understanding. until you realized the block's world was all it knew. Both programs showed the same lesson from opposite sides. Fluency in a narrow frame is easy to mistake for intelligence, and humans are desperate to make the mistake. Then came the winter, and it had causes. In 1966, a government committee, ALPAC, judged that machine translation, a decade into lavish funding, had produced nothing worth the money, and the funding stopped. In 1969, Minsky and Seymour Papert published a small, devastating book called Perceptrons, which proved, with clean mathematics, that Rosenblatt's single-layer machine could not learn certain trivially simple patterns, could not even compute the XOR function, the little logical operation that asks whether two bits differ. Everyone knew a deeper network could escape the proof. Nobody knew how to train a deeper network. The book did not claim more than it proved, but its effect was wider than its proof. Funding for the neuron approach dried up for a generation. And in 1973, the British government commissioned Sir James Lighthill to survey the whole field. And his report judged that AI had failed to deliver anything like its promises, and Britain's funding collapsed, and the chill crossed the Atlantic. The first AI winter, the field that had promised a summer, had to survive a decade. What thawed it in the early 80s was the first bet wearing a business suit, the expert system. The idea was humble compared to the old dream. Do not simulate intelligence. Capture one narrow expert's knowledge as thousands of explicit rules and chain them. It had begun quietly in 1965 with Dendril at Stanford, which inferred molecular structures from mass spectrometer data, genuinely useful to chemists. Mycin followed in the 70s, diagnosing blood infections with a few hundred rules, performing in tests as well as specialists, and never once deployed in a hospital, because nobody could answer the question of who is liable when the rule machine is wrong. And then the one that made the money. XCON, built by John McDermott at Carnegie Mellon for Digital Equipment Corporation, went to work in 1980 configuring VAX computer orders, making sure every order's components, cables, and cabinets actually fit together. Human configurers got about 30% of orders wrong. XCON got it under 2% and saved DEC tens of millions of dollars a year. Corporations stampeded. An industry of expert system companies and of special Lisp machines to run them boomed within a few years. And then it broke for the oldest reason. The systems were brittle. They knew thousands of rules and no common sense. They could not learn. They fell over the first time reality wandered outside the rulebook. And the expensive Lisp machines were undercut by cheap Unix workstations. By the early 90s, the second winter had arrived. 2 booms, 2 busts. The field's own historians now say the lesson plainly. AI's winters are made of its promises. The second dream, the neuron, had never actually died. It had just gone unfunded and unglamorous. And in October of 1986, in Nature, David Rumelhart, Geoffrey Hinton, and Ronald Williams published a 2-page letter with the title Learning Representations by Back Propagating Errors. And it gave the world the missing piece from 1969, how to train the deep network. The idea is, at heart, one of the oldest tricks in calculus. Run the network, measure how wrong the answer is, and then flow the blame backwards, layer by layer, asking each connection how much it contributed to the error, and nudge every one of them a tiny step in the direction that reduces it. Billions of tiny nudges. Paul Werbus had described the method in his thesis in 1974 and been ignored. Now, with more computers and more patience, it worked. And multi-layer networks began to learn things no one had been able to teach them by hand. The pendulum began its long swing back, powered by statistics instead of logic. But the first summit to fall fell to the other camp, to pure search. Chess had been the field's chosen proof of intelligence since Shannon's 1950 paper on how a machine might play. And in May of 1997, in New York, IBM's Deep Blue, 200 million positions evaluated per second, faced Garry Kasparov in a rematch. Kasparov had beaten it the year before. This time, in the deciding sixth game, the champion, the greatest player in history, cracked under the pressure of the machine's strange, calm, inhuman moves, and resigned after 19 moves, the shortest loss of his career. The world gasped, and the AI researchers mostly shrugged, because Deep Blue did not learn anything. It searched. It was the logic theorist's lineage, with 40 years of Moore's law behind it. The real lesson of Deep Blue was not that machines had become intelligent. It was that a narrow enough pinnacle of human intellect could be toppled by brute force. The learning lineage needed 2 more ingredients, and both arrived from outside AI. The first was data. In 2007, a Stanford professor named Fei Li began a project her colleagues considered insane. Label millions of images, every object in them, organized by the tens of thousands of categories of an existing lexical database. ImageNet was finished in 2009. About 15 million labeled images, assembled with the help of tens of thousands of internet workers across 167 countries. The second ingredient was the graphics card, the GPU, built to shade video game polygons, which turned out to be exactly the right machine for the vast, dumb, parallel arithmetic of neural networks. In 2012, Hinton and 2 of his students, Alex Krzyzewski and Ilya Suskiver, entered the annual ImageNet competition with a deep convolutional network trained on 2 gaming GPUs. It made errors on 15.3% of the images. The runner-up, the best of the carefully engineered traditional methods, made 26%. The gap was not a margin. It was a discontinuity. Within 2 years, every major lab on Earth had converted. The deep learning era had begun, and the recipe from then on stayed eerily constant. A simple learning rule, an ocean of data, and a pile of GPUs. Scale did what cleverness could not. 2 more moments fixed the shape of the age. In March of 2016, in Seoul, DeepMind's AlphaGo faced Lee Sedol, one of the greatest Go players alive. Go was supposed to be safe for decades. Too many positions for search, too subtle for rules. AlphaGo won 4 games to 1, and in Game 2 it played Move 37. A shoulder hit on the 5th line that every professional watching thought was a blunder, a move with, by the system's own estimate, a 1 in 10,000 chance of being played by a human. It was the winning move. Centuries of Go wisdom said no, and the machine had found, through millions of games against itself, that the wisdom was incomplete. And then, in Game 4, Lee Sedol, down 3 games, played Move 78, a wedge between 2 white stones that no one saw coming, which the machine fatally misread. The humans called it God's touch, 1 game back for our species, and then no more. The next year's version learned Go from 0, self-play only, no human games at all, and crushed its predecessor 100-0. And in 2017, a team at Google published a paper with a title that reads, like a dare, "Attention is all you need." They threw out the recurrence and convolution everyone used for language and built a network out of pure attention. A mechanism that lets every word in a sentence look directly at every other word and weigh which ones matter. It trained fast because everything could be computed in parallel. It scaled beautifully. The architecture, called the transformer, is underneath essentially everything you have seen since. The GPT series scaled it up on internet text, and on the 30th of November, 2022, a research preview called ChatGPT was released, and 100 million people arrived within 2 months, the fastest adopted technology product in history to that point. The same transformer idea folded proteins in AlphaFold, wrote code, passed bar exams, and started arguments we are still having. Where does that leave the 70-year pendulum? The symbolic dream wanted machines that reason and delivered logic that could not learn. The learning dream wanted machines that adapt and delivered systems that learn fluently and reason shallowly, that can discuss Gödel and count the letters in a word incorrectly. John Searle's old objection from 1980, the Chinese room, still hangs in the air. The argument that a system manipulating symbols by rule, however fluently, may understand nothing at all. Whether the modern network has refuted him or merely made his thought experiment harder to dismiss is a live question, and honest people still divide on it. Roger Penrose argued in 1989 in The Emperor's New Mind that human mathematical insight must be something no machine following rules can replicate. David Chalmers gave the deepest form of the doubt its name, the hard problem of consciousness, the question of why there is anything it is like to be a mind at all. What is not in doubt is the pattern of the history. Every time the field promised understanding, it froze. Every time it accepted a dumb mechanism at enormous scale, the tally marks of Part 2, the statistics, the arithmetic, it advanced. Intelligence, whatever it is, keeps turning out to have more computation in it and less magic than we expected. Whether there is any magic left at the bottom of it is the question the next 50 years will answer. We leave the thinking machines there, at the frontier, and turn to a quieter branch of the field that touches your life more times a day than any other. Because none of this connected world, not the banking, not the shopping, not the messages between lovers or generals, works unless strangers can keep secrets from each other in public on wires anyone can tap. The mathematics of secrets. Cryptography is next. The oldest surviving act of encryption may be a recipe. A clay tablet from Mesopotamia, about 3,500 years old, records a formula for ceramic glaze in deliberately scrambled writing, a potter's trade secret. From that day to this one, the contest has never paused. Sparta wrapped leather strips around a rod called a saitale, so that only the matching rod could read the marching orders. Caesar shifted his letters by 3. For 2,000 years, that was the whole game. One side invents a disguise, the other side learns to see through it, and nobody could say, in any rigorous sense, how secure anything was. It was an art, and it stayed an art until a single paper, in 1949, ended the ancient era in one stroke. We will get to that paper. First, the person who made breaking ciphers a science, 5 centuries before the paper. In 9th century Baghdad, the polymath al-Kindi wrote a manuscript on deciphering cryptographic messages, and in it, he described the first known technique of cryptanalysis, frequency analysis. The idea is so simple, it seems unfair. In any language, letters have personalities. In English, E dominates. A substitution cipher only relabels the letters. It does not change their personalities. So count the ciphertext, match the frequencies, and the disguise falls away. Any simple substitution, any Caesar shift, any code that maps letter to letter, breaks open under arithmetic. For centuries after al-Kindi, the code breakers ruled. The answer, eventually, was to change the disguise letter by letter, cycling through several alphabets with a keyword, and the result, perfected in the 16th century, and known by the name Vigenère, held out for 300 years as the indecipherable cipher. And here is a face from Part 3. Charles Babbage, in his restless middle age, took up the Vigenère as a diversion and broke it around 1846, realizing that a repeated keyword makes repeated patterns, and that once you measure the key's length, the cipher collapses into a handful of separate substitution puzzles, each one soft prey for frequency analysis. Characteristically, he never published. A Prussian officer named Friedrich Kasiski published the same break in 1863 and got the credit. Even in cryptography, Babbage was early and unrewarded. Now, the paper. Claude Shannon spent the war years at Bell Labs thinking about secrecy, and in 1945 he wrote a classified report, declassified and published in the Bell System Technical Journal in October of 1949 as Communication Theory of Secrecy Systems. It did for ciphers what his 1948 paper had done for communication. It gave the whole subject mathematics, and inside it sits one of the most beautiful results in all of computer science, the proof that perfect secrecy exists, and exactly one machine has it. Take your message as a string of bits, and take a key of purely random bits just as long, and add them together, bit by bit, modulo 2. The result is the one-time pad, first described by Frank Miller in 1882 and built into a teletype machine by Gilbert Vernom in 1917. Shannon proved that the intercepted ciphertext contains zero information about the message. None. Not a little. Zero, because every possible plaintext is equally likely. The catch is in the name. Use the pad twice, and the magic evaporates. The Soviets reused one-time pad keys in the 1940s, and American analysts spent years patiently reading the traffic in a project called Venona. The strongest cipher ever proven, defeated not by mathematics, but by a shortage of fresh randomness. Shannon had also proved the bad news inside the good news. Perfect secrecy demands a key as long as the message itself. Which means the hard problem was never really encryption. It is, and always was, getting the key safely to the other side. Hold that thought. It is the hinge of this whole part. Post-war cryptography left the battlefield and entered the bank. Computers were moving money, and money needs ciphers. At IBM, a physicist turned cryptographer named Horst Feistel built a cipher called Lucifer in 1971, which IBM licensed to Lloyd's of London for some of the first cash machines. When the U.S. National Bureau of Standards asked the country for a national encryption standard in 1973 and again in 1974, IBM submitted a descendant of Lucifer, and in 1977 it became the Data Encryption Standard, DES. And a controversy attached to it immediately, because the National Security Agency had been consulted in secret. The internal structure had never been publicly justified, and the key had been cut from Lucifer's 128 bits to 56. Critics, including two young researchers named Diffie and Hellman, suspected a deliberate weakening, a key size a government machine could grind through. The truth, when it surfaced years later, was stranger and more interesting. In 1990, two Israeli researchers published a powerful new attack called differential cryptanalysis, and when they aimed it at DES, the cipher held up suspiciously well. Its mysterious internal tables turned out to be hardened against exactly that attack. IBM and the NSA had known about the technique since 1974 and had quietly armored the public standard against it, while saying nothing and letting a whole field rediscover it 16 years later. But 56 bits is 56 bits, and Moore's law is patient. In 1998, the Electronic Frontier Foundation built a machine called Deep Crack for under $250,000 and pulled a DES key out of a challenge ciphertext in 56 hours. 6 months later, they did it again, in 22 hours, with the help of thousands of volunteers' computers. The point was political. The government had spent years telling industry that DES strength was enough, and a civil liberties nonprofit had just bought enough silicon to prove otherwise, and the sequel is one of the finest governance stories in computing. Instead of another secret consultation, the Standards Institute ran a fully open competition for a replacement. 15 ciphers from around the world, years of public attack, open conferences, and in October of 2000, the winner was announced. Not an American design. A Belgian one, Rijndael, by Joan Damon and Vincent Richman, standardized in 2001 as AES, the cipher that protects your banking tonight. Bruce Schneier, whose own candidate lost, wrote afterward that he had nothing but good things to say about the process. The lesson took a century to learn, and is stated best by its 19th century author, Auguste Kerckhoffs. A system must remain secure, even if everything about it, except the key, is public. Secrecy belongs in the key. The algorithm should face the world, all of which still leaves Shannon's catch untouched. The key. However good the cipher, two strangers who have never met cannot share a secret over a wire that enemies are reading. Or so every cryptographer knew until 1976, when two of the field's outsiders proved everyone wrong. Whitfield Diffie and Martin Hellman were warned by colleagues not to work in cryptography at all, a field owned by governments. They worked anyway, and in November of 1976, they published New Directions in Cryptography, and it changed the world permanently. Here is the idea, and you can hold it with paint. Two strangers, Alice and Bob, agree publicly on a can of yellow paint. Each privately chooses a secret color. Each mixes their secret into the yellow, and they exchange the mixtures in public down the tapped wire. Now each adds their own secret color to the other's mixture. Both end up with the same final color. The eavesdropper, holding only the exchanged mixtures, cannot unmix paint. That is the Diffie-Hellman key exchange, with the discrete logarithm problem playing the role of unmixable paint. Two people who have never met end up sharing a secret in full public view. Ralph Merkle had been groping toward the same summit with his puzzles, submitted for publication in 1975, and in the way of these things, left waiting. The door they opened had a second room behind it. Digital signatures, a way to prove a message came from you, unforgeably, again with strangers. Colleagues had warned them off the field. The field was theirs. The Turing Award followed, decades later. What Diffie and Hellman had was the key exchange. What the world also wanted was the full machine, a public key that anyone can use to seal a message, and a private key that only you can open. It arrived the next year, and the night of its invention is one of the great scenes in the field. In April of 1977, three MIT researchers, Ron Rivest, Adi Shamir, and Len Adelman, had spent a year chasing the idea. After a Passover Seder at a student's house with a fair amount of wine, Rivest stayed up, unable to sleep, and by morning he had worked out the scheme on paper. Two enormous prime numbers multiplied together. Multiplication is easy. Splitting the product back into its primes is, as far as anyone knows, crushingly hard. And on that one asymmetry, they built RSA. Martin Gardner announced it to the public in his Scientific American column in August of 1977. And with it, a challenge, a 129-digit number, and a $100 prize. Rivest estimated factoring it would take 40 quadrillion years with the technology of the day. It took 17. In 1994, 600 volunteers on about 1,600 machines, including, wonderfully, 2 fax machines pressed into service, factored it over 8 months. And the hidden message read, "The magic words are squeamish ossifrage." An ossifrage is a bone-breaking vulture. Cryptographers have always had their own sense of humor. RSA secured the first generation of Internet commerce, and the three inventors took the Turing Award in 2002. Around the same, mathematics grew the rest of the toolkit of trust. Digital signatures, which let you prove a message came from you and no one else, and hash functions, which grind any file down to a short fingerprint, so that changing a single letter changes the fingerprint, and tampering announces itself. And then, in December of 1997, the British government admitted that the revolution had happened twice. James Ellis at GCHQ, the successor to Bletchley Park, had proposed the possibility of non-secret encryption in 1969. Clifford Cox had found the factoring scheme in 1973, 4 years before RSA. Malcolm Williamson had found the key exchange in 1974, before Diffie and Hellman. All of it classified, all of it silent for a quarter century. Ellis died on the 25th of November, 1997, 1 month before the announcement. Diffie had once traveled to meet him and asked what he made of the public explosion. Ellis's answer deserves to be quoted. "Well, I don't know how much I should say. Let me just say that you people made much more of it than we did. The secret world had the mathematics first. The open world had the imagination to know what it was for. The 90s turned all of this from mathematics into politics in what are now called the crypto wars." Strong encryption was classified by the United States as a munition, like a missile, illegal to export. In June of 1991, a software engineer named Phil Zimmerman released Pretty Good Privacy, PGP, free military-grade encryption for ordinary people, explicitly as an act of civil disobedience, and it escaped onto the global internet within days. The government opened a criminal investigation that lasted 3 years. Zimmerman's defense found the perfect loophole. The source code was published as a book by MIT Press because books are protected speech even when their contents are regulated as arms. The book was mailed abroad and scanned back into code overseas. The investigation collapsed in 1996. The Clipper chip, the government's 1993 proposal for encryption with a built-in key the authorities could hold, died in 1994 when Matt Blaze found a fatal flaw in its design. By the end of the decade, the export rules were dismantled, and the principle the wars established is the one you live under now. Cryptography is not a weapon reserved for states. It is the load-bearing wall of ordinary life. When Netscape layered encryption into the web in 1994 and 95, creating the protocol called SSL, shopping, banking, and private life moved on to the public wires, protected by the descendants of that 1976 paper. Now the honest turn, because this part has 2 halves, and the second half is the one that actually gets people hurt. The mathematics holds. Almost nothing else does. The history of security is mostly not the history of broken ciphers. It is the history of everything around the ciphers failing. And the internet learned this in one night. On the evening of the 2nd of November, 1988, a Cornell graduate student named Robert Tappan Morris released a small, self-copying program from an MIT computer to cover his tracks. The Morris worm walked into Berkeley Unix machines through a forgotten debug feature in the mail program, through a buffer overflow in the finger service, and through a dictionary of weak passwords. Morris had meant it to spread slowly and secretly, a measurement of the internet's size. He had miscalibrated one number, the rate at which it reinfected machines already infected, and that one number turned a quiet experiment into a flood. Machines choked on hundreds of copies of the worm. Within hours, roughly 6,000 computers were down, about 1/10 of the entire internet as it then existed. Morris sent an anonymous apology and removal instructions out across the network. And the message could not get through, because the network was too damaged to carry it. He became the first person convicted under the Computer Fraud and Abuse Act, fined, given probation, and 400 hours of community service, and the response institutionalized security. Within weeks, DARPA stood up the Computer Emergency Response Team, CERT, the first organized nerve center for Internet incidents. The pattern set that night has repeated for 4 decades. 1971 had already seen the first playful worm, Creeper, displaying "I'm the Creeper, catch me if you can," and the first antivirus, Reaper, written to hunt it. In 1986, the first PC virus, Brain, rode floppy disks out of a shop in Lahore. In 2018, Spectre and Meltdown showed that the processors themselves leak secrets through their speed optimizations, through timing, the hardware's own heartbeat betraying what it computes. And always, beneath the technical layer, the human layer. Phishing. The phone call to the help desk. Remember from Part 11 that the very first computer passwords on CTSS in 1961 were stolen within a year by a student who simply asked the system for the master file. Alan Scher in 1962 and the most sophisticated modern attacker are running the same play. The mathematics of secrets is strong. The systems and the people operating them are what the attackers actually hunt. 2 frontier ideas belong in this part's last pages because they show where the mathematics of secrets is going. In 1985, Goldwasser, Macaulay, and Rakoff introduced zero-knowledge proofs, the eerie possibility of proving something is true while revealing nothing but its truth. I can prove I know a password without ever showing you the password. That idea now sits inside modern authentication and at the base of the privacy-preserving machinery being built today. And in 1994, Peter Shor proved that a sufficiently powerful quantum computer could factor those enormous numbers in polynomial time, which is to say, could dissolve RSA, and with it, much of the current world's encryption, in principle. The word principle matters. The machines do not yet exist at the needed scale, but the world's cryptographers did not wait. NIST ran another open competition, and in 2024, the first post-quantum encryption standards were published, new locks being installed everywhere, years before anyone can be sure the old ones will break. You will hear more about the quantum machines themselves in the final part. So, across 16 parts we have built the machine, wired its logic, taught it languages, given it an operating system, connected it to its siblings, built the web on top, organized its memory, taught it to learn, and taught it to keep secrets. There's one thing we have not yet honestly faced, and it is the most human part of the whole story. Building large software, on time, working as intended, remains something our civilization still cannot reliably do. Bridges mostly stand up. Software mostly does not. This has a name, the software crisis, and it was named at a specific conference in 1968. And the attempts to solve it created their own discipline, full of hard-won and bitterly funny lessons. Software engineering is next. Here is a confession the computing industry has been making in public for nearly 60 years. It began at a conference in October of 1968 in Garmisch, Germany, where NATO's Science Committee gathered about 50 of the field's leading figures, The conference was called Software Engineering, and the title was chosen, in the organizer's own words, to be provocative. It described a requirement, not a reality. There was no engineering of software in 1968, not the way there was engineering of bridges. What there was a body of shared pain. Project after project had arrived late, over budget, and wrong. Hardware was improving on its Moore's Law glide path, and the programs were collapsing under their own weight. And in the conference report, you can watch the attendees circle the admission. Software was in a crisis. Dijkstra later put the cause in one sentence, accepting his Turing Award. The major cause of the software crisis is that the machines have become several orders of magnitude more powerful. We had built machines that could do almost anything, and we did not know how to tell them what to do, reliably, at scale. The canonical disaster, the one the whole discipline learned from, was already underway at IBM. When IBM announced the system /360 in April of 1964, it bet the company on a family of computers that would share one operating system, OS 360, the most ambitious software anyone had attempted, and the software nearly sank the bet. The development staff was described as in disarray a full year before launch. The operating system struggled to run more than one job at a time. IBM poured people into the project, 1,000 additional programmers, spending more on software in a single year than had been budgeted for the entire machine line, and the system still shipped months late, incomplete. The man who had managed the hardware and then been handed the software was Frederick Brooks, and Brooks did something rarer than shipping on time. He wrote down what the failure taught him. In 1975, he published the mythical Man Month, and it remains, half a century later, the book everyone in software eventually reads, usually too late. Its most famous lesson is a law. Adding manpower to a late software project makes it later. This offends the instincts of every manager who has ever stared at a slipping schedule. And it is true, and Brooks explains exactly why. Software is not ditch digging. The work cannot always be partitioned. Some tasks are sequential, like pregnancy, 9 months, no matter how many mothers are assigned. And every new person must be taught the system by the people already building it. So the veterans stop building in order to teach. And the communication paths between people grow with the square of their number. Double the team, and you quadruple the conversations. The unit in the title, the Man Month, is the managerial fantasy that people and months are interchangeable currency. They are not. Around the law, Brooks scattered other permanent observations. The second system effect, the tendency to make your second design bloated with everything you were disciplined enough to leave out of your first, which is why the follow-up to a lean success so often collapses under ornament. And the advice that anticipated modern practice: plan to throw one away. You will anyway. The first version is for learning what you were actually building. 11 years later, Brooks delivered the deeper verdict in a 1986 essay titled No Silver Bullet. Everyone wanted the software equivalent of hardware's exponential ride, some technology that would make costs fall like transistor counts. Brooks said no such bullet exists, and he explained why with a distinction worth keeping for life. Software has accidental complexity and essential complexity. The accidental kind is the fight with the tools, the machine language, the slow turnaround, and that kind had been beaten down enormously by high-level languages, by time sharing, by better environments. But the essential kind is the problem itself. If the users want 30 behaviors, the program must contain 30 behaviors, and no tool removes them. And he named the 4 properties that make software's essence so hard. Complexity. A large program is one of the most complicated things humans make, and no 2 parts are quite alike. Conformity software must bend to every human institution it touches, with all their irrational edge cases. Changeability. Software is expected to change forever, because it can. And invisibility. You cannot draw a program the way you draw a bridge. It has no shape. So the field would get better, Brooks concluded, the way it always had, not by magic, but by accumulated craftsmanship. No silver bullet. He was right then, and every decade since has tested him. And so far, he is still right. The method's pendulum swung for decades, and one of its strangest stories belongs to the most famous methodology of all. In 1970, Winston Royce published a paper on managing large software projects, and it contained a diagram of a development process flowing downward through stages, requirements, design, coding, testing, like a waterfall. For 40 years, that diagram has been taught, attacked, and defended as the waterfall model, attributed to Royce. And the joke is that Royce drew it to warn against it. Read past the diagram, and he tells you plainly that the single-pass sequence does not work, that you must plan to iterate, to build a preliminary version first, to involve the customer continuously. The industry took the picture and skipped the text, then spent a generation discovering, painfully, that the text was right. In February of 2001, 17 practitioners met at a ski resort in Utah and issued the Agile Manifesto, 4 short lines valuing working software over comprehensive documentation, responding to change over following a plan. It was less a new invention than an overdue correction, and the pendulum has kept swinging between process and flexibility ever since, because, as Brooks would say, the difficulty is essential. There is no method that makes the hard part easy. There are only methods that keep the hard part visible. Now, the failures. Because this discipline was paid for in a currency of specific disasters, and 3 of them should be known by heart, the way engineers know the Tacoma Narrows Bridge. The first is the worst, because it is measured in lives. The Theric 25 was a radiation therapy machine, treating cancer patients in hospitals across North America between 1985 and 1987. Its predecessors had physical interlocks, hardware that made dangerous states impossible. The Theric 25 replaced those interlocks with software. And the software contained a race condition, a flaw that only appears when events coincide in time. In this case, when an experienced operator typed the treatment settings quickly, editing a field with practiced speed, the program's internal bookkeeping could fall out of step with the machine's actual configuration. And the machine could deliver the high power beam without its protective target in place. Patients received doses up to 250 times the intended amount. The machine's own display, when this happened, reported only malfunction 54, with no mention of radiation at all, because no one had imagined the failure, so no one had written the message for it. Hospitals reported the accidents. The manufacturer insisted the machine could not overdose anyone. It took 2 years and 6 known massive overdoses and deaths before the connection was made. Nancy Levison's investigation of the case, published in 1993, became a founding document of safety-critical software, and its lessons are carved into the field. Do not remove physical safeguards because the software seems reliable. Treat every malfunction as a possible catastrophe until proven otherwise, and never, ever let the same people who wrote the code be the only ones who check it. The second failure is the expensive one, and its cause is so small it hurts to read. On the 4th of June, 1996, the maiden flight of Ariane 5, Europe's new heavy rocket, ended 37 seconds after ignition, when the launcher veered, broke apart, and destroyed itself, taking 4 scientific satellites and about $370 million with it. The Inquiry Board's report is a masterpiece of clarity. A piece of the guidance system had been inherited from the older Ariane 4. Good engineering practice, reuse proven code. Inside it, a conversion took a 64-bit floating point number and stored it in a 16-bit integer. On Ariane 4, the value in question, a horizontal bias, could never exceed what 16 bits hold, so the conversion could never overflow. The new rocket flew a different, more aggressive trajectory, and 36 seconds into the flight, the value exceeded the range. The conversion crashed the guidance computer. The backup computer had already crashed the same way, a blink earlier, running the same code, and the rocket, flying blind, corrected toward nowhere. The precondition had never been written down, because on the old rocket, it had always silently been true. It had been true for so long, as one analysis put it, that it had stopped looking like an assumption at all. Reuse is not free. Code carries the invisible expectations of the machine it was born in. The third failure is the one every student memorizes because it is so purely avoidable. In September of 1999, NASA's Mars Climate Orbiter arrived at Mars after 10 months of flawless cruise, fired its engines to enter orbit, and was never heard from again. One team software at Lockheed Martin reported thruster impulses in pound force seconds, English units. The navigation team at the Jet Propulsion Laboratory expected Newton seconds, metric. The difference is a factor of 4.5, accumulated over months of small corrections, and it steered the spacecraft into the atmosphere to burn. The review board's verdict is the sentence to carry out of this part. The problem was not the error. It was the failure of the checks and balances in our processes to detect the error. Every mature engineering discipline is defined by that sentence. Errors are inevitable. Engineering is the system that catches them. And for balance, remember the disaster that did not happen. The year 2000 problem, 2-digit dates rolling over, was real, expensive, and mostly invisible at midnight, precisely because thousands of programmers spent years finding and fixing it first. The crisis you do not see is the one that got engineered away. Against this backdrop, the field built its actual toolkit, slowly, unglamorously, and this toolkit, more than any methodology, is what practicing programmers actually trust. Version control, the memory of the project. It begins in 1972 with Mark Rochkine's SCCS at Bell Labs, passes through RCS, CVS, and Subversion, and reaches its modern form in a fit of frustration. The Linux kernel, one of the largest collaborative projects in history, ran on emailed patches for its first decade, then adopted a commercial tool called BitKeeper in 2002. And when that arrangement collapsed in 2005, Linus Torvalds sat down and wrote his own replacement in about 10 days. It is called Git, and it is now so universal that it is less a tool than the heir of the profession. Testing, with Dijkstra's warning always attached. Testing can show the presence of bugs, never their absence. Code review, the simple discovery that a second reader catches what the author cannot see. Continuous integration, the machinery that rebuilds and retests everything on every change, so that errors are caught in hours instead of months. And open source, which Eric Raymond analyzed in 1997 in The Cathedral and The Bazaar, contrasting the cathedral builders, closed and careful, with The Bazaar, the chaotic open crowd, and formulating the Bazaar's faith in one line. Given enough eyeballs, all bugs are shallow. Sometimes the crowd fails badly. But the operating system this whole story has been circling, Linux, and the databases and the web's foundations were all built in the Bazaar. And the Bazaar's methods, review in the open, release early and often, have seeped into every serious software organization on Earth. So where does the crisis stand? 60 years after Garmisch. It never ended. It was absorbed. Software engineering turned out to be less like civil engineering, with its settled physics, and more like medicine, a practice of managing an irreducibly complex subject with accumulated discipline, honest postmortems, and humility about what one mind, or 1,000 minds, can hold. The field's deepest insight is that the machine was never the hard part. The hard part is us, our limits, our communication, our assumptions, the invisible preconditions we forgot we were standing on. Software engineering is the discipline of designing for human fallibility, using human fallibility. And that brings us to the person we have served throughout, usually badly. For most of the history in this video, the human being was expected to adapt to the machine, learn the codes, punch the cards, speak the command language, wait for the batch. The machine was a god in a glass room, and you approached it on its terms. Then a handful of people asked the inverting question: what if the machine adapted to the human? They gave us the mouse, the window, the desktop, the touch screen, the device your grandmother uses without a manual. The interface, how the computer became personal and then invisible, is next. For most of the history you have just heard, using a computer meant surrendering to it. You learned its codes. You punched its cards. You typed its commands in its grammar, waited on its schedule, and read its errors in its vocabulary. The machine was an oracle, and you approached it the way you approach oracles, carefully, in the prescribed form accepting whatever it deigned to answer. The story of this part is the story of a handful of people who found that arrangement unfriendly, and worse than unfriendly, philosophically backwards. The machine should adapt to the human. And their work is the reason a child can pick up a slab of glass today, and without a manual, without a lesson, without knowing what a file system is, make it do things. The philosophical root is a 1962 report by Douglas Engelbart, whom we met in Part 13, Demonstrating the Future in 1968. The report is called Augmenting Human Intellect, and it is worth pausing on its argument, because it is deeper than any gadget. Tools and minds, Engelbart said, co-evolve. The pencil changed how we think. Language changes what we can think. So the design of a tool is never neutral. A tool that fits the human, that matches our motor skills, our vision, our way of leaping between ideas, does not merely save time. It enlarges the mind that uses it. He called it intelligence amplification, and it stands as the quiet rival to the artificial intelligence dream of Part 15. One camp wants the machine to become smart. The other wants the machine to make us smarter. Both camps won. You carry both victories in your pocket. The first proof that a computer could meet a human on visual ground came from a graduate student. Ivan Sutherland, at MIT, writing his doctoral thesis on Lincoln Laboratories TX2, one of the first transistorized machines with a display, built a program called Sketchpad, finished in January of 1963. With a light pen, you drew on the screen, directly. You pointed at a line and moved it. You could define a shape once and stamp out instances of it. You could state constraints, these lines parallel, this length fixed, and the machine would hold them true as you dragged the drawing around. Every drawing program, every CAD system, every design tool on Earth descends from this thesis. Sutherland's own summary of what had changed deserves to be quoted. In the past, he wrote, we have been writing letters to rather than conferring with our computers. The Turing Award came in 1988, and by then, the whole world was drawing on screens. But Sketchpad ran on a research machine that filled a room. The full vision, a personal machine, graphical, networked, made for one mind, needed a home, and in 1970, it got the most famous one in the history of computing. Xerox, the copier company, flush with money and afraid of a paperless future, founded the Palo Alto Research Center, PARC, and hired a generation of researchers, many of them Engelbart's scattered people, and told them, in effect, to invent the office of the future. They did. In March of 1973, a machine designed by Chuck Thacker came alive at PARC, the Alto. Look at its portrait of the future, piece by piece, because every piece is your present. A bitmapped display, every pixel individually controllable, so the screen could show anything at all, where earlier displays had been limited to a fixed set of characters. A mouse, descended from Engelbart's, now optical. Ethernet, invented at PARC that same year by Bob Metcalfe and David Boggs, so the Altos talked to each other and to shared printers. The laser printer itself, another Park invention, and software to match, because Alan Kay's Learning Research Group was there, working toward the dream Kay had formed back in 1968, a portable computer for children of all ages, a Dynabook, a medium as malleable as paper and as alive as thought. The Alto was the interim Dynabook, and on it, Kay's group built Smalltalk, with its overlapping windows, and others built Bravo, the first editor where the document on screen looked like the printed page. What you see is what you get. And then Gypsy, where Larry Tesler and Timothy Mott worked out the gestures you used 5 minutes ago. Drag to select, double-click for a word. Cut, copy, paste, standardized by Tesler, who spent his career campaigning against modes, states where the same key does different things, because modes are where errors breed. He drove around with a license plate that read, "No modes." The Alto was, functionally, the computer of 1995, running in 1973. Xerox built about 2,000 of them, for itself and for labs, and never sold one as a product. When the company finally commercialized the ideas, the Xerox Star of 1981, it priced the machine at $16,000 and aimed it at offices full of specialists. The vision was right. The price and the audience were wrong. Kay's line from those years has become the motto of every lab since. The best way to predict the future is to invent it. PARC invented it. PARC did not sell it. The selling is where the famous visit comes in, and let us tell it honestly, because the legend has outrun the facts. In late 1979, 2 groups from Apple Computer visited PARC, and Steve Jobs was on the second visit in December. The access was not a favor and not a theft. It was a deal. Xerox's venture arm had just invested $1 million in Apple, buying the right to 100,000 pre-IPO shares, and the demonstration at PARC was part of the arrangement. Jobs was shown the Smalltalk environment, and as one of the people present later put it, he was shown 3 revolutionary things: networking, object-oriented programming, and the graphical interface, and he grasped the third instantly and undervalued the other 2, which tells you both his genius and his limits in one stroke. Apple's people were not blank slates either. Jeff Raskin, who had started the Macintosh project, knew Park's work well. Bill Atkinson had read about Smalltalk as a student. Some Apple engineers had worked with Engelbart's team at SRY. What Jobs carried out of Park was not a blueprint, but a conviction, a proof that the graphical way was the way, and a deadline's worth of urgency. Apple's Lisa arrived in January of 1983 at nearly $10,000, too expensive. And then, on the 24th of January, 1984, the Macintosh at $2,495, with its one-button mouse, its little beige case, and its face. Susan Kare designed its icons and fonts, and she is remembered accurately as the woman who gave the Macintosh a smile, the smiling computer that greeted you when it started, a machine announcing itself as a friend. 2 days before, during the Super Bowl, Apple had aired its Ridley Scott commercial exactly once nationally, a hammer throw at Big Brother, and the product it introduced was, in the words of its own marketing, the computer for the rest of us. The point-and-click era had reached the public. Microsoft followed. Windows 1.0 in 1985 under a license Apple granted for certain visual elements, a decision Apple came to regret, and then to litigate suing over the look and feel in 1988 and losing by 1994, by which time Windows 3.0 had put the GU1 on every office desk, and Windows 95, with its Start menu, was about to make the metaphor permanent. The Xerox conception had become the world's default. Through Apple, through Microsoft, and the arguments about who stole what from whom obscure the larger truth. The ideas were so good that no single company could have kept them, or should have. Underneath the products, a small science of interaction had formed, and it is worth knowing that the rules of thumb on your screen are measured things. Fitz's law, from the psychologist Paul Fitz in 1954, predicts how long it takes to point at a target from its distance and its size, which is why the menu bar hugs the edge of the screen, an edge being, in pointing terms, a target of infinite width. In 1983, Ben Schneiderman gave the field its key term, direct manipulation, the feeling that you touch the objects themselves rather than commanding an intermediary. The command line, remember, never died. It survives wherever power and precision matter more than welcome, a reminder that interfaces are chosen for their users. And different users deserve different ones. And then the last reduction. The mouse was an intermediary too, a proxy for the finger. The finger itself needed screens that could feel, and it needed the industry to unlearn the stylus. The path is littered with the prescient dead. The GRID pad of 1989. Apple's Newton in 1993, whose handwriting recognition became a national joke on the comic pages. The Palm Pilot, which made pocket computing work by making handwriting conform to the machine, a compromise. The old arrangement one last time. The BlackBerry, with its beautiful keyboard. And then, on the 9th of January, 2007, at Macworld, Jobs again, older now, standing on stage and listing 3 products: a widescreen iPod with touch controls, a revolutionary mobile phone, a breakthrough internet communicator. And then, in the rhythm that made the keynote famous, telling the audience these were not 3 devices. 1 device, the iPhone, a multi-touch screen, no stylus. Who wants a stylus? He asked. You use the best pointing device of all, the one you were born with, your finger. The Dynabook, 40 years after Kay drew it for children of all ages, was finally real, and it was for everyone, and it was connected to everything. And within a decade, 5 billion people carried one. Step back and see the whole arc of this part. We began with humans queuing at the machine's door, speaking in punched cards. We end with the machine as a pane of glass in the hand, answering to a fingertip, to a voice, to a glance. The machine did not get friendlier by accident. It got friendlier because specific people, Engelbart, Sutherland, Kay, Tesler, Kerr, and hundreds more, treated the boundary between human and computer as the most important engineering surface there is. They were right. The boundary is where the value is. All the power of the previous 17 parts flows through it, or it flows to no one. And so we arrive at the present. And the present is where a story like this one has to stop pretending to be a history. What remains is the frontier, the quantum machines that promise to unmake the locks from Part 16. Computers grown from biology, built from DNA, wired in imitation of the brain. The question of whether anything, anywhere, is not, at bottom, computation. And one last question, the largest and the oldest, the one that has been quietly running underneath every part of this video since the Ashango bone. What is all of this for? The final part, the frontiers, and the closing next. We end where every honest account of this field must end, at the edge of the map, where the certainties run out. And the first thing to say about the frontier is that the engine of the last 50 years, the one we met in Part 7, has been quietly changing character. Moore's law, the doubling of transistors, was only ever half the story. The other half was Dennard scaling, the rule from 1974 that said smaller transistors would use proportionally less power, so the chip could run faster without running hotter. Around the middle of the 2000s, that rule broke. Leakage currents, quantum effects at a few dozen atoms width, and suddenly every additional transistor made the chip harder to cool, not easier to speed up. Clock rates, which had climbed from kilohertz to gigahertz across the decades, essentially stopped. The industry pivoted to many cores, and in 2011, a study gave the new wall its memorable name: dark silicon. We can print more transistors than we can afford to power at once. Whole regions of a modern chip must stay dark or dim most of the time. Progress continued, but it changed shape, from general speed to specialization. Graphics processors, tensor processors, chips built for one kind of mathematics done extremely well. The free ride became a negotiated one, and beneath that wall there is a deeper floor, and it is one of the most beautiful ideas in this entire story, because it says that computation is not an abstraction floating above physics. It is physics. In 1961, an IBM physicist named Rolf Landauer proved something astonishing. Erasing one bit of information costs energy. Not approximately, not as an engineering inconvenience, but as a law, a minimum of kT log 2 joules per bit, a tiny, real, unavoidable puff of heat. Forgetting is thermodynamically expensive, and the conclusion inverts the way we usually think. Information is not a ghost that rides on matter. It is a physical quantity, like momentum or charge, and manipulating it obeys physical law. A few years later, in 1973, Charles Bennett showed the loophole hidden in Landauer's law: only erasure costs. If a computation never throws information away, if it runs reversibly, keeping enough history to retrace every step, then, in principle, it can run with no irreducible energy cost at all. Physicists have since built the experiments that confirm Landauer, measuring the heat of deleting a single bit. The laws of computation and the laws of thermodynamics are written in the same language. That would not have surprised the people at the 1981 MIT conference on the physics of computation, because that conference is where our next frontier was born. Richard Feynman gave the keynote, and as usual, he went straight to the embarrassment everyone else was politely not mentioning. A classical computer cannot efficiently simulate quantum mechanics. A quantum system's description doubles with every particle you add. A few hundred entangled particles already require more numbers than there are atoms in the visible universe. And then he turned it around in the line that founded a field. If you want to make a simulation of nature, you'd better make it quantum mechanical. If nature computes quantum mechanically, build a computer that does the same. In 1985, David Deutsch at Oxford gave the idea its formal shape: the universal quantum computer, a machine whose bits are quantum states, qubits, each one not 0 or 1, but a weighted fog of both, entangled with the others, so that the machine's state lives in a space that grows exponentially with each added qubit. Then came the algorithms that made governments nervous and physicists famous. In 1994, Peter Shor at Bell Labs showed that a quantum computer could factor enormous numbers in polynomial time, which is to say, it could dissolve RSA, the lock on the world's secrets from Part 16, the moment such a machine exists at scale. That is why the post-quantum standards we mentioned there exist, new locks being fitted years before anyone is sure the old ones will break. In 1996, Love Grover showed a gentler but broader gift, a quadratic speed-up for search of any kind. And in October of 2019, Google announced that its 53-qubit Sycamore processor had performed a task, sampling the output of a random quantum circuit in about 200 seconds, estimating that the best classical supercomputer would need 10,000 years. Quantum supremacy, the headlines said. The honest accounting is more modest and more interesting. The task was chosen to be easy for a quantum machine and useless for anything else. The classical estimates were improved within weeks, and the result's real significance is exactly what Google's own team said it was: the first experimental evidence against the extended Church-Turing thesis, the belief that any reasonable computing device can be efficiently simulated by an ordinary one. A wall in the theory of computation, the theory we built in parts 4 and 10, may have a door in it after all, and the door is made of physics. The wall that remains is error correction. Qubits are the most fragile objects humanity has ever engineered. The enemy has a name: decoherence, the collapse of the quantum state at the slightest touch of the outside world. A stray photon, a breath of heat. And a useful machine needs many physical qubits to protect each logical one, thousands for one, by some estimates. Between today's noisy devices and a machine that threatens your bank lies possibly decades of patient work. Nobody knows. That is what frontier means. While one wing of the field dives down toward physics, another wing climbs up toward biology, and the meeting point is strange and wet. In November of 1994, the same year as Shor, Leonard Adleman, the A in RSA, published an experiment in Science that reads like fiction. He encoded a small, traveling salesman-style problem, the directed Hamiltonian path, into strands of DNA, cities and roads as sequences of bases, mixed them in a test tube, and let chemistry do what chemistry does. Trillions of molecules tried trillions of combinations in parallel. And with enzymes and filters, he read out the answer. The first molecular computer. The catch, which everyone saw immediately, is scale. Parallelism in a test tube is vast, but the mass of DNA required explodes with the size of the problem. And reading the answer takes days of lab work. DNA computing did not replace the laptop, but the sibling idea, DNA as storage, is becoming quietly serious. In 2012, George Church's group at Harvard encoded an entire book, Church's own book, along with images and a program, into DNA at densities around 1 million times that of a hard drive, because DNA stores in 3 dimensions, and a gram of it could, in theory, hold hundreds of petabytes. Your civilization's archives may one day be kept in a few grams of the same molecule that built you, readable 10,000 years from now, long after the last spinning disk has died. There is a poetry in that which I will not spoil by underlining. And then there is the computer you are using to hear this, the 3-pound one between your ears. 86 billion neurons, running on about 20 watts, less than a light bulb, out-computing, in every way that matters for living. Machines that draw megawatts. The von Neumann architecture we described in Part 5 and 6, the separation of memory and processor, the endless shuttling of data back and forth, is the source of both our machines' power and their appetite. The brain has no such wall. It computes where it stores. Neuromorphic engineering is the attempt to steal that trick. Chips like IBM's True North and Intel's Loihi, built from spiking neurons, event-driven, sipping watts where a graphics card gulps them, learning on the chip itself. They are research machines today. They are also a reminder that the most successful computer ever field-tested was never designed at all, and that the field's deepest current rivalry, the one from Part 15, logic against learning, symbols against neurons, may end not in victory, but in some architecture that, like the brain, refuses to distinguish them. There are quieter probes at the same wall. Chips are going vertical, stacked in 3 dimensions, because the flat plane is running out of room. Optical computing, routing photons instead of electrons, sits in the labs. So do transistors made of carbon nanotubes. And on the software side, the defining problem of the next decade may be verification, the art of proving that a system does what we think it does, which becomes hardest exactly where the systems are learned rather than written. Understanding what a trained network knows and guaranteeing what it will never do is an open frontier, and the stakes of leaving it open keep rising. One more idea, and then we can rest. In 1989, John Archibald Wheeler, who coined the term black hole and taught a generation of physicists, published an essay asking the oldest question, how come existence? And gave it a 2-word answer. It from bit. Every it, every particle, every field, every feature of the physical world, he argued, derives its significance from bits, from yes or no answers, from information. The universe, at the very bottom, may be informational. Physicists and philosophers still argue, fiercely, about how literally to read him. And we will not settle it here, in the dark, at the end of a long story. But notice what it would mean. We began this video by asking what a computer is. We end with the possibility that the question was backwards. Not whether the universe contains computers, but whether computation is one of the things the universe is made of, like matter, like energy, like time. So let us close, slowly, the way we came in. We started with a bone. 40,000 years ago, or 20, on the shore of a lake in Africa, someone cut notches into a fibula, and in doing so, performed the act this entire story is about. They took a thought, a count, a tally of days or moons or debts, and put it outside their head into the world, where it could outlast them. Every artifact since has been that act, elaborated. The tally stick and the quipu, the abacus and the zero. Al-Khwarizmi's little book, whose author's name we still speak every time we say the word algorithm. The loom that wove with cards, Babbage's engine and Ada's notes, the first time anyone fully saw that a machine could manipulate anything that could be symbolized, music, language, law, and numbers, were only the beginning. Hilbert's dream, and Gödel's wrecking ball, and Turing's small, plain machine that could compute anything computable, and the discovery, immediately afterward, of everything that could never be computed at all. The war machines, built in secrecy and haste. The transistor, smaller than a fingernail, and then millions of them, then billions. The languages, the operating systems, the networks that sent their first 2 letters and crashed. The web, given away. The databases holding the world's facts, the algorithms quietly sorting and searching underneath everything. The ciphers keeping secrets in public. The interfaces that finally bent to fit the hand. The machines that learn. The machines, perhaps soon, that compute with the deep grammar of matter itself. And through all of it, one pattern repeats so reliably, it might as well be a law of this field. Every generation builds a tool and discovers it has built a mirror. The counting tools showed us that thought could be mechanical. The logic machines showed us that reason had limits. The networks showed us that minds are for connecting. The learning machines are showing us, right now, uncomfortably, how much of what we call understanding may be pattern and scale. Each invention tells us something about the universe, and something less comfortable about ourselves. What is all of it for? The honest answer is the old one. It is for the same thing the tally was for. To hold a thought outside the skull. To share it across a room, then a planet. To ask questions too large for one lifetime, and hand the partial answers forward. A computer is the current form of the oldest human habit. The habit of making our thinking durable and shareable. And the people in this story, from the unknown carver at Ishango to the student in Helsinki who announced his hobby to a news group, are one continuous community, separated by millennia, working on the same project. The project is not finished. The walls from Part 4 still stand, and always will. P versus NP is still open, with its $1 million bounty and its quiet suspicion that some truths are simply hard to find. The quantum machines are still fragile, the learning machines still opaque, the software still late, the secrets still hunted. Somewhere tonight, there is another student in another small room, writing the first lines of something, just a hobby, that will not be big. There always is. You now know, in outline and in some depth, where computation came from, what it is, what it can never do, and where it is going. Let it settle. The tally marks, the gears, the relays, the gates, the packets, the neurons, one long counting, from a bone by a lakeshore to a machine that dreams in text. You are there for all of it now. Sleep well.